Mop, mop, mop.
Fucking stereo. Let's stop.
Baby, can't you see when you look at me? I can't keep this feeling when it hits. All alone in my bed at night, I grab my pillow and squeeze it tight. I think of you and I dream of you all of the time. What am I gonna do?
Ladies and gentlemen, welcome to the second day of Airtec. We'll start the presentations. And the first speaker is Professor Alexander Knoll from the Technical University. Oh, okay, University of Applied Science in Munich. And he speaks about future challenges for artificial intelligence in aerospace.
So, good morning, ladies and gentlemen, also from me. Good morning to the persons over here and to all those at home at the TV screen. So what I'd like to present is I'd like to talk about future challenges for artificial intelligence, especially in the field of aerospace industry. So first of all, what's special with this term aerospace? So I think we do have extreme requirements. Extreme means, for example, safety is a major issue for all our applications, basically because failures might always result in the loss of life, of course. Then we do have something which is also a little bit different from, for example, the automotive industry. In automotive industry, there is always a solution just to drive to the right lane and stop the car. If you have an aircraft which is in the middle of the transatlantic, forget this solution. So this also means we need some alternatives or alternative ways to go on. This means we should have a dedicated high level of quality. We, of course, invest a lot of money into research. We do have also very special certification requirements, and this has pro and cons. Pro is just certification ensures that you are not doing a failure twice, not more, because certification basically is made out of all the experience you had in the past. So everything you know is hopefully covered. But the problem is if you are going to completely new technology, there is always a chance that there is something new you don't know before. So this is something you have to keep in mind when switching from established techniques to new techniques. Or basically, this is perhaps the solution why our industry is also quite often called a conservative industry. So, and what's the result of all those things? We do have long product cycles. So, next thing is what's currently hot, or what's hot topics under discussion. This is, of course, electric propulsion. You heard about additive manufacturing. You are going to hear a lot of lectures on this today. Artificial intelligence and the combination of all those within urban air mobility. So, what's the current situation? Currently, we do have a fierce competition between different concepts, which are enabled by those new technologies, for example, these technologies regarding the electric motors and so on. So this is a positive thing. Then the effect is also due to the big amount of new technologies which are right now available. This means there's a chance, a good chance, for new competitors to come to the market. So this is a major change which might be possible right now. But of course we do have other effects, Corona, something which nobody needs at all, of course, which is going to restrict perhaps research budgets, hopefully not. But nevertheless, we don't have any chance to avoid it, so we have to make the best out of it. Good. What's now regarding artificial intelligence? What are the goals? Of course, number one goal is to improve the flight safety. So this means basically there are two possibilities on this. Possibility number one, combine the human with the artificial intelligence, which means basically come up with new assistance systems. Or, the second way, come up with autonomous systems, which means if we are going to exclude the human from the whole system, then we have to find ways to get those capabilities which are special to the human, to get those capabilities to the artificial intelligence. And this is something I'm going to talk about. And of course, improved sustainability is part of the whole game. And economics, which is availability, for example. So, first of all, just some examples for autonomy projects, examples you already know, so this is nothing new for you. So, among those, there are quite a lot of those projects. This is just a small selection of it. There's this new product of Garmin, which basically allows even auto land. So the idea is for small aircraft which are typically owner flown, there's just the owner as a single pilot in there and his family, which is not accompanied to flying. So the idea is if this pilot is going to leave, is no longer able to fly the aircraft, you just push this auto land button, the system gets via dedicated data connection, gets information on all available airports how the weather is there, the available approaches there, and then the system does the complete flight from pushing the button until stopping the engine on the runway, completely autonomous. And this is, I think, a major improvement. And they are already offering this system with 3 different aircraft, and they are going to apply to it to much more. But a major thing is it's an auto-land system. Auto-land in case of an emergency. So certification is different from normal operation. It's just in case of emergency, and this means a lot of certification requirements are eased up or are only fulfilled to a certain degree to fulfill this emergency thing. Okay, this is one thing. The other project, this is what Airbus is doing or had been doing, this ATOL project, autonomous taxi, takeoff and landing. The idea behind this project was basically to do automatic landings just based on visual cues. So there's a camera, there's artificial intelligence, and this is going to guide the aircraft to the landing. And they proved this, as you see, with quite a lot of flights, and they did automatic taxiing, automatic takeoff and landing. And right now this campaign is already closed. They are doing a new campaign, but the basic idea is, of course, assist the pilot and, in the future, perhaps reduce the number of pilots on board the aircraft. So there's quite a lot of things going on in this technology. So what are the gaps, according to my opinion, in current implementations? So I think current systems, they already fulfill several tasks. For example, they fulfill basically isolated problems which have a relatively predictable behavior. The result may be reproduced with a limited effort, and failure handling is mostly done right now by redundancy. So if we have a problem which is, or a system which is failure prone, we just duplicate it or whatever, and this is quite a solution we use quite often. But I think it's not the final solution for everything. Because what's lacking in current systems, according to my opinion, is cross-system intelligence. So right now, all intelligence we do have is limited to dedicated systems. But there is basically not one system which is going to be connected to all systems in the aircraft. It's always just parts of it which are connected. Resilience, I'm going to talk about this in more detail. Cross-system learning capability, and all this basically is going to improve the failure handling capability, which is a major issue if you are going to increase autonomy. So, cross-system intelligence, what I mentioned. What's different from current systems to old systems, old-fashioned systems? Current systems are more and more software-driven. And this means having software-driven systems allows that in case of a failure, the system is not completely gone, but instead there is some degraded mode with a degraded capability available, which is fine, of course, but it also means that the system might handle different from now on. So this means the moding, to understand the moding of a system gets more and more complex with those software-driven systems. Of course, there's an advantage. It's no longer on-off, but it's more complicated to understand. And there are interdependencies which are much more complicated. For example, with one transport aircraft of a big European manufacturer, the problem is, there's no problem there, or at least in old versions, there was a thing that EHAS, Attitude Heading Reference System number 1, is connected to the weather radar. you do have 3 attitude heading reference systems. So if one is gone during the flight, there's no need for a precautionary landing or so. You still have 2 and in addition the standby system, which is fine. But what not too many people knew, at this time at least, is that the weather radar is just driven by EHAS number 1. So if you are losing EHAS number 1, you don't have weather radar capability. And this is, especially if you are in a place with a lot of thunderstorms around, it's at least a little bit surprising. So this makes this interdependencies between the systems makes it a little bit more complicated right now. So what I think, we need a monitor of systems which is really cross-system. So resilience. Resilience is, as I would call it, the capability to react on unexpected situations with a new strategy. And this is, I think, a core capability of the human, which is right now not always implemented in our technical systems. So it requires learning capability. And this is perhaps a problem, because learning means that the system under certain conditions is going to react differently. And our current credo of certification is repeatability. So everything is going to handle the same situation always the same way. Learning is opposite. So this means repeatability is in contrast to learning, and this is a problem regarding certification. So cross-system monitoring, the first point I mentioned. So let's see what the human does and whether this could be a clue how to go on with technical systems. So the pilot basically is going to develop a mental model of the aircraft behavior. This mental model means he memorizes connections or correlations between different systems, flight controls, environmental conditions, and so on. And so he gets this, I call it, relational physical model. So this is no model which has numbers on it, exact limits or so, but it's just a model which allows to understand how the system is going to react. And this also allows the pilot to interpret indications which might be contradictory or might be at least strange. So he has some capability which allows him to look behind the scene of the caution indication or whatever. But all this, as I said, requires learning capability, what we call the feeling of the pilot. And this also requires the capability to manage the computational resources. What do I mean with this strange phrase over here? I'm talking about this, perhaps you know the book Thinking Fast and Slow from Kahneman. Kahneman describes in this book the behavior of the human. And he says, basically what the human does, he has 2 different versions of systems inside his brain. System number 1 is coping with all standard cases. So this means you don't really notice what's going on. You're not aware of this. So that's just the standard thing. And the second system is for, I call it here, increased attention. It's for all those things where you really have to think about, where you really have to make decisions you are aware about. And by the way, the human is lazy, which means most of the time the human tries to avoid system number 2. Do it via system number 1, and only if it's really necessary to think about it, then we are going to use system number 2. And perhaps this is also a way to do the management of the computational resource. Basically to have part which is just doing the routine things, which could be fast and so on, and there is the other part which does all the non-standard tasks. And I think this might be a way to go on regarding this. So resilience by customized learning behavior. So what's this? I already mentioned we need resilience for sure, because if you are going to develop an aircraft, it's impossible to predict all situations which might come up during the lifetime of the aircraft, for sure. So you need the capability to solve new problems, basically, and this is resilient. So how do we implement resilience? Of course, it has to be a stepwise process. One step is just analysis of the current situation. Second is forecasting. Third is come up with a new strategy. And 4 is, of course, again, this monitoring, which is back to step number 1. So this means basically learning capabilities result in modified behavior, as we already said several times, and this is something which has problems regarding our current opinion regarding certification. So adaptive learning, what I call, needs 2 capabilities. One is learning during normal operation. Here there is some technique called supervised learning, which might be fine. So this means the system is going to learn over the normal lifetime, and afterwards the human is going to check, is this correct? And then it's going to be implemented in the whole fleet or whatever. But it is not going to fulfill the second term. Second one is learning in emergency cases. So this means you need something else, a second type of technology which allows you to do fast decision making. And our idea is we are going to work, we are really at the beginning of this, so there's a lot of work to be done, basically to come up with a model similar to the model the pilot has, and based on this model, allow for fast decisions in cases you have never known or have never seen before. So basically similar to what the pilot does. So build up during normal operation a model and then use this model in these rare cases. So this is what I just said. This statistical relational learning has some advantages. It basically, what it does, it makes a correlation, or it shows if things which do have a high probability. So it looks to all those correlations and then sees which correlations do have a high probability, and this is what it's going to learn. So the advantage is basically it allows you to limit the extent of the learning, but it needs a time history. So, and certification is an issue, of course. Perhaps statistical proof of evidence might be a way. But as I said, we are at the very beginning of this, so we will see whether this is good or not. And just the final thing, I think, what you shouldn't forget when you're talking about artificial intelligence is still the human. Because artificial intelligence is not working in a place where no human is around. So this means it works in an environment which is full of humans. So you need an interface to show what's going on. And the interface has to be different from the interfaces you have right now. Because right now, basically you show the status of a system, it's on, it's working, whatever. Here, it's a system which is has much more intelligence, or is much more clever. So you have to show basically what the system really has as a strategy, what its plans and so on. This you have to communicate. So the interface have to be quite different. So difficulty, as I said, showing complex decision process to the human and enabling the humans to predict the behavior of the system. Okay, good. So conclusion, humans do have considerable gross system capabilities, even if they don't show up every time. But nevertheless, basically they do have. And this is a necessary thing, I think, which is really vital to autonomous flight operations in the future. So a lot of effort for research is necessary, and yeah, this means a learning process, and the learning process, which is part of resilience, basically is something which is in contrast to our current philosophy of certification, and so we have to come up with new ways of certification which are perhaps not centered about repeatability, but about limiting the influence or whatever. So this is what I'd like to show you. Good, thank you for this.
Thank you, Professor Knoll. Do you have any questions? No questions? Then I have a question. If you compare autonomous flying to autonomous driving, what do you think? Which is more complex in the, I would say, decision-making of the cognitive system, for example?
I'm not going to answer this question. Why? Because when I'm going home to the university, all my automotive colleagues are going to shout at me. So what I'm going to answer is a different application. Automotive means you have really short decision times. You have to do this in millis of seconds. But the solution could be within a limited time frame. We, in aerospace, we have long time for decisions, quite often, not always, but in cruise flight, we do have quite long times to make a decision. But we have to live with this decision for hours, perhaps. So it's a different environment, and I cannot really say it's more or less difficult. I think it's better to put it this way, otherwise I might get into troubles with all the other colleagues.
Okay, another question. You talked about self-learning systems. Yeah, so far as I know, for example, in a Tesla, there is also a self-learning strategy which is trained by the driver. If you think about learning from a pilot, for example, I think this is not an easy situation, yeah, to get a license or something, or to a release for this, because one pilot, yeah, has a competence, a good competence, another not so good competence. Yeah, how do you think you can get a license for this?
Yeah.
Yeah.
I'm not talking about learning from the pilot during a flight. This, I think, wouldn't really work. I'm a pilot too, so I don't think it works. But nevertheless, I think we, as engineers, as psychologists, whatever, we know capabilities the human has, and we are trying to implement those capabilities into the system. I'm not thinking or talking about learning from the behavior the pilot shows during a real flight. I know it's not always this behavior a pilot shows could be used as an example. Sometimes it's better to do it before and not during the flight.
Thank you, thank you.
Thank you.
Okay, we come to the next presentation. It comes from Airbus Helicopters, from Dr. Christian Seidel, who is the responsible person.
From Airbus Helicopters. I'm working in mostly in Donauwörth and also in Marseille, Marignane, our plant. We have a big department on avionics, obviously, which is not only integrating the system but also preparing the future for our helicopters. Helicopters are our most sold momentarily objects, but we are on a path to a new future where the aircraft itself is just an asset which you take as a vehicle and you add your mission systems, and when it comes to urban air mobility, it's a completely different vehicle. So it's a huge span we are covering here. Just to mention this, maybe it's not everybody is aware, Airbus Helicopters is a division of Airbus we are a 6 billion euro company all across the world and roughly 20,000 employees. And also what's interesting to know, we are, let's say, half military, half civil. So we are fully integrated military civil. Some of our platforms are militarized from civil platforms, which gives us opportunities and potential for new developments. Also, we make some business with the services. I mention here now what are the missions we are covering. For the civil ones, the best example is always the helicopter emergency medical services. When you see the ADAC helicopters flying, they are all coming from Donauwörth, DRF most. So, and these are demanding missions which require always a very present pilot who's hands-on, knowing what he's doing and needs to be very well trained. On the other hand, even more so in the military range, where we cover also all the missions which are not only the flying itself, but also the helicopter is just performing a mission to reach an objective. My talk is about artificial intelligence. Airbus Helicopters is not an artificial intelligence company, but we are seeing artificial intelligence as an enabler. It's a range of technologies, it's not just one. Mostly heard about today is machine learning, but this is not only the only thing we want to deploy, but it's a range. As Professor Knoll said, and it was really a perfect introduction to my talk, not only an introduction, it was a very good basis. And maybe I can complement a little bit on some of the parts he has mentioned where we are. And I'm saying autonomous flying will require artificial intelligence. Maybe it's not the deep learning. This is, let's say, a sensing optimization, but it's the decision making and the cognitive intelligence which will be required. What we are differentiating, and this is not only in aerospace the case, you have to differentiate between AI in the enterprise, where you use it in processes, in manufacturing, in developing, in engineering, and in the products. Professor Knoll mostly talked about the products, obviously, which you deploy in the aircraft or for the actual flying. We have also to see that there's a lot of opportunity of AI in the processes. Coming to the world megatrends, and there I'm coming back to what I've seen yesterday in a lot of talks. Why are we doing all this, and what's the momentary state? I don't want to repeat what was said yesterday in the talks a lot, but there will be a lot of megacities around. So there's the commercial traffic is increasing. Okay, we have a situation at the moment where this is not the case, but it will most probably recover in the next years, and afterwards we will see how the increase will look like. And on the other hand, that's the need, and there's also the possibility, because we are in technological breakthroughs, and you see this in the automotive range, but also you see this in the data dimension. We can store a lot of data which was not available before, and learn from this and use this to come farther. I'm going out to some applications, not in detail, it's far too much, but also you have to consider that there's a lot of potential in of AI, for example, in production. You can combine learning system with humans on routine tasks. It might be more easy to use a machine which has learned to do, and then combine it with a human who can really knows the problems, has the competence and the experience to really show the machine in which direction it's going. Complex operations which require a lot of routine but also attention might be easier to be done by artificial intelligence, which has learned to do it. Obviously in logistics and supply chain you have a lot of opportunities where you can, demand management is easy to, is a very complex system, but on the other hand it's just data which you have to compile, and that's a strength of artificial intelligence. We also see it, and are already using it in the maintenance range, in the services. We have a system which is called Skywise, where we store a lot of aircraft data from after flights, and from this you can learn a lot on first the usage, and second also on the problems and the wear of the machines. And from this you can easily derive, if you have this huge amount of data available, derive new information which cannot be seen by a human by simply looking at some of the information. One I'm going in is the fault localization and status monitoring. AI allows to detect anomalies in data and also to learn from the past to find these. We can use this to simplify some processes in our monitoring system. HAMS is the word for health and usage monitoring systems. We have a vibration condition indicator, which we have now checked via machine learning. Just an example. I don't want to go into the detail of this example, but what we see is artificial intelligence allows us to better understand and better predict behavior just using a few parameters, and that's the asset. So we don't need to have a full-blown model, but we can use a few parameters to predict what's going on. And here in this case, what does the vibration mean? Are we still in the nominal case or already in a critical case? Vibration is a problem, for example, of gearboxes, which you might have heard of in the past. Would be the same in turbine engines, where you see from the vibration that you have that a maintenance task, for example, is due. Can make on-condition maintenance. Now I'm coming closer to my range where I'm working. Next level is you don't have to go to the product to use it in engineering, because we are there. You can, for example, simplify huge computational effort calculations, like simulations by artificial intelligence. You train it with the existing data you had, with the models, not with the models, with the results of some model calculations you have done, and you can more easily predict when it comes to variations in the input parameters. You can predict the output by artificial intelligence much faster. You can make more calculations, which means at the end you can optimize better because you can make more calculations. An example could be rate reduction through optimized models and more calculations done in the same time frame. And now I'm coming to the product, and I'm directly going into the topic which Professor Knoll before me has mentioned. And here I'm showing a picture of my fixed-wing colleagues. It's a commercial airliner. You see the crews, which have how they were built up in the past. You see two pilots on the upper left, two pilots, navigation operator and a comms operator for the communication part. This role then in the second part is done by one person, because you have simpler interfaces. You don't have to tweak too many knobs at the same time. Nowadays you have only two pilots, because a lot of systems are already automatized, are easified. The human-machine interface is much more comprehensive, and you don't need to do so many actions, which is already the way. But still the pilot is flying, not in all cases, but in many cases hands-on, as we say. So he's using his stick and still flying. In the fixed-wing vision we see in the next step, and the ATOL project is one of the bricks which is going in that direction. We see the human as only the strategic decision maker. So this hours range, which Professor Knoll was mentioning, is still done by the human, but the short-term decisions and actions are done by the aircraft itself. So the pilot gets a supervising role, a monitoring role, and he checks if it's according to plan. And in case of deviations, he will react and take over to a certain degree, whatever this will be then. The vision is here is to go directly to autonomy. This is not realistic when you have hundreds or more people on board in the back. This is not the next step, definitely not. When it comes to closer aircraft, you can see it's always a matter of impact you can have when it comes to a failure. But here we don't see it. Cargo aircraft might be the first part where you go for autonomy, and then you go to manned with passengers on board. This by the way is called single pilot operation. So when you hear this, it comes from the normal crew concept of two pilots to single pilot operation. I take this picture also to show the consolidation of interface, the consolidation of intelligence already in the machines today. We have to automate more to come to this position, and you can see a lot of functions which you can then, which are done by the pilot today, and the next step be done by the systems on board. Permanent out-of-flight flight envelope protections. So today, especially in the helicopter, which is not in the same situation as a fixed-wing aircraft, it's not that automatized already. We are far away. The absolute authority is with the pilot, and but you can start to warn him when it comes to, for example, flight situations where he shouldn't be, which like too big angles, bank angles, for example. And then warn him, and then the next time the system can interact and say, okay, I correct, and then it comes in the next step. You can have, for example, a pilot supervision, monitoring if the pilot is still healthy and okay, and if not, in emergency mode could be started. We're talking about virtual assistants. You have seen in the picture also in the first one of Professor Knoll an actual assistant, which is a robot arm, which is using in a normal cockpit as of today, acting as a second pilot and then really pushing the buttons and checking the interfaces. Now, VTOL, vertical takeoff and lift. It's not only about city Airbus, which has recently been transported to Manching from Donauwörth to have a bigger test range. But it's also about cargo drones, it might be. We had a Skyway system in Singapore. In the military range, it's about surveillance drones, which fly their missions autonomously, which are autonomous, which are then just an asset in a bigger tactical picture. And then we have also this UAM blueprint for urban air mobility, which you've seen on all our competitors' presentations yesterday. We are in a consolidation phase, and a lot of things look similar and are going in the same direction, but we have all our unique parts in it. So this is now where we are going to see, and an essential brick in this, for example, now I go a little bit more into artificial intelligence as of today, not the longer term vision, but as of today. What do we want to do? Also, when you look at the video of the Atoll fixed wing project, where you see an aircraft autonomously or automatically somewhere in between landing, based on vision-based navigation, deep learning for vision systems, computer vision. So you will see that the complexity of the scenery, and that was also the question before, is, let's say, limited, because a fixed-wing aircraft always lands on a runway, which makes the situation a little bit more easy, I would say, and I hope I don't get into trouble with my fixed-wing colleagues, than for a helicopter. So first we want to automatize the segment of a flight for a helideck, which is similar to an airport, but not as controlled and not as monitored, because you don't know if there are obstacles in the way, if there's a car standing. If you imagine a hospital landing deck, you don't know if an ambulance car is still parked there, because the processes are not the same as on a fully supervised and monitored airport. So the next brick for Atoll means I have to identify where I am. Okay, GPS is a help, but it's not sufficiently there. We don't have precision-based navigation approaches in all the airports, which is an infrastructure asset which we want to avoid. So you need to know it by yourself. You can use simultaneous localization and mapping based on the vision systems, where you get your position and also a 3D environment. Then we will have computer vision to detect obstacles, which is, let's say, state-of-the-art in automotive. You know the pictures of bikes and cars and SUVs and whatever. We have wind turbines, pylons, trees, buildings, which is essentially the same problem, and we use the same algorithms, but we have to, in the usage of artificial intelligence, and this is why there are also so isolated solutions, is the approach is generic, but when it comes to the actual implementation, it gets very specific, because you need to train it on your classes of objects, and this is where the effort then is. And then now try to get like in car case, 5 million pictures of a wind turbine. Difficult. No? So it's much more, it depends definitely on your environment in which you are working, how good you approach data. And the second thing we are testing is also to do this in IR range or in different wavelength ranges, because we are not flying only in daylight, but also at nighttime or in degraded visual environment, where other systems might be of more help because they can look through or look in reduced light conditions, for example. You know, these pictures, they are always the same, but here it's the wind turbines. This is about the simultaneous localization and mapping. You can get these results when you have, you see, for example, stereoscopic camera, you take it on the scenery, and by moving, you get the information of the points around. You get 3 pixel clouds, point clouds, and your own position inside those. And with the map matching, for example, you can do georeference positioning. And what is also wished by a lot of customers and also by us is to detect non-cooperative traffic. And you see some examples here. They come actually again from the ATOL project, because where our commercial airliners normally are flying is completely controlled airspace. So there should be no other aircraft around. You can fly fully on instruments. This is not the case for helicopters, and this might not be the case also for the others in the future, because you have a lot of drones which are flying in every direction. Imagine Amazon is starting a full delivery system on drones. How many drones you will have around? We're talking not about thousands, we're talking about millions and billions of drones in the world which are flying around. So a next potential use of artificial intelligence, because of the strength in calculating the sensor information you have, is detection of non-cooperative traffic. And then to see in this picture, differentiate a drone from a bird is difficult. And our experience shows when you can see it as a human, the machine can see it, but the border is quite similar, depending then obviously on the resolution of your cameras. So, as a conclusion, complexity is increasing and artificial intelligence contributes to master it, to say it cautiously. Thank you.
Thank you very much for your presentation. Do you have any questions? Okay, then I have some.
Good.
Okay, you spoke about autonomous flying and one-pilot solutions for flying. What do you think? How long will it be before you have a one-pilot solution?
Okay. The real one-pilot solution is a dream of a commercial aircraft and an airliner, because you can save the crew. And only then you have the full solution. Before, if you still have to have 2 pilots on board, but you could fly it with 1 pilot, that's not what we're talking about. I think we are talking about the real solution when you have an actual single pilot operations cockpit. And how to say now a time frame. Maybe, let's say, what we are talking about in Airbus is on the cargo range, the single pilot operations will be in this decade.
Another question. You show a nice spectrum of a vibration measurement. And you said you compare it to the reference. Do you see any early indications of wear, which you are not seeing, for example, by MRO or something?
Yes, this is even, let's say, easier in a sense, because you can test the machines on ground and you don't have to do it in flight. And we have a lot of examples where you use artificial intelligence from learning from the past to detect faults in test environments, for example, vibrations. In flight, it should be possible, but then you need to know how it looks like. So you need to make the reference between the already existing fault and your vibration spectrum.
If you look onto a completely different industry, the wind energy industry, then there is lots of problems with gearboxes, for example. Mm-hmm. And what you presented is maybe also really attractive for them. Do you think it's possible to use your technology also for this kind of business?
I'm sure, because it's actually the same issue. And as I said before, the approach will be the same, I guess, but the specifics have to be implemented and learned.
Okay, let's talk with each other. Maybe it's interesting. Okay,
Yes,
thank you again for your presentation. Okay, we'll come to the next talk. Now I have the information for you that we have a problem. Dr. Simon Kote from Fraunhofer Institute became ill. Yeah, I was just informed. We come to the next following presentation. This is Dr. Gunnar Merz from Composites United. He's the CEO of Composites United. We'll talk about future factory for composites, and hopefully he's on the line. One moment. Okay, Dr. Gunnar Merz is on the phone. He will put in the line as soon as possible. One moment, please.
So, yes, good morning, Dr. Günewig. Thank you very much for the introduction. I hope you can hear me. So, I'm here virtually, and it's a pleasure also to start a little bit earlier as Mr. Kote is ill today. So, good morning, ladies and gentlemen. A warm welcome on behalf of Composites United. The topic for today in my presentation is Future Factory for Composites. I would like to give an example from German Aerospace Center, from DLR. I will talk also about the role of the human being and the role of 5G net, which is, of course, also very important, and also the importance of sustainability, which plays more and more a very important role. And finally, I also would look. So starting maybe with the first slide, I hope I can see it as well, because at the moment okay, perfect. That is, before I start, so I have to say many thanks to Dr. Jan Stübe, because he was providing a significant input here for this presentation, so that I can show you firsthand state-of-the-art future factory for composites. Next slide, please. So this is the agenda. Basically, what I said, I would like to talk about an example from German Aerospace Center, DLR. I would also talk about the role of the human being, which is very important in future. Also the role of the 5G net and the importance of sustainability itself, because this is more and more an important criteria to judge and make a decision on materials or processes. Recycling is in this context very important. And finally, I would like also to give a small outlook. Next slide, please. So here's now the key question. Future factory for composites, how does it look like? Next slide, please. So you see here actually a model of the future factory for composites. And on number one, first to mention, is the human-robot collaboration, which is very important. Robots and the human co-workers interact in safe and efficient industrial applications. In number two, you see the mobile manipulation, which means mobile autonomous production unit support by carrying out backward. Number three is the autonomous assembly, which is also very important, of course. The robots running autonomously, assembling individually customized products. Number four, you see the part additive manufacturing, like 3D printing, for very complex parts. Then number 5, very important, are the so-called digital twins, whereby comparing model and reality processes are optimized. I will give an example in a minute to explain this in more detail. And number 6, finally, is the digital guidance, which plays an important role, for example, to minimize setup times. Next slide, please. This explains now an example for the digital twins of machines. You see here a virtual autoclave and the real autoclave. And both are compared, and by applying a sensor system, you can really optimize the real process by using data from the virtual process. And they are controlling each other, and then they are improving themselves so that you get more and more efficient. This is very important in composite technology because you have to run an autoclave for a long time. And of course, you need to automate and you need to improve the setting time so that this can be actually run faster. This is a picture which shows actually the largest research autoclave in the world, which is located in CFK Nord here in Stade at the German Aerospace Center. Next slide, please. Very important is the role of the human being, of course, in this automation. The over-automation is like production hell. You see here a citation from Elon Musk from Tesla, because he was finding out that it's still very, very important that a human being is interacting and taking control here, because the robots also can slow down production, and it's very important that the human being is involved. Learning element for Industry 4.0 is that the human skills are very, very important. Next slide. Here you see how the human-centered digitalization in lightweight construction plays an important role, how the human being is really interacting in areas like manufacture, design, assembly, and so on, because the human being can interact, correction of processes, and also can interact in joining of substructures, for example. And this is very important. So this is a clear tendency. You do not rely really on robots. You have the interaction, the human-centered digitalization. Next slide, please. So why does the human-aided automation work for composite production? Here are some examples. In composite production, possible sources of errors are very individual. In case-by-case decisions, humans are superior to computers. You might remember the landing on the moon, which would not take place if computers have done for their own. The human being need to interact. This is also the case still in composite production nowadays. You can step into fully automated processes physically to detect a problem would be difficult. Virtually, it's of course possible to do that. And automation suspends humans from interaction. Digitalization brings human back to involvement, which is also very important, that the human being really is involved in the process. So therefore, this is the human-aided automation for composites production. Next slide, please. Yeah, this actually would have been a video which would explain how virtual reality and augmented reality works, which is already implemented for RTM process here in Stade at the German Aerospace Center and the DLR area. And it's very important to mention that here the human being is really re-involved in the automation. And it's possible to have a smart remote maintenance on the one side by virtual reality, by login for a service provider, or by augmented reality for on-site worker. So basically you can really walk through the plant, have a look at the control units, change data, and so on. This is all possible for any place from any place in the world. This is quite important. The process monitoring then means that process data are displayed in the right contexts. And you have the collaborative troubleshooting, which means a multi-user virtual reality and augmented reality is also possible. When you need to involve your experts from the other side of the globe, you can do that. It is quite easy. And also, you have an excellent process documentation. So whenever you need to review a process, why something has happened which was unexpected, or you need to know into the data, you can walk through instead of having just one perspective video. So this is really a great advantage. The next slide, please. Now, what is one basic and very important requirement? And I show this because I think it's very important to mention. You need a very good and fast internet. 5G is essential for any future factory because big data have to be handled, and 5G is about 1,000 times faster than LTE. And when you look on the right side, the LTE coverage related to countries, you see number one in the world is South Korea, having nearly 97% LTE coverage. And when you look at Germany, is somewhere place 53, I think, between Spain and Morocco. So there's really something more to do. This is very important that we have a good internet. Next slide. Also, we need to consider for all processes and all materials, especially nowadays, that sustainability plays an important role to do a judgment. And finally, to allow to implement a new product or a new process. So therefore, the composite industry is really looking at this from a very in a detailed way and works hard on finding ways, first of all, of course, to reduce the waste. Then the next one would be to reuse the material. The recycling would be the third part, recovering, and finally the disposal. These are the options. And of course, you want to be as much as possible in the reduction phase so that you have a process efficiency improvement to avoid and prevent unnecessary waste generation. Therefore, especially in the aircraft industry, a lot of effort is done really to do this, to minimize your waste. And if it is not possible to minimize it completely, of course, then you have the reuse. That means the preparation for reuse of the material in its existing form for its original purpose. This is also possible. You can use material in processes again, prepare new material out of this. This is possible, of course. In other cases, for example, end of life, you need to have other processes. That is, for example, the recycling. Industrial process dedicated to convert a waste into a product for another application cycle. We have, for example, pre-bag waste here for fibers recovery. And there are processes already in place like pyrolysis, where you remove the matrix system and you can get back the very expensive fibers. You can recover the fibers and you can use them for new applications, and you can produce new materials out of this. The recovery is, of course, also possible just to generate the waste out of the material. We should not forget that all the composites material are originated on oil, crude oil. And crude oil in Europe, for example, 80% of this is just used for generating energy. And this is a material also origin from crude oil. So you can, of course, burn it and recover energy. Last not least, there's also an option disposal. Of course, you don't want to really do this, just combustion, or you do the landfilling. This is the worst case scenario, I would say. You try to be as long as possible on the green side. Next slide, please. I already come now to the outlook, saying that future factory for composites will define a new role also for the human being. He will be strongly involved in the interaction with robots. We really have to make sure that we have a good internet data transfer. 5G, I think it's necessary to handle a huge amount of data in an acceptable time. And also it's important to mention that the composite waste handling is already addressed. And we have to realize that really sustainability is a main criteria for the selection of materials and processes nowadays and more in future. There are technologies for reduction, reuse, recycling, recover and disposal in place. They are available, or in some cases they are also further developed, because also in this area the industry wants to define state-of-the-art technology and wants to really look for the best available technologies, which means a continuous improvement. The next slide, please. So then I would also like to mention, if you want to hear more about Future Factory, it's possible on the LightCon. It's a new international event which we have set up in cooperation with the Deutsche Messe AG, which will take place in June, hopefully in a presence 23rd to 24th of June, where lightweight material is the topics and hybrids, and also Future Factory will an important part. And this is under the patronage of Peter Altmaier, the German Minister of Economics. On the next slide, I would like to show you, basically, this was an animation showing you and explain you what is Composites United. In case you have not heard about this, it is actually the fusion of carbon composites in Augsburg and the CFK Valley in Stade. The successor is now Composites United, and by forming this large network, it's one of the world's largest network for fiber-based lightweight design. And I'm very proud today to present as a CEO of Composites United to you. On the next slide, you see the organization. It's a very international organization with red marked countries where we have members, also very international representatives in Austria, Switzerland, Belgium, Japan, China, India, and Korea. So a very international network. Feel free to contact us in case you have questions related to Future Factory for composites. Next slide, please. We say, first of all, thank you for your attention and our future with composites. We think that this material will have still a bright future. And when you have questions, when you want to join our organization, please feel free to contact us. We really look forward to working with you. Thank you very much.
Do you have any questions to the presentation? Okay, so far there are no questions. So 2 questions from my side. You spoke about the Future Factory of Composites. So far as I saw in your sheets, you spoke about resin-based materials. Do you see also a future for carbon fiber reinforced thermoplastic materials?
Yeah, absolutely. When we talk about cycle times, and especially in automotive industry, cycle times are very important, and there with thermoplastic matrix systems, you have significant faster times. But on the other side, it's of course a little bit more expensive. But we see a very bright and important future for thermoplastic materials, also because in the recovery, in the recycling process, it's much easier to recycle composite materials based on thermoplastic matrix.
Okay, another question. So far as I know, you did your PhD thesis on additive manufacturing of CFRP materials. Is additive manufacturing of CFRP materials also a part of the Future Factory of Composites?
Well, I have to apologize. My PhD was based on a chemical topic, which was related to medicine and pharmacy, so totally different. But of course, I'm aware of 3D printing and these methods. They play also in composite material more and more a role, and they are important, especially when you look for complex materials. And there are also some tendency to use endless fibers already in 3D printing. So, but this is an area which is not the strong competence of Composites United. There we have networks where we cooperate. For example, in Berlin, we have a network where medicine goes additive, for example, or manufacturing goes additive is our partner when we have specific questions in this area.
Okay, thank you. But I see there is another question.
Sound, yeah. As we are here at Airtec, an aerospace event, how do these automated processes, can they be also used in the aerospace industry? And are they in progress, or what is the situation and the status?
Yeah, it's quite exciting because just recently I had a meeting with our site leader here at Airbus in Stade, Mr. Bethke, and he was telling me that they have started now to use the first cobot in the production at Airbus, and the first automation also for production of the wing. So there's a lot going on in this area, and especially in aircraft industry like Airbus, they also make use of these automation technologies.
Okay, I see there are no more questions. So again, Dr. Merz, many thanks for your presentation. Ladies and gentlemen, now we have a break, a short break until 11:30. Then we start our session on additive manufacturing. So please be back at 11:30. I close the session now. Many thanks for your attention. Please be back at 11:30. Thank you.
chased a million stars and touched as only one
Ladies and gentlemen, welcome to the second session on additive manufacturing. Yeah, it's a pleasure for me to introduce our first speaker. Our first speaker is Sebastian Reinsbach from Airbus Helicopters. He's the head of manufacturing engineering airplanes doors, and we speak about integrated product and process development of additive manufacturing applications at Airbus.
So, hello everybody, can you hear me? Okay, perfect. So as mentioned, my name is Sebastian Reinsbach, I'm working for Airbus Helicopters. And I have the honor to talk about our approach of integrated product and process development of additive manufacturing applications at Airbus Helicopters. The next 15 to 20 minutes will look like the following. I will briefly give you an overview of who we actually are in Airbus Helicopters, where we currently are with additive manufacturing, and then the main part of the presentation will be how we got there, which is basically based on what we call integrated product and process development. And in the end, I will talk about just a few minutes or seconds about where we will go. Okay, who we are is basically well known. I mean, we are a worldwide operating company or group. Airbus Helicopters is part of the even bigger Airbus group, and we are one of the key players on the world market as far as helicopter products are concerned. I won't go through all these numbers that you can see, as you can find them easily on airbus.com or any other media. So the main message is basically that we are a big company which is well known for its helicopters, but it's not all we do, and this is going to be important for the next minutes. We also do the majority of all airplane doors, cargo doors, emergency exits for the Airbus commercial aircrafts, even though our name is Airbus Helicopters. And this is important because the products that we develop and produce, so these airplane doors, are currently playing the main role in our additive manufacturing landscape. This is so because the products, one of them you can see on the up left, do have a lot of metallic moving mechanics inside, and they are kind of, I would say, easy to get a product in additive manufacturing out of. So Airbus Helicopters is placed one of the biggest sites in Donauwörth, which is roughly 100 kilometers up north from where we are right now, and there is roughly 25% of this big site is airplane doors business, and we are more than 1,000 people working on these products. So where are we with additive manufacturing right now in Airbus Helicopters? As I already said, the main part is our airplane doors business as far as additive applications are concerned. And we are seeing additive manufacturing as just what it is, as all the other manufacturing technologies, just a means for the purpose of building safe and competitive parts that do provide a business case. So in the end, we want to produce very safe, but best cost parts. So what we do is we produce more than 2,000 mid-scale or big-size parts. That means they are roughly 300 millimeters in height. So I will just steal this thing here. It's above this size, so that high. And it's more than 2,000 per year. We do use our machine, which is an EUS M400-4. Maybe Mr. Bäumer will talk about this in half an hour, a bit more in detail, I don't know. We do use this as it was a milling machine or any other thing with more than, or basically, 24/7. So we do as if we would do with milling. We only work on solid business cases, so that means we don't really do what I call political parts, so just print for the purpose of printing, because we can print. No, we do only print when we have a really solid business case, and the part that you see here is basically the first part which is a system-relevant part in the aerospace industry. That means this is playing a key role in the opening and closing operation of the A350 aircraft doors. And yeah, because we did reach all this, we are kind of proud what we achieved in the last years, and the main part of my presentation now will be how we got there, because we think the success that we currently have is based on kind of a smart integrated approach of developing the product and the process at the same time. You see once again the airplane door of the aircraft door of the A350 aircraft. It's basically a composite structure. And inside of this composite structure, there's the so-called mechanism, which provides the opening closing operation of the door. This consists of more than 2,500 metallic parts, most of them moving. And there is one sub-assembly, which is in these rectangular marked areas, and this is called the latch shaft sub-assembly, which is latching the door after it's closed. And you see on the down left, you see the classic milling sub-assembly. And there was an idea of a dear colleague, Christian Wolf, who would be here, but is unfortunately unavailable today. A couple of years back, he saw this and thought that it could be, this could be an approach to implement 3D printing, because he just read a couple of days before he had the idea about the maturization of machines in additive manufacturing. By the way, if I say additive manufacturing, I myself and we as Airbus Helicopters mean mainly powder bed fusion titanium 6-4 process. Yeah, at that time it was kind of a crazy idea because no one did this before, and of course everyone told us it would be a suicide mission to do this and take it into an airplane. And the timeline of this project looked like this. This idea was in late 14, very early 15. In between, the gap between 15 and 18 was basically our product development that I will show you now. But coming back to this timeline, before that, we decided just mid or end of 2017 to do it ourselves. So in the very beginnings, of course, we had the idea to go straight to a supply chain and just order something like Airbus does this usually. But we wanted to understand and master the technology really, so that's why we decided to do it ourselves. And we got the printer 2018, did start serial production 2019, and the part will be in an aircraft which will be delivered in the next weeks or months. And on an aerospace timescale, this is pretty fast actually. But now coming to this technical maturization that took place between 15 and 18. What we did is basically we went our way along this. I sketched it on the right, this hype cycle of technologies. Of course, in the very beginnings when we had this idea, we started with doing super high sophisticated and optimized designs, which, as you can see, are basically based on optimization plots from a stress guy. So if you are in structure dynamics, you could see, or mechanics, you could see that we have a part that is carrying torsional and bending loads, but optimizing it just for the printing process and nothing else in the end does not really help you. Because if you have a metallic AM part, there is a whole process chain that you take, that you should take into consideration. And this is basically what we learned when we went our way from this very first part, which was kind of optimized to the printing, up to the final one, which is optimized to a whole process chain and is in the end using a lot of the benefits from 3D printing, but with a focus on the whole process chain. We did so as a big team, interdisciplinary, where we really do not differ anymore between a colleague from manufacturing, engineering, quality, whatsoever. We work in a big plateau organization in an office all together, and as such an integrated team. So when I talk about integrated product development, I also mean integrated teams. We came up with a part that is optimized for this process chain I already mentioned, and one benefit that we have and why I think we learned so quickly is that this process chain is basically on-site. So in Donauwörth, we basically have everything we need. What this is, I will show you in the next slides, but I want to repeat that I think to understand a technology which is, of course, present for decades, but getting into an industrial scale in the airplane sector just for a couple of years now, it plays a very, very important role to really have hands-on experience. Because what we experienced is that it's not only the printing as mentioned, it's all the processes that you need along this process chain to create and build a successful part in additive manufacturing. That said, it is the design that has to be at least very good. It has the part that comes out of this design has to be testable, because in the aerospace industry we have to have as our first and goal, which is not to discuss safety. So the parts have to be safe, therefore they have to be tested. So the part should be testable. You need surface treatment, of course. All these post processes have an influence on the part design, and this is why integrated product development for AM applications, as far as we understand it, is developing the design to the print process and all the subsequent processes at the same time. So the part that we came up with in the end is basically designed for process, but when I talk to people about additive manufacturing, it's a lot of times the case that when they say design to process, they actually mean printing process, and if you ask me, that's just not true. Because metallic additive manufacturing is really more, it's mastering the whole process chain. I will come to the chain in a couple of seconds. So our part is designed to this additive manufacturing metallic process chain. But we did not reinvent the wheel actually, so the old part, which is in an A350, if you would fly it now, you would have this left lead shaft part in there. This is also, of course, kind of designed to a process chain. It's just an old one and a much simpler one. So a milling process chain is simpler, yet I wouldn't say that additive manufacturing is necessarily always superior to that. Definitely not. So we didn't reinvent the wheel, but we just benefit from new possibilities of new technologies in a smart way, we think. So this is a sketch of this process chain that I was mentioning a couple of times already. You see there are a lot of process steps that you have to do, and what I show here is even simplified. So it's not everything. I left out a couple of sub-steps actually. So if you create a part or develop a part, it should kind of not make a compromise to match and fit to all those process steps in a sum. You have to compromise to make it fit to each of these process steps so that in the end you get a global best solution. One example is the CT testing or the surface treatment. You may remember the very first design that I just showed you, which had this crazy bionic structure. This would be perfect from a stress guy's point of view, and maybe even more weight optimized than the part that we currently have, but it is a nightmare to test, for example. What we do have is dye penetrant testing, for example, as one of these process steps that we implement to detect cracks of the part. And this is something that you can just do better if you have a closed surface. And this is just one example. So if we go along the process chain of pre-print, print, unpacking, stress relief, removal, dry blasting, hot isostatic pressing, and so on, the part has to really be at least good for all of these process steps, then you will in the end become a really, really good part. That's what we learned basically along our journey in the last years. And one more thing to prove that in the end it's of course about printing, but not only, is the role that printing plays if you take a look at your whole lead time or at your cost structure of your parts. As you can see, it plays an important role, but it's definitely not everything. So taking the lead time, the print itself takes us roughly 2 days, maybe 2.5. But then it's just 5% of our whole lead time, and as far as the cost structure is concerned, integrating the material to the printing process leads to roughly 30% of the whole part cost. And that said, really, once again, if we talk about integrated development, we focus not only on the printing, we focus on everything we need to get the part into a final and good product. Based on this, based on what we learned, so the knowledge about having a whole process chain that you should consider, we will now go on in our journey, and we will kind of leverage the success we had and the knowledge that we gained as a big additive manufacturing team. So we will have, after the first application, which will be in an aircraft in the next weeks or months, flying, we have a next one coming, which is also part of this A350 mechanism. You see the A350 door here again, and the cutout in the middle is again showing you details of this moving mechanism in the door. And above these two parts, these are the LED shafts that I already talked about. And below this, from the very left to the very right of the door, with a total length of more than 1 meter, there is the so-called drive shaft, which is basically the main shaft of the whole mechanism and driving everything else. We will go from a classic milling assembly to an additively manufactured part as well. But because, for example, we don't print to print, but we print because it makes sense, we will do this as a kind of a hybrid product and implement a product which consists of 2 printed parts you see here on the bottom, and a winded CFRP mid-piece in between, because it just makes sense in between, because there you need just a tube and it wouldn't make sense to print that. So we will have products to come which are very closely to the product that we currently have, because we experienced that with this process chain that we put in place, where every single process is really optimized to the 3D printing. So it may look easy to have this process chain just as a chain with all these processes, but our knowledge really is in the details of all these processes. So the CT scan, for example, is crazy fast because we optimized it up to the last detail, and we adopted the design to fit to the CT scan. And this is true for all these process steps. And this is why we have a really competitive process chain in place. And we know how to develop the parts. And we do have kind of more parts to come, which are similar shaft lever integration parts. And you see some of them here. So we will introduce new parts. We will expand our knowledge to our dear colleagues in the helicopter world. As mentioned, we are a helicopter company, and we are working on that. I have not yet the pictures, but there are parts already in preparation for the helicopter world as well. And what we also do, and there I will already come to the end, is that we will expand based on the success that we had and on the solid business cases we really can deliver. We will expand our infrastructure. We will get another machine that we will use 24/7 for the products that I just showed you. We will implement things like automatic powder supply, because this is currently, if you do that manually, it's a nightmare. I don't know who of you is in additive manufacturing, but not every single sub-process step is industrial today. The powder supply definitely is one of them. So we implement an automatic powder supply. We will get an own building actually because of our success. We will implement in situ or implementation, online process monitoring, and actually expand our additive manufacturing team, because we are getting more products, and so we need a couple of heads more. And that's basically it. Thanks for listening, and stay healthy, which is the most important one.
Yeah, thank you, Sebastian, for a kind presentation. Do you have any questions? Okay.
So what does not exist anymore? Yeah, okay. Well, we would not have right now, but of course you are right. One thing that our dear colleagues from the program organization or the supply chain are asking us a lot about is having fallback solutions. And so what I mentioned is that we currently have one EOS M400-4 in place, which is running 24/7. And because of the request of a certain redundancy and process robustness, we will get a second one actually next month due to this redundancy requirement that we have. So then it still would be kind of sad if EOS would go bankrupt, and of course we don't hope this. But maybe we can ask Benjamin half an hour and he will tell us about the situation. No, really, it's an important thing, and redundancy is something we have in place for each of the process steps that I did show you. Yeah, actually, maybe the lead time of one of these products, if you print it, and if you after that want to hold the final product in your hand, I think in between we do have like 5 months or so. So it is quite a long time. You're right.
Are there more questions from your side? Okay, there's another one.
I have one question. You said that the costs for the overall cost, 30% is only on the additive manufacturing process. What is the biggest cost driver in the post-processing chain then, like the rest, the 70%?
That actually depends. So if you would ask external suppliers, or if you would ask companies who provide the service of printing 3D parts, which implement all of these process steps, you mainly get CT scan as one of the cost drivers, because this is quite an expensive process step which takes a certain time and you have to test every single part 100%. HIP is often named as one of the key drivers in terms of cost. But as I said, I mean, we really developed and improved all of our process steps, not only in the technical but also in the economical way. So we actually do not have this one big cost driver anymore, because we, for example, took a look at having the biggest possible HIP furnace so that we can just put a lot of parts in there. And as mentioned, we do more than 2,000 a year. So if you have a big furnace and you put in like, I don't know, 100 parts, of course, the cost per part are pretty low. If you have the usual HIP furnace, which is not that big, and you put in like 10, of course, the costs are high. But usually you would go for HIP and CT scan, but that's different for us. We don't have one big cost driver anymore.
Okay, one question from my side. You said the part is a system relevant part.
Yeah.
So I would call it a critical part, more or less.
Yeah.
Okay, and if it's a more or less critical part under dynamic load, so far as I can remember from the standards, the maximum allowed pore size is 0.1 millimeter.
Yeah, okay, that's... Yeah.
So titanium is not really the best suited material for CT. Yeah, there's a lot of scatter and the absorption is also not so, it's relatively high. So are you sure that you can detect pores of 0.1 millimeter by CT in your part?
Well, answering that question directly, I would have to say no, but we don't have to.
Okay.
It's actually the case that the part is called system relevant by certain colleagues in the authorities. So system relevant means for the airplane as a system, it plays a certain role because you have to be always able to open and close the door, of course, and there is a key player. And that's why if you change this part, no matter if it's a milling one or if it's a 3D printed one, it is a major change because it's a system relevant one. But you do have these these safety classes in the aerospace, and this part is a safety class 2.3 because it does not have these dynamic loads. It is mainly statically loaded, and this is why the pore size is 0.5. We could detect 0.1, and we already detected 0.02 or something like that by optimizing our CT process up to the very, very, very last detail. But then a scan took like 1 day, and this is of course not a business case anymore. So we really optimized it to the fact that we just need to have these 0.5 pore size, and that's what we do.
Yeah, and the last question, okay, the process time, the process costs for the testing and for the heat process and so on are extremely high, as said. Do you have strategies to avoid this by a better sensor system, for example, into your AM machine? That means something like in situ sensors for the process, because in my presentation I will say something about the network AM quality. You are participating in AM quality, so this would be a good idea, because to implement such strategies.
Yeah, definitely. So this is, you're right, it's one of the main areas of interest is, of course, all the testing, and or not all the testing, maybe to get rid of all the testing, or at least parts of it. And currently, we test 100% all of the parts we produce. And yeah, of course, the strategy is to get rid of at least a part of this. And we do this by implementing, for example, an optical tomography system. And I didn't mention it, I had it just, is it still working or whatever? I had it on one of the slides. So this is something that we implement, and the good thing for us is because we do produce such a high number of parts, we do collect data in a very, very, very high amount very quickly. And this is why we really think, and we are convinced that in the end, this will help us a lot. I mean, there are other companies who are way more mature in optical tomography, for example, than we are in the aerospace industry, but we are kind of a fast learning company, at least as far as AM is concerned. And this is why we are very confident and focusing on getting rid of, for example, CT scan by implementing optical or in situ process control.
Okay, thank you again for your presentation. We'll come to the next. We'll come to the next presentation.
Oh, that was one too fast. Really happy to be here. It's my first in-person conference since a few months, so really good to see a few new faces and make new contacts, and yeah, happy to share that with you. So over the next 20 minutes, I will try to give you a broad overview on additive manufacturing technologies, where we are now and where we are going, and what do we see as the biggest hurdles to basically implement additive manufacturing on really big industrial scale. But before I start my presentation, maybe just one or two slides about us. I probably don't have to say too much about the Fraunhofer organization itself. It stands for Applied Research, so we try to help the industry to adopt new technologies and help them to use them in the best way. And it's organized in different institutes, and we are the Institute for Additive Production Technologies, Additive Manufacturing Technologies. So everything that we are doing is somehow connected to additive manufacturing. We are located in Hamburg, around 100 researchers working there on additive manufacturing technologies, and with the size, probably one of the biggest research organizations on additive manufacturing, at least in Europe. So with the size we have, I think one of the biggest strengths is that we can basically help our customers and partners really from the start with additive manufacturing to the end. So we have a lot of customers where we help them to make the first steps in additive manufacturing, trying to find the right business cases, but we also work with machine manufacturers and established companies to basically further develop the technologies and make the next steps, and that's some of the parts that I will try to give you a good overview on today. Also the topics that we are working on and we see as the biggest hurdles on additive manufacturing. We have quite a long history actually in additive manufacturing in the aerospace industry. Obviously we are from Hamburg, Airbus has a big branch there, so there's a long cooperation with Airbus on metal additive manufacturing that goes back to 2010, so 10 years cooperation with Airbus, and some of the success stories here. Whoever is familiar with additive manufacturing in the aerospace probably has seen this part here on the top left, one of the most famous parts on metal additive manufacturing that was actually developed, designed and manufactured at our facility in 2012, and was the first metal part that ever flew on a civil aircraft in 2013. Obviously there was special qualification, no serial production, but the goal for that project was to show, okay, if we understand the process, it's mature enough to put parts on the airplane. And obviously we've gone quite some steps over the years, so we've just seen serial production of parts. So I will reference some of that work over the next slides. Also, we are working a lot in the automobile industry and medical, that are probably our biggest markets: aerospace, automobile, and medical. Obviously, the focus for today is the aerospace activities and what we see here. I would like to start my actual presentation with showing where we are standing today, which is probably important if we want to see where we are going with additive manufacturing. I think everybody knows the big advantages additive manufacturing offers us: the design freedom, the possibility that we can do bionic features, product development really fast. I don't want to talk too much about that, because if we are honest to ourselves, we are really still a niche. The slide I show here, you see the overall production volume, not only aerospace, but overall. And if you see how much or how important is additive manufacturing, it really basically doesn't play a big role. It's less than 0.1% of the overall revenue that's done in production technologies is going through additive manufacturing, despite the growth we have in the technology with 20–25% of growth every year since over 10 years now in a row, and it's going to continue that way. How does that fit together? It's basically where we see the production of additive manufacturing and where we apply it. It's product development, it's small series production, it's small scale production, even 2,000 parts. It's a good step for additive manufacturing, but if you go to other technologies like casting, that's really a small number. And this is obviously where the revenues from the other technologies are coming from. So if you want to leverage the potential of additive manufacturing, it really establishes as an industrial manufacturing technologies, we need to leverage the potential of additive manufacturing for serial production and mass production. The list of things that we need to overcome to do that is probably quite long, and here are just a few of them where I personally think are really important to overcome. One of them, obviously, we need to identify the right business cases and correct business cases. I'm a big fan of what we just heard, to not do additive manufacturing as a purpose of itself, but to really find the business cases, and usually just do it when you save money in the end. We obviously need to lower the cost of additive manufacturing. We did some calculations. As a rough number, we say we need to be 10 times cheaper than we are today for mass production to really do it on a mass scale. Obviously, you need fully automated production, robust processes, and streamlined quality assurance. If you're not working in additive manufacturing, especially the last three things, you might think, well, isn't that something we already have today? And honestly not, but probably the idea of additive manufacturing then comes how it is presented in the media. You see pictures of factories like here where nobody's working in, everything is automated, and we already heard in the presentation before that it's not the case. And if you go to the factories today, it looks more like this. There's still a lot of manual work necessary to unpack the machine, to assemble the machine, for quality assurance. And also the process chain itself is not completely automated. So what are we doing with the parts that are coming out of the AM machine? We need post-processing, and we need a interconnection for all these different post-processing steps that are not established today. So there are a lot of things that we need to develop, and I will go through the things I just mentioned to show what we think are basically the right steps and how we can address these points. And I would like to start with the first point I mentioned, is identifying the right business cases and identifying the right parts. And this is actually more challenging than you might think, because there's a lot of knowledge necessary. You need to understand, obviously, the products that you have. You need to understand additive manufacturing. You need to understand cost calculations. And then usually the companies, they don't have like 10, 20 parts. They have like 10,000 parts, 100,000 parts, and going through them hand by hand is quite challenging. However, I think that there are still a lot of business cases today, or most of the business cases that are even feasible with the technologies we have today, are still untapped, and we just don't see them because they are hidden, and we didn't take a look at that. Obviously, going through all these databases hand by hand is not what we see as a sufficient approach. So what we are developing at our institute as an examples, there are other companies doing similar things out there, is trying to automize these part screening, how we call this. Basically to have a software that goes through your database and identifies potential business cases. Obviously we know the software today cannot be as smart as an engineer, but that's not the goal. The goal of the software is to reduce the amount of work the engineer needs to do himself to identify the right parts. So basically, if a company has 20,000 parts, that the software screens these 20,000 parts and puts out like 50 parts where you say these might be feasible with additive manufacturing in the terms of costs. So it actually analyzes, is it feasible with additive manufacturing? How is it with the quality and cost comparison to conventional manufacturing technologies? And by that, we can reduce the amount of work that we need to put in to look at actual parts by high amount. So yeah, you find good business cases. We already seen a quite impressive one. Just to show a few ones we've done here at our institute. One is a small part. You see, it's not the most fancy part. It's not bionically designed and not optimized. It was actually a milling part, but we saw it's quite feasible with additive manufacturing due to the bite-to-fly ratio. It was titanium part. So throwing all the material was not sufficient, and that part actually flew on the flew to the Mars, and obviously quality assurance here was a big issue. And everybody knows product development, it helps us a lot to further develop applications, to test new structures, as you see here for 4-meter test airplane that was completely printed, except the motors obviously, but the whole structure was printed, and that helps us, or Airbus in this case, to test different wing structures in the actual wing place. So it can help us in this place, but we think as an institute that the actual potential is not in this product development or one-to-one part replacements, but if you actually use the design freedom additive manufacturing offers you in your part designs. And we see different categories for these. It's on the one hand part integration, it's obviously bionic and lightweight designed, and additional functionalities we can implement in our structures. If you go to part integration, this is probably the easiest business case you can ever identify. And if you take a look at where we apply additive manufacturing today in serial production, it's usually the case that there was complexity taken out of the manufacturing process and chain and the part by utilizing the design freedom. So taking a part that was 15, 20 parts before and now printed in one part saves you a lot of cost, and that's the easiest business case we see today with additive manufacturing. Obviously, lightweight design is another advantage you can use, or implement additional functionalities, and the more you try to combine these things, the better your products will in the end be. So that's our approach here, that we try to develop new design methodologies to implement all these different requirements in a single part design. So if we do a lightweight design, why not implement additional functionalities like for optimization, heat exchange, wherever it is feasible. Obviously, there you have always different constraints that you need to apply. Just to show you one example on where we applied this, it's a cooling structure for an LED light, which is conventionally built in such a design, and we did several iterations over the structure, and in the end ended up with a topology optimized design, considering heat exchange rates, and had a design that was 75% weight reduction, and in the same speed 70% improvement in the performance for heat exchange. So this is really where we see that the potential of additive manufacturing is, and we see we need to combine these different things. Obviously, if you design these parts, you need a lot of knowledge about additive manufacturing, about optimization. There are quite only a few people out there that can actually do that. One thing where we see big potential for the future is the topic of design automatization, and we are really happy to see that the software companies are going this way to automate the design process, especially for additive manufacturing. We also at our institute develop software tools for design automatization, basically taking the responsibility of the designer out. This is an example for a heat exchange application. So designer who wants a heat exchanger that might look always quite similar but has different input parameters can actually he doesn't need any knowledge about design, he doesn't need any knowledge about additive manufacturing, he just needs to type in his number and gets a manufacturer optimized design in the end. So obviously this application can only design heat exchangers now, but we see that there are a lot of companies that have these requirements. The next step, if you have your design, you need to print it, and we've seen on one of my first slides these image of the how we see the manufacturing hall in the future, and we saw, printing is not only the cost driver, 70% is coming by additional processing steps, by heat treatment, by post-treatment of the parts, and we need to combine these, and we see a big potential to save the costs by streamlining these different processes. One example where we are working on this is a container-based solution for additive manufacturing. So the idea is here to have basically all in one container. So you put in your design, and you have the AM process. In this case, it's not a powder bed process, but it's a wire arc or a blown powder process, so a little bit more robust process, and the milling process at the same time. It's for us also a development platform, because especially for such a container, we need the interaction of these different manufacturing change and automate this change, and this helps us to basically automate these different processing steps. Another big topic for the future will be quality assurance. I was quite surprised that I heard that CT is not the biggest cost driver for you, but that's good for you. But that's also what we hear a lot, that especially in the aerospace industry, that the quality assurance of the part is the biggest hurdle. And you identify business case, and in the end, if you look at the quality assurance for your parts, especially for the metal parts, if it's critical parts, it just gets too expensive and destroys your technologies. And we see for the future a lot of potential by monitoring solutions, so directly measuring the quality with sensors in the AM machine. However, we see a big hurdle by all these data that we are gathering. So if you have a sensor and just print one build job, you have several gigabytes of data that you need to handle, you need to store that, and that gets quite expensive as well. So we see that there's a big demand for big data handling, for developing software solutions. It helps us to collect and analyze all these data that we get in the quality assurance. Here it's basically shown one development we had of our solution. It's called Additive Quality Manager. It's basically a solution to do all this handling of this quality data and analyzing all this quality data. And what we learn is if we have the data and can analyze the data, it really helps us to further understand the process. Additive manufacturing is a complex process with a lot of process steps involved, with a lot of influence parameters on the quality, and it's quite challenging to fully understand these processes and use that for stabilizing the process. So where we are going, I think we made a big step in additive manufacturing in recent years, but still what I try to show is that we still need to go a long way to really establish additive manufacturing on large scale, in science, in engineering, and also at the end users. And I think the end user part is probably one of the enablers for the technologies. We need to see the business cases in the industry to further get the community to believe in the technology and take it to the next step. And we see that enabling the customers is a big issue in this place. So trying to get the right people working on the right topics So happy to help that. If that's ever an interest for you, we have a large academy for additive manufacturing where we do design trainings, production trainings, management trainings. So big customer base, over 2,000 engineers that we basically did training on over the last years. And with that slide, I would like to end, and happy to have my presentation here. Hopefully you had some good new insights, and looking forward to get some questions.
Thank you, Tim, for a kind presentation. Do you have questions? No questions? Then some questions from my side.
Okay.
First question, you presented this interesting concept of a heat exchanger for this laser spotlight. Do you also have projects in the e-mobility area? That means you have ECUs, for example, with high power electronics, and the cooling concepts without ventilators or so are very interesting if you use additive manufacturing in combination with these internal bionic structures. Are there any projects so far?
That's actually a quite big topic, like the cooling of Leistungselektronik, I don't know the English word. So that's a big topic for e-mobilities. We have two projects. I unfortunately cannot show any slides on that because it's confidential at the moment. But it's a big topic.
I'm very interested in that. Another question. You presented a container-based solution for additive manufacturing. Are you interested in including a CT scanner? Because we are selling our CT scanners also in containers. So maybe because CT at the moment is the most relevant NDT technique for additive manufacturing, so maybe it would be a good synergy.
Obviously, and especially if it's already in the container, I think that could be a good solution. If there's a demand from the customer, obviously that would be the next step. We haven't had that yet, but we can definitely discuss that.
Okay, we'll discuss it. Last question from my side. You presented software for the evaluation of the printability and the price of the AM part. Is it some kind of freeware, or is it commercial software? Is it an online software? What is it?
So it's basically software. It's not freeware now. We're actually thinking about putting it on our website for free, so people can do that. So it might be free in the future. But at the moment, it's something we use in projects with customers, and we have it installed at two companies' site, so they can use it internally for the part evaluation.
Okay, thank you again for your presentation.
Okay, thanks.
We'll come to the next presentation from Sonja Rush. Sonja is the Sales Director Manufacturing at Materialize, and she will speak about the minimizing of the investment risks with additive manufacturing.
Thank you, Olaf. So as Olaf said, my name is Sonja Rush, and I'm Sales Director at Materialize, and mainly responsible for business development in serial production and aeronautics. And for the ones who don't know Materialize, we are a full solution provider for industrial AM. So on the one hand, all the software, but on the other hand, also all the 3D printing services. And today I would like to share some ideas about the smart use of AM in additive manufacturing and how to save or minimize investment risk when using or implementing AM. Because in the end, we all want to earn and not to burn money with this technology. 3D printing is a topic in aviation since ages. This industry was one of the early adopters of this technology, and they already invested a lot of time and research, as we heard today also from Airbus, and identified already a lot of parts. So the number of flying parts is increasing rapidly, especially in plastics. And we at Materialize, we also followed this trend already many years ago, and since 2015, we are EN 9100 certified and have Part 21G approval. So that allows us to deliver really flying parts to this industry. There are many focus points for AM in aviation. So, for example, on the one hand, for the huge OEMs and their tiers, but also for smaller planes like VIP and luxury planes, like sailing planes and so on. And definitely, as we heard yesterday, also for the whole air taxis. The most common usage is for sure the prototyping and testing, but you can also use it for jigs and fixtures, customized to your needs, so for assembly jigs, painting jigs, covers and so on, with high accuracy and sometimes with some clever designs, even with better functionality. And in end-use parts, there are really thousands of applications, so from behind panel to structural parts, investment patterns for casting, but definitely all over the cabin interior, you find many applications. Yeah, and last but not least, there's the spare part business and the retrofitting, because here every hour on the ground costs a lot of money, and yeah, stock costs and recovery costs are often very high, and the lifetime of the planes are quite long, what we also heard before, and often it's even impossible to find back parts. So I personally do not believe in printing spare parts on home printers overnight in the hangar, but I believe that there are a lot of cases where additive manufacturing or the advantages of AM really justify the case. And you can find a lot of examples where time is money. One good example is the 3D printed bionic spacer of Airbus. So that is a cabin part we printed, which fulfills really the high requirements regarding flammability and painting for cabin interior. So I assume you are aware of the potential of the advantages of AM, but and then there are already a lot of cases, but the big question is, why are those cases not even more common? Why are there some lighthouse projects, but not really so many profitable business cases? And yeah, why do people often struggle when implementing AM and have difficulties to find the right entry path? And often there's a big dream between the AM dream and the AM reality, and many companies are very frustrated and think that AM is really horrible expensive. And some companies even did huge investments in software and hardware and then find out that it's a long, stony way to bring AM really to a success. So it's nothing what you install today and tomorrow you have successful parts. And for me, one thing is very important. Before you think about make or buy, really think about the right application. Think about really where and why do you want to use AM, and gain experience with external suppliers and learn where to save money. So the best entry point and the most common usage is for sure the prototyping, and prototypes save a lot, time and money for the development process, and yeah, you can speed up your development process. But keep in mind that prototypes are more or less always one-to-one substitutes. So most of the time, even in serial material. And before you can reach here a lot of, and you can reach here a lot of savings if you do not stick to your serial material 100%. Really think about why do you want to have prototypes and what kind of prototypes do you need? Do you need mock-ups or do you need functional parts? Can you live with alternative materials, for example, for mock-ups and icing simulation and testing? There you don't need the 100% serial material in general. And if you really need functional prototypings, then also focus here on the main property you need. Do you need strength? Do you need stiffness? Or do you maybe just need the thermal resistance for the first test? Or EMV protection and so on? And I can just recommend, tell us what you need, and we will find then the right material and machine combination for you. And you can also save a lot of money if you are open for little design changes. So not real design changes, but little ones to save material, and definitely for saving support structure, because that is a very cost-intensive process. On the one hand for the building, but also the manual process afterwards to remove all this, these support structures. And before you invest here in your own machines, really think about gaining experience with external suppliers so that you de-risk here your investment, that you do not invest in the wrong technologies. So another topic is always spare parts on demand. And AM promises here much faster and cheaper supply chains and also lower storage costs. And usually these spare parts are also always one-to-one substitutes and always in serial material, because you don't want to repeat the full process. And to be honest, the number of profitable cases you find here are really rare. Nothing is fast and cheap here. So similar to conventional, you need the full qualification process before you can really order them on demand. So that needs to be considered, that you need the full process. And special attention you should put here really on difficult to obtain, time-critical or system-relevant parts, because these justify the case to use AM. And you can also think here a little bit maybe about compromises. You can think about an alternative spare parts catalog with reduced requirements so that you maybe bridge your time with alternative spare parts until your long life super spare parts is available. I always used here the illustrative example of a V-belt. Hello? Of a V-belt. A V-belt is normally designed as a high-performance, long-life part, but in case of a breakdown in the desert, you are happy to have nylons. Yeah, the most exciting field for AM is definitely the serial production. And if your numbers of serial parts are low, it's always worth to think about identifying parts for AM. But if you substitute here, you will hardly find any case. So here it's important, do not substitute. Really think additive, design additive, combine parts, make one part out of 5, add functionality, increase the performance of the part, increase the reliability of the parts. And to find here the right candidates, look for the most cost-intensive parts with low amounts and maybe also with some special issues, so which you can overcome then with the advantages of AM. And tell us as much as possible about your needs so that we can really help you to explore fully new solutions instead of substituting the old one. Yeah, and what is also important and what's often forgotten, if you first design conventionally and then need a full redesign, then you have double costs. So really a consequent AM design from the beginning. And what you also should consider, you should not just look at the pure part cost. If you send a part like this to your purchasing department, a conventional design, and say, please compare conventional to AM, AM will always fail, always. So if it's not really a design for AM like this, the conventional technologies will always be cheaper. And that's for plastic, definitely, but for metal, it's always the case in 99% of the cases. So you should always look also at the full TCOs, because beside your part cost, you always have also tooling cost, and you have later design changes and later cost for changing the tools, and then scrap cost, because you already produced a lot of parts. And when you consider all these extra costs, and then you consider cost savings like weight saving, higher performance, higher reliability, lower assembly costs, and so on, then you will explore the real business cases. So let me summarize. What is important is no substitution, a consequent AM design from the beginning, no pure part cost comparison, and considering the full TCOs. That are the key factors for success and also the factors for saving money. And maybe to the talk before, I do not believe that this is fully possible with this piece of software. I think you need the experience of your designers, because you know your product, and that knowledge about all the pains, issues, troubles need to be included in the calculation to find the cases. Oops. So you have now maybe an impression how complex the AM topic is, and that the whole industry is often a little bit like a jungle or a labyrinth. And we see companies often very early investing huge amount of money in their own hardware and software before they do not even have an application. So for me, one thing is important: first the case and then the investment. And you can definitely try to explore everything on your own to get an overview about the technologies and so on. But you can also take a shortcut with experienced partners. So I can highly recommend to consider external consultants who can give you a neutral overview about all the technologies, applications, possibilities, and really let them explain the limits and the possibilities of each technology. And then you can also fight yourself the way through the jungle of all the software solutions and all the software applications for designing. But you can also consider D&E services for a common approach to design parts. And as I said, in addition to software and hardware, you need the right mindset. And this mindware is often not very common in conventional companies. So external consultants can help you to inspire, to find some new ideas, new approaches. And this additive thinking can help you to identify other cases. So, and as soon as you have an application, we can also help you to set up your production, to scale up the production process, and also the whole qualification process and the software you need for the qualification process, the software for traceability and so on. Also there we can give an overview. And then finally, when your application is ready and when your process is set up, then it's still time to invest in your own equipment and to scale up your own production much faster. So I hope that I could highlight a little bit that besides software and hardware, the right mindware is important. And I would like to invite you to use our Materialized Mindware consulting service. So thanks for listening.
Yeah, Sonja, many thanks for a kind presentation. Are there any questions to Sonja? No questions?
No questions.
Question from my side. Okay. You presented the usage of AM parts as prototypes, spare parts, and for serious production. Can you say something about the percentage? That means how many, because you are a big service provider, how many parts are there in, let's say, prototypes, spare parts, or in serious production?
I cannot really give you the full numbers. And percentage, yeah, let's say from the number of parts, I say it was 80% of the parts were prototyping, and maybe 20% was serial production, but this number is increasing a lot, and therefore also the turnover is increasing a lot. So in turnover, I don't know if I can give the full numbers, but...
No, not the numbers, but is there a trend to AM series production?
Definitely, yes.
Okay.
It's a long way because these additive thinking takes a long way. What I said, that often companies come with these kind of parts to us and say, yeah, we want to do it additive, and then we say the price, which is 5 times higher than milling in this case. And we say, yeah, but it's possible to make it cheaper, but we don't have this design in the case when they ask purchasing. Yeah, and of course, they do not believe then that you can be cheaper. So many cases really stop at purchasing, let's say it like this. And that's a pity because, yeah, when you do not consider the full cost, then you will not find so many applications.
Okay, thank you again.
Welcome.
Okay, we come to the next presentation. The next presentation comes from Benjamin Bäumer, who is the account manager aerospace at EOS. And the presentation is the title, 3D printing arrived at the aerospace supply chain.
So, thank you for the stage today here. So it's a pleasure to be here today. And it's also great that we can present something here. And the best thing for me is today that now 2 of our customers were right in front of us, and showing also the complexity of this topic, and also showing that this is, yeah, nothing what you easily install like a 2D printer, which you just place your software on it and then you print simply some parts. It's not. It's completely different. And let me just jump on the slide. Maybe I just start here. We already heard something about EOS. Who are we, or where are we located? So EOS is a family-owned AM supplier since 89, sorry for that. We are producing, on the one hand side, the metal solutions, so metal AM systems, and on the other hand side, polymer systems. And even more about that, we also provide here software solutions. We provide our services and also our internal consulting about that. Sonja said it also at the beginning, consulting is very, very important, even better if it's external, but we have also our internal one. We need to help our customers at the very first stage that they're not struggling with this new technology. It's very important for us that our customer is successful with the technology. And as Sonja said, not each and every case which is coming up here is 100% a case where you need a machine. This is by far a number which is somewhere at 10% or lower even. Most cases really we have to give to our suppliers who then, or our technical suppliers, who then simply print the parts and help the customers to find the best solution for themselves. So this is quite important about that. Anyhow, we have also on our side, the entire street more or less. So we're providing also everything from the very beginning, from the first idea. Then we help the customers with the design and the engineering with our consultant, in-house consultant. We move further with the production. There we have, on the one hand side, our polymer systems, as said, and on the other hand side, our metal systems. And in this way which we have in here, we're also trying to involve then also partners of us who then help the customers with their software, which can be Magics, for example, which can be also other solutions which I will show you later on. And then we have also a huge step with post-processing. We hear it. This is a huge step where you have also additional costs. Customers have to have this in mind before they make an investment in a machine. And in the end, we hope to bring the customer to a production way that he can easily or can produce the parts which they need. I said it, it's not just us. It's always us together with partners. On the one hand side, it's the EOS group. As said, EOS is still family owned, so we have some sub or sister companies which are working quite close together with us. On the one hand side, it's Additive Minds, the consulting approach. So our application engineers, which we're moving in this direction and help now the customers with certification, with the first setup of the machines and with the first prints and the first benchmarks. We have ALM. ALM is, for example, our powder supplier on the polymer side. They make the powder customized for the customers. But we have also some others like AMCM. They are, for example, the ones who take our machine setup and just improve it in the direction the customer needs it. For example, if you need a biggest frame of the machine because the one we have in our portfolio is too small, these guys jump in and just simply extend the machine to a level where it's needed, or also bring in other lasers, for example. We have always the standard lasers because they are for serial approach, but on the other hand side, there are many other, like for copper, it's good to have a green laser. Green laser solutions, for example, can be provided by these guys. So we try to give the customer also a setup which fits to his needs best, so to say. On the other hand side, we have also a venturing arm, which is AM Ventures. AM Ventures is a corporation. It's also, again, the family, which is a top on EOSL as well. And they are trying to build up the entire landscape, so to say. So we don't want to have only our machines, which are just the production machines. We also want to have software on the other hand side, like additive works, where you can simulate your parts, where you can understand why up. For example, when you have a interruption between the building process, why did it happen? Because with such simulations, you can easily find out this. Others like Dimension, for example, so I just take now some of them, but all of them have a huge portfolio, a great portfolio. Dimension, for example, we could at the beginning only print parts in polymer in white and in black. So this was for the customers not enough. Now we have these guys in there who are making some painting or some painting on the parts, and so you can have each and every raw color now easily with also Litos, for example. They have, for example, the printing of ceramics, which is also quite interesting. External partners like Materialize with Magix. We don't have a software here. We have also to take the one which is provided in the market, and we are proud that we can work here together with these colleagues. I already said it, if you need a part which is not really fitting inside our machine, no problem at all. There's always a partner in our family, in our sister companies, where we then try to help the customer that in the end, even a part which is like you see on the left-hand side, more than 1 meter high, or something around 1 meter high. So this is there's a burner of a rocket in this case, so this is all possible. Why AM? We hear already lots of things about it, so I hope I'm not just repeating things now. But you have to think about two different ways. On the one hand side, it's the component level, so to say. On the component level, we see with our technology the huge advantage that you can easily print customized parts. So if you need parts like helmets or stuff like that on polymer side, if you have a customer behind whose detailed needs for just a small series, for example, in this case, the technology is great because you can print easily many or a small number of parts and just combine it with different parts inside your building frame. And in the end, you have a stable and robust production there. On the other hand side, we have the functional integration. We saw it. Here we have also the LED shift, which was shown already before. But this is a great example. So integrating 10 functions into one part is a huge step forward for us. And also the parts are getting more and more complex. We saw it, the heat exchanger, for example. We have also cases like this in our business development, where we see also heat exchanging is really something where you can bring in huge advantage to the entire industry, and therefore this is something we can push forward further. On the other hand side, we have the production, the supply chain level. Production supply chain level, yes, for sure. On the one hand side, your production is getting flexible. When you have then a business case where you have many parts and you want to produce the parts flexible, can raise up the volume quite easily, you can combine different parts within one build frame. So this really makes it easy for you to scale the production in there. Also, on the other hand side, you have a flexible production chain. So what does it mean? For example, when you are producing now parts right now here in Germany, you want to send them then to United States or something else. Today we are thinking about the process of bringing it to the first of all to truck, then we bring it to ship, to send it over there, or sometimes also by aircraft or stuff like that. The world will be changed. On the other hand side, there's also a 3D printer, and you only send a file from one place to the other side, and the guys over there are also just simply printing the parts. So this can be a huge advantage there, and this will also change some kind of the industry and also of the availability of parts within the world. We also have here also the digital product lifetime. We added obsolescence parts, for example. You had always to keep the parts over a long period of time. You had to have them on stock. You had high stock costs. In this case, all you have to store are simply the digital files. And for sure, you have to freeze your process. This has also to be clear on that. Only in this case, you can also then later on produce the parts and can also, after years, easily have the parts available if they are needed. What are the main challenges which we see today? I put this now a bit on the polymer side this year. Last year we talked lots about metal side, so this year is a bit more about the polymer side. But when we check now the qualified materials, it's already tough with our technology. So we have selective laser resintering in this case, so you need semi-crystalline material to print it. So therefore, you have already a bit limited number of materials which are available. So but we have to handle these materials, and we have to find now the best way of getting these materials to the customers. So when you check now, for example, we have a PA12. PA12 was not possible to be used within an aircraft. Why? You will not fulfill the FTS requirements, so fire, toxicity, smoke, and also not heat release. So in the end, we came up with a new polymer, which was 2241FR, which was a polymer which is based on PA12, but it has some additionals inside. So we could, in the end, provide a material which can be used for the cabin. If we now go to the bit more, complex parts, or let's say also the parts which have to see more heat or has also to see more load, then we have to go for other materials. In this case, we run for a PEC material, which is HT23. What's HT23? So sometimes the wording of our materials are a bit strange, but it does mean it's a high temperature material with 23% of carbon fiber inside. So always also here the idea, we go together, the customer says, well, I have a requirement here, I have the requirements that, for example, I have to transmit high temperature gas. So what can I do? I want to have it easy and high, low weight construction-wise. Then we came up with this solution, and the solution was possible to be used for these customers there. When I'm jumping now back to the HT23, PA2241, sorry for that. This material is already available for Airbus. So it's something where we have a signed Mars together with Airbus. And these are parts which can be now easily printed. You can print them, you can have them available on your aircraft. So not just for small aircraft, for business jets, but also for an A350, which is here the case. Great about that is coloring is possible. You can have each structure on the surface, which can be easily adopted on there. And even more, you can print a high number of parts even after years if you have them maybe also not available anymore. Of course, there are limitations, like always. In this case, we just allow to use this material for class 3 parts, so only without load, only fire, toxicity, smoke, because heat release has really a problem here. This material, like all the polyamide materials, tend that you have not the chance that you fulfill the requirements of heat release. In the end, these are now materials which can be used for the aircraft, and we hope that we can see them quite fast also there. Oops, sorry for that. HT23. HT23 is now the second material. I already said something about it. Perfect for high stress, perfect for high temperature And you see we fulfill there with this material already the requirements of the Deutsche Bahn, which is extremely tough to reach here the figures. And even these parts can be produced quite easily with high strength of the material and yeah, perfectly for cabin interiors, for example. Now we come to the positive business cases. Of course, like Sonja said it before, not each and every part which we see is a good business case. So for example, the worst thing I saw within the last year was a part, as you said, it was really just a T steel part. It was huge, which they said, hey, can you print it on the machine? And I said, probably yes, but frankly, it will cost more than 10,000 euros. And they said, what? How can this be 10,000 euros? Because when I take it somewhere else, you know, it's just under 200 euros. It's unbelievable. It's too expensive. I said, yes, but it's not even a minimum optimized for our technologies. And this is important. You really have to change your mindset, as said. You have to change your parts. You have to make them bionic. You have to integrate functions. You have to make them lightweight. And you have to print as less material as possible. Then it makes really sense. This is what I said here. So you can change cost, you can really save costs with your parts. You can easily do this. So by simply first step that you just filter your parts, your pool of parts, and the second then you just have to bring together a team, as Sebastian said so correctly, and you just bring together a team, and this team is then simply trying to make this setup fitting for the AM technology. If this is not really working, in the end, there will be no cost saving for you, and in the end, this technology makes also no sense, especially not for this part in this case. Faster aircraft turnaround time, yes, we saw it today. It's great when you have your serial production in-house today. If you have the business case for it, it's perfect, because then you simply don't have problems there with the parts with your suppliers. We know now, due to the Corona situation, many suppliers are a bit struggling, like everybody. So therefore, 100%, if you can make it on your own this way, easily, it's an option. Learning by doing, this is also quite nobody steps into this market and is a 100% expert. These experts are really rare. So we hear it also, there's now software coming up which helps you, but it will never, also in my opinion, replace a application engineer. These application engineers simply know extremely good what's happening inside the machine, and they also know pretty well what's the best setup of this part. So it's really, at the beginning, you have to go together with the customer when they decide for a machine, and you have to walk together with these customers that in the end they are successful with the solution and that they are happy with the solution. Just bringing their printer, saying, well, have fun with it, doesn't work. But in the end, yes, there are solutions. Now, I just show you some additional ones. For example, Deutsche Bahn, they highlighted quite good here these air duct, which is a part. Normally, you would say, okay, it doesn't matter. It's a small part on the side that can be produced for huge numbers and stuff like that. But the numbers which are produced are so low that it really makes no sense for them to do this differently. So they can do it this way. Also, we had Etihad. Etihad also walked the long way with us, and in the end, they had now the certification done for the parts, and they can now produce cabin parts with PA2241FR. The last one is also quite funny, or a great example, so to say. This is for a business jet. This is F-List, who's producing the inlays. So it's before that it was honeycomb structure. And the work which has to be done was incredibly high. So these parts had to be milled with the 5-axis engine stuff. And the workload was extremely high. And in the end, it was just a very, very easy to be printed part. Because in the end, you don't see the part. It's just in the inside. And if you have then the different layers on top of it, like here, you see furniture on there, the part is great. It was a good business case in this case. And in the end, it was also quite useful for the customer. Here's again the picture, just a bit that you see it a bit better. It's just the armrest, and you see where the cups are normally inside, and now you see the inside on the right-hand side. A bit more, I already said it, is then also these mindsets, this changing mindset. I already had this with the transportation times, which really go down on the one hand side, but also the customized parts, which are available already today on the right-hand side. You can easily print your own interior parts on a car, for example, or also parts like we have here on the right lower side, like a prothesis and orthesis, which are customized in this case. And on the left-hand side, you see the huge data volume, which we had also already discussed before. Many startups and small companies starting in this area right now and are really trying to store and handle all this data which is available right now. And therefore, in the end, this entire industry is really moving further. This is the good thing. So we're making step by step and going, as far as I see, in the very good right direction. Today, not everything is perfect, but for sure, this is a good step in the right, in a good aerospace-driven industry. Don't want to say any more about this because we had it already before, but it's a great business case, and I just want to say here, this was for us as well a jackpot situation, because high numbers of parts, a huge trust from the customer, a well-experienced and a well-trained and good team on the other hand side, who is working together with us on this. That was really just fun, and in the end you see what's possible with the part. Also, this is quite interesting. What we see more and more coming these days is the space industry. Here, for example, we see a burner nozzle for launcher. This is simply perfect functional integration. On the one hand side, you can easily integrate the cooling, so you fill the cooled or the ice-cold liquid oxygen outside, and inside you just have the burning process taking place. So this is a perfect combination of two things, and we see today already that this mini launcher market is now really moving further, and this is just possible with such an industry like additive manufacturing, because printing so small and detailed rockets and rocket engines is pretty tough, and it's just possible with a process where you have no other way of doing this today. Okay, so just also coming right now to the end, if you have questions, would be happy to answer them. Okay.
Thank you, Benjamin, for your presentation. I see there is a question.
Mm-hmm. I have a question. We heard now 3 presentations from point of machine manufacturer, service provider, and OEM. I would like to know from everybody who is involved in that, where is the real driving force coming from? Is it the machine manufacturer, or is it the service provider? We saw a little bit of a competence in between. Where go most of the machines? Do they go to service providers or OEMs? And why do OEMs still invest into this?
Yeah, it's a bit hard to say this. It's a bit different, the markets worldwide. So when I check now, for example, a bit more the East, I would say it's a bit more the machine seller. On the other hand side, when we check now here, Europe, Central Europe, for example, then I would also say our hugest customers for sure are the engineering suppliers or the distributors which we have in here. So this is the basic driver for this industry. And we see this especially also with their software. So lots of software really come from these colleagues, and they are really driving this also further there.
Because you still have a long way to go with conventional production.
For sure.
Processing, metal processing, and
for sure.
Injection molding, and all these processes, which are still very large.
It's huge, it's huge. And one important point is we will never replace one of these technologies. There was also some starting point where people saying at the beginning, okay, in future I won't need milling anymore. So we saw it perfectly on Sebastian's presentation today. You need it of course. We can't live without the support on these sites, for example. And also the fine work which has to be done by conventional systems. Yeah.
I liked one of the slide which said talk.
Yeah. Was yours? Yeah.
Very good.
Yeah.
If you don't talk to each other, you will never find out what the demand is.
And frankly, this was also a problem, or there was a mistake we did in the past. So not we as AOS, the entire machine sellers in the past did this. We sold the machines and were running through the market, let's say something around 2015, 16, in this direction. We were running through the market and saying, well, look, more or less everybody can do it. But in the end, you found out, no, it's so complex. You really need well-trained people on the other side who know what they are doing, knowing much better than we do. And the most important thing is we have to learn from this market. So we are just the ones bringing the system. Yeah, okay, there's the system. But we have no idea about the entire complexity of these processes which are right behind that. All these things like the qualification and stuff like that, these are things we can try to help and tell the customer, well, look, we can tell you what's happening inside the machine, but the customer knows what's really needed from the authorities and all the guys there. I hope I answered the question. Okay.
Okay. Thank you, Benjamin, again for the presentation. Thank you.
Thank you very much. Good.
Yeah, ladies and gentlemen, now I have the honor to introduce myself because I have the last presentation before the lunch break. Yeah, and I started work in additive manufacturing, I think 6-7 years ago. There was a chairman for the standardization committee, aerospace testing methods in the DIN NL. This is the DIN committee for aerospace. Yeah, and together with Airbus and other companies, there was a decision to introduce standards in additive manufacturing. Okay, so we started making these standards, and after a short time, I saw many questions. Okay, what are the critical parameters, depending on the materials? What kind of quality assurance is necessary, and so on. Yeah, and this was the decision for me and other partners, Airbus, BMW, ESA Aerospace, to make a public-funded network. This is called AM Quality. I will present also a little bit. Yeah, and so in my talk, I will present you some information what we as manufacturer of industrial CT scanners can do for making the testing of AM components maybe a little bit cheaper. Okay, so my presentation, where is it? Okay, so as I said before, my name is Olaf Günewig. I'm working as business development manager at Dayondo. Dayondo is a relatively small company with 45 employees located in Hattingen, in North Rhine-Westphalia, sorry, not in Bavaria. And we are a leading manufacturer for industrial CT scanners for non-destructive testing. Yeah, we have completely different machines in our setup, starting from ultra-high resolution CT with 300 nanometers resolution, up to very big CT scanners with linear accelerator as radiation source, where you scan a complete car, for example. Yeah, if we look onto additive manufacturing, what's important? Important in additive manufacturing for entering serious production is the automation, the robustness of the process, the quality of raw materials and manufactured components, so that you have a right first time production. Now, so based on these 4 factors, we started this network AM Quality around 3 years ago. It's public funded. Here on this page you see the partners. And many thanks to Benjamin, because he introduced the launcher nozzles. Okay, it was not ESA Aerospace, I think it was a competitor, but ESA Aerospace is with exact this topic, launcher rocket nozzles, out of Inconel, member of our network. Yeah. So you see there are many small and big companies. There are R&D institutes, several Fraunhofer institutes. Yeah, so it's a very interesting combination. And yeah, what we will do in this network, yeah, we have 3 blocks. The first block deals with the powder, the stable quality of the powder, and the effects of recycling of the powder, of the metal powder, on the quality of the AM parts. Yeah, the second block, block 2, deals with the introduction of in situ sensors into the AM machine, because I love selling CT scanners, but we try to implement by cognitive systems, that means artificial intelligence, as a process control where we get the results of different in situ sensors, not only optical tomography or melt pool monitoring, but also some kind of NDT testing. Yeah? We get the results of these sensors, put them into the artificial intelligence, and in the third block, we are doing quality control. That means destructive and non-destructive testing, and the results of these block are used as training data for the neural networks. This is the thing we would like to do in this network. Yeah, how can computerized tomography help? Okay, I will present some interesting topics, computerized tomography in the area of powder analytics, and computerized tomography for quality control of the parts. Yeah, this is one project, one sub-project I would like to present in this network. This project 1.4, incoming inspection of the metal powder by nano-CT and 3D image processing. Yeah, that means at the moment you have lots of different analytical methods for the characterization of the metallic powder. Yeah, you use, for example, optical microscopy, scanning electron microscopy, chemical analysis, metallography, laser diffraction. These are only some techniques you are using. And the costs are extremely high. For all these instruments, 700,000–800,000 euros, plus the technical experts you need for the operation of these different techniques. Okay, so we had the idea to use computerized tomography to get as much information of the powder as possible, and therefore this is our new CT scanner with ultra high resolution. That means with this machine you get 300 nanometers of resolution. And if you put a powder sample into this machine, you get the exact size, the morphology of each particle of your powder. And here you see the powder distribution out of the CT data, for example. Here you see the powder grain size distributions of different powders. This is Inconel, this is aluminum alloy, this is steel, for example, so you can investigate all kinds of metals. Here you see also that it's possible to detect holes inside the particles and also foreign material inclusions in the powder. So with this technique, you can analyze the powder with only one technique. And as part of this network, we'll develop a new CT scanner especially for the automatic investigation of the AM metal powder. This machine will fit onto your table. You put 30, 40, 50 samples inside, push a button, and you get these kind of results. Yeah? And you don't need analytical equipment for 700,000, 800,000 euros and 5, 6, 7 experts. Okay, this is one thing we do in this network. Now I come to the block 3. Here is another system which we are using for the testing of the manufactured AM parts. This is our system Diondo D2. This is a more or less universal high-resolution CT system. That means this system starts at resolutions of, let's say, 1 micron. But you are also able to investigate samples with 500 millimeters diameter and 680 millimeter high. So that means it's really universal. You can do investigations on powders, you can do investigations on polymer and metallic AM parts. Yeah, and what's interesting is you can, on the one hand, add onto this machine an automatic part changer. That means you can place, it depends on the size of the samples, of course, but you can place up to 100 samples into the machine. You put a switch, then you go into the weekend, and on Monday morning, you get the results fully automatic evaluated. Yeah, that means I think this is a really decrease of the costs. Yeah. Yeah, if you have samples like Airbus, then this automatic part changer, maybe the parts are a little bit too big, but we also have systems with a robot. That means, again, here your parts enter the machine. The robot takes the part, puts it into the machine, and again, you press the switch, go to the weekend, and afterwards, you have all parts in fully automatic investigated. At the moment, these machines are in the casting industry, in the automotive casting industry, for example, but you can also use it for additive manufacturing, of course. Yeah, now I will present some examples, what you can do with these kind of machines. Yeah, as an overview, with a CT scanner, if you put the metal AM part inside, yeah, you have the whole 3D data. You get the whole 3D data of the whole part. You can look for pores inside the part. For each individual pore, you can characterize the position and the size. You can do investigations, process characteristics, for example, for the hot isostatic pressing process. That means this is the situation without hip. This is the situation with hip. So you can compare the effect of the hip process. You can do metrology, take the dimensions of the part, the internal dimension and also the outside dimension. You see powder residues in the part, of course. And what's also possible, you can characterize the surface roughness of inner structures where you have no chance to enter these regions by optical techniques, for example. Yeah, some examples. Here's this part. This is the real sample, a photo of the real sample. This is the result of the 3D CT scan. You can do tomographic cuts through the part, and you see here pores inside the part and powder residues and so on. This part is from a satellite. It's an aluminum alloy. This is a wheel bracket from a satellite. Very interesting part. Again, you can do pore analysis, defect analysis. The interesting thing at this part is there is a QR code inside the part. so that you are able to identify each manufactured part. This is a very cool thing. Yeah, and here you see the QR code, for example. You can read out the QR code, of course. Yeah, here an example for the surface characterization. Yeah, here you see a relatively rough surface. Yeah, and it looks similar if you look by optical microscopy onto this region. Yeah, so this is an outside region, but you get the same results at internal cavities, of course, where you have no chance for an optical investigation, of course. Yeah, we talked about titanium parts. I said titanium parts are not really the best suited parts for computerized tomography because you get scatter, you have a relatively high absorption of the material. So what's the benefit of our CT scanners? Our CT scanners, they are really flexible. That means you can put different X-ray sources into the machines and also different detectors. So if you have a 3D CT scanner which has an area detector, that means you rotate the sample over 360 degrees one time, and then you have recorded the whole data for a 3D CT scan. Then you get, for example, this is a gimbal made of titanium, also an aerospace part. Then you get really bad results because of X-ray scattering. That means, especially in these areas, you see these are very bad results. And so you can switch to the other detector, in this case, a line detector. And by these collimators here, you can reduce the scattering effect significantly, and then you get very good results. So this means it depends on the samples you have. Yeah, what kind of CT scanner is the best solution? And Dioner is also very flexible in the design and implementation of the individual CT solution, the best CT solution for you. Okay, here I will present an example for the automatic part changer. Yeah, our customers was interested in the evaluation of the HIP process. And in this case, 24 test samples were put into this automatic part changer. And they were investigated fully automatically by the machine. And here you see the examples of the results without HIP and with HIP. So there is a significant reduction of pores as consequence of the HIP process. And if you implement new components, new materials, then this qualification process is very relevant to do. And so the automatization is a real benefit. Yeah? Because if you look on the cost situation, on the one hand, you have the costs for the machine. Okay. On the other hand, you have the employee costs. And if you have qualified employees, then the influence of the employee costs are higher. Okay, some examples on polymers. These are this carbon fiber reinforced material which was manufactured additively. And this was also a qualification project with the customer. So the customer was interested in the orientation of these fibers, of these carbon fibers inside his part. And by computerized tomography, it's possible to automatically detect the fiber orientation. That means, again, you put the parts inside the machine, put the switch, go to the weekend, and then you get the results, the automatic fiber orientation measurement. Another example, also an additive manufactured CFRP component. In this case, there are metal inclusions inside. I don't know why, But here, these bright spots inside the part, these are these metal inclusions. Maybe some kind of contamination, I don't know. Yeah, this is a part, a normal plastic AM part, which we have investigated. Okay, at the moment, the quality, this was fused deposition modeling, of course. The quality, you can compare it to injection molding. Okay, it's not so good, but by computerized tomography, okay, you see some problems here in this area, but it's also possible to make a variance comparison between the CAD model and the 3D CT. And this is done here. Yeah, that means you see where is a very high derivation between the CAD model and the produced component. Also, again, fully automatically, of course, and 3D. Yeah, last example, also again an aerospace part out of PEAK. And here you see the 3D pore distribution inside this part. Yeah, again, you see every pore, the location, the geometry, and the diameter. Okay, thank you yeah, for your attendance. Do you have any questions?
You showed the system for the powder analysis. Can you say a little bit about the cost of that? Like how much would scan cost for like a powder sample?
Okay. I said we will introduce a new CT system for the powder characterization at the moment because it's the R&D phase, I would say. Yeah. I have no ideas concerning the costs. I think the costs would be in the same region as a high-end laser diffraction system. A little bit more, I think, 140, 150. But we have to discuss this internally, of course, because at the moment, because it must be attractive. But with this system, it's a specialized system for powder analysis, of course. This is not a universal CT system. But we implement a special kind of software. I'm not allowed to say because of NDA and so on. But we will implement special kind of software in image enhancement to get nearly the same results as with the very high resolution system, because the very high resolution system costs a lot of more money, 500–600K. Yeah? And you can do some software tricks. Okay, as I see that there are no more questions, this was the last presentation of this morning's session. Yeah, then I end this session, and now we have a lunch break until 2 p.m. Thank you, everybody.
His heart is cold. No need to ask, he's a smooth operator. Smooth operator. Smooth operator. need to ask, he's a smooth operator. Smooth operator. Smooth operator. Smooth operator. Coast to coast, LA to Chicago, Western Mail. Across the north and south to Key Largo, love for sale. Smooth operator. Smooth operator. Smooth operator. Smooth operator. Smooth Diamond line, lover boy. You move in space with minimum waste, maximum joy. City lights and business nights. When you require streetcar desire for higher heights. No place for beginners or sensitive hearts. Sentiment is left to chance. No place to be ending, but somewhere to start. No need to ask, he's a smooth operator. Smooth operator. Smooth operator. Smooth operator. Coast to coast, LA to Chicago, Western Mail. Across the north and south to Key Largo, love for sale. ask. He's a smooth operator. Smooth operator. Smooth operator. Smooth operator. Coast to coast, LA to Chicago, Western Maine. Across the north and south to Chicago, love for sale.
Somebody's taken over already. It's either that or I'm very good at throwing my voice. Right, so welcome back to the Future Mobility section of today's conference. I'm Daryl Swanson. I'll be moderating for you today. So my background, I'm an aviation planner, an aviation consultant. I help people buy airports, plan to design airports around the world. Got involved and stung by the electric aviation bug. So I'm really looking at what the infrastructure looks like for electric aviation and trying to do some demand modeling because when we're actually looking at where these new future aircraft are going to be flying, we haven't got this traditional methods of doing that type of demand modeling. So we're going to kick off first from a presentation from Marius Bibesel from Airbus. He's going to update us on things that are happening with the city Airbus concept and what Airbus are doing. He's also just informed me that he's moving internally within Airbus. Obviously, lots of changes going on, but the good news is that the work that they're doing is going to continue. So I'm going to pass straight over to you, sir. Hand the mic to you and take it away.
So thanks a lot for the invitation. It's a pleasure to be here during these challenging times. So as Daryl mentioned, City Airbus is the topic today, so it's a pleasure to give you an update on this one. No, this is the wrong presentation. It's an interesting one, so I like the vehicle, but it's not the City Airbus. So, I'm in control of the slides? Yeah, I hope so. So I would like to switch to the slides, but yeah. So, well, a bit of a difficult introduction. So, I mean, before I go on to give you some details on the City Airbus as the electrical vertical takeoff and landing vehicle we have developed at Airbus Helicopters, I would like to give you an introduction. What is the motivation behind? So what drives us to go into urban air mobility? And I think that the first slide is quite obvious. So we have urbanization as a trend. I think this is confirmed. So a lot of people will move to cities. So we expect that 60 to 70% of the world population will live in the cities in I would say, couple of years. And this, of course, leads to the known problems. So we have strong congestions in cities. And this is something which is, of course, very annoying, but on the other side is also an economical factor because we spend a lot of time in traffic jams and we are not productive. So what we are offering and what drives us at Airbus is to introduce the third dimension. So just to go away from the ground-based transportation and to offer in cities this kind of, let's say, air taxis to take a certain part of the transportation needed in a city. For sure, we will not replace buses and metros on ground, but I think air mobility is a very interesting option we have because it's something which will be on time and which will offer you to move inside a city in a completely new way. So, well, the headline is Shift from Premium to Mass Market Solution. I think urban air mobility will not be the mass market solution. However, to increase the amount of transportation we can offer, we have to take some steps. And what you see here is I would say, the technical milestones against the economic factor. So what does it take? In fact, you can offer urban air mobility even with the conventional helicopters we have today. If you adjust the business model, which we did, you can pool helicopter operators and offer already, let's say, helicopter transportation in cities, which is quite attractive. But of course, with the conventional helicopters, which are more expensive and which have a higher impact on environment, this is not the way to go. So, of course, the next step to come closer to urban air mobility is go to the next generation of electrical vehicles. So this will have an impact on safety. This will have, of course, an impact on environment because we will be locally emission-free. And we expect that in terms of noise emission, there will be a huge advantage on this kind of aircrafts. Then the next step is, well, pilots don't like me when I say this, but getting rid of the pilot from an air taxi is something which is interesting in many aspects. First, of course, it's an economic factor because the payload of such an electrical vehicle is not that large for the time being. So if you can load more passengers is better. And of course, the safety and reliability moving in this, I would say, delicate urban environment is something which is very important. And then the integration into the smart cities will be the next step. So once we are there and we manage to have traffic management, to have all the ground segment, the infrastructure needed for this kind of vehicles, I think then we can say that we have fully developed this kind of market. Why urban air mobility is so attractive? It is because it's not just about the aircraft. So, of course, this is the entry card, so you need one efficient, safe, certified electric VTOL to provide this kind of business. But on top, I think there are a lot of other business models which are very attractive, so support and service is something we can offer as well. All the aspects of flight operations, so offering fleets of air taxis is an attractive business model. Air traffic management will be a bit of the backbone, I would say. This will be a very essential brick in urban air mobility. And then, as mentioned before, the ground infrastructure plays an important role. So we will need definitely the right ground infrastructure in cities to provide urban air mobility. And the passenger solution. Of course, it will be, so we're aiming for seamless transportation, so the right passenger solution, the right app to book this kind of flights will be very important. So, coming to the City Airbus. So this slide is highlighting the, I would say, main design criteria we have set in the beginning. So this was back in, I would say, 2016-17 when we started. And we were pretty sure, which is a no-brainer, we need the high level of safety and the low environmental footprint to be successful. Moreover, we think that simplicity, modularity, scalability is essential because to provide this kind of business, we need to be more cost efficient than helicopters. The sweet spot is around 4 packs, so I think this is the best compromise between being very agile, managing to load the aircraft in a very fast time, and I would say then the right size, not to get too big, too heavy, and too noisy. This kind of air taxi transportation, I would say in average, it takes 15 to 20 minutes per trip. So you need a spacious, easy accessible cabin. So it doesn't make sense to have some kind of a very fancy aircraft and then you sit like in a sports car and it takes 2 minutes to get in and out. And then the other point is, of course, even though City Airbus is a demonstrator, it's not a product, but we wanted with this demonstrator to look into how we could design this kind of aircrafts for higher volume production and for lower costs, because this again will have an impact on the costs. And one of the paradigms, I'm not sure we can keep it because it's a bit of a trade-off between the compact dimension we have on a City Airbus and the efficiency. So the bigger you go, if you implement wings, the efficiency will be much better, but at the same time it becomes more difficult if you go to higher wingspans. The operation in cities on the helipads will be a bit more tricky than it could be with a City Airbus. Just a quick overview. We launched the City Airbus project in 2017. So I would say it was done in a very agile mode. So for Airbus, it's really in a startup mode. It was built around a core of only 30 people, which is amazing. We had, I would say, a particular governance and cooperation model. So one important part was that we developed the electrical system together with E-Aircraft System, which is it's part of Airbus, and Rolls-Royce, which was former the Siemens AG. So this kind of ménage à trois offered us the electrical system we needed for the City Airbus. And as you can see, at least for the milestones to the first free flight we have done with the City Airbus, we were pretty quick. So we have done a demonstrator PDR after just 6 months. Beforehand, we have done a lot of de-risking testing. Then we had a bench test of the full electrical system by begin of 2018, which was a very important milestone for us. We had high voltage power on in, I would say, after 1.5 years, which is, I think, amazing. And then, of course, we went, I would say, through a maturation process. So we did a lot of testing to be able to do the first flight in Donauwörth on the airfield of Airbus helicopters, mid of 2019. So this one was tethered for safety reasons. And then after further improvements, we were able to do the first free flight by end of 2019. So what is the approach? What is the rationale behind the City Airbus demonstrator? So we call it a no-toy approach. So we wanted to have no cheating there. So in terms of platform, it should be representative. So the size, the weight, and moreover, what is important, the safety architecture, which we implement, which we integrated in this kind of vehicle, should be realistic. So, of course, we did not qualify this or certify this kind of vehicle, but the safety architecture behind it is good enough to be certifiable if you want to. And then, of course, we wanted this kind of very quick proof of concept of this kind of bird, which I think is unique because we are around 2.3 tons, and I'm not sure if there are many competitors out there at this weight class flying such a vehicle. And we wanted to use this kind of platform as something we can use as a basis, and then if there is anything we need to focus on or to improve, that we use the City Airbus as a basis for this one. There are some, I would say, key design features on board, which are very important from a technical point of view. So one of these is really the high lift duct concept. So this is very particular, something we discovered and we developed, I would say, on the way to the demonstrator, and which provides a lot of efficiency, in particular in hover. And the other point is we wanted to step already into this kind of low noise design. So what we have done already with this kind of demonstrator is first optimization. So we have a 3-bladed propeller, and moreover, we have an extremely low tip speed. So in this case, we are around 120 meters per second tip speed, which is, I would say, 80 to 100 meters per second lower than on a conventional helicopter. And this makes a difference. It doesn't make it particularly more silent, but I think the annoyance and the way you perceive this kind of low frequency noise is completely different to helicopters. Some technical details on the City Airbus demonstrator. So we have in total 8 fixed pitch propeller. We have a variable RPM control around the nominal, I think it's 950 RPM, with a RPM change of plus minus around 60% to control the aircraft. We have 8 electrical direct drives, so the power installed is tremendous. So the maximum power per motor is 200 kilowatts. So in total, we have more than one megawatt of installed power. Of course, this is not something you can deliver at one time. Is the maximum peak power per motor. The maximum power you can get out of the batteries is around 700 kilowatts. We have this kind of single failure tolerant architecture, so the safety architecture I mentioned before. We have 4 distribution boxes, and all the architecture, in particular the electrical architecture, is designed in a way that we can cope with any kind of single failure. So we can lose one of the 4 batteries, we can use one of the 8 motors, we can use one of the 4 distribution boxes without having a critical or a failure of this kind of aircraft. Then the low noise design, and on top, this is, I think, important to mention, the ground control station. So we had a ground control station which was very well equipped, so all the monitoring necessary to operate this kind of vehicle was on board of the ground control stations. And moreover, at a certain point in time, we decided that we don't go on with automatic flight from the beginning, so we implemented a pilot input. You can see on the right lower side, so there was really the pilot in the ground control station having some basic stabilization of the aircraft, but still controlling and steering this kind of aircraft, which was a challenge for us all, and was a challenge for the pilot, of course, who is not used to not be on board and not feel in this kind of aircraft. This is a testing overview. So you see, we used to say, if you have a small aircraft, you have small problems. If you have a big aircraft, you have big problems. So what you can see in this kind of testing overview is it is challenging to put such a vehicle in flight. So we started end of 2018. We've done a lot of ground testing to make sure the functionality is there. Then we started with ground runs, so meaning with the propeller turning. So this was a lot of work to be done to make sure that this kind of aircraft is functioning well. And then we moved on to the first bound flight. So the first tethered flight was, I think, on the 1st May, on the Labor Day of 2019, which was just a small hop, in fact, but a big hop for us. And then we did a lot of refinement until we were, I would say, confident enough to have a free flight. And please keep in mind, this kind of flights were done in Donauwörth on the regular airfield. So, of course, we had a safety concept behind, but still, it is tricky to operate such a new vehicle for the very first time, close to the proximity of buildings and hangars and so on. So this was a challenge for us all. But I think in the end this was the right approach because we faced a lot of small and big challenges, and it was good to be there, to be close to the aircraft and to be able to really solve this problem by problem, and then to be able to go on the airfield and to test if it works or not. And then we're very proud that we managed now to have the final step, which was the automatic hover and a slow forward flight, which we've done mid of this year. So this is quite fresh. So this is summing up the highlights for this year. So I mentioned the flight test campaign. We call it in manual hover mode. So we're with the pilot in the loop. Was completed mid-2020. We did the first automatic flight in July 2020. We have performed some successful VIP demo flights. So our Minister President Söder was here, or not here, was in Donauwörth, and witnessed one of our flights, as well as the Verkehrsminister Andreas Scheuer. So we were I would say pretty happy and very proud to be able to provide this, because it makes a difference. If you are there, if you can see, if you can hear and feel this kind of aircraft, it's a game changer. It's not just having this kind of theoretical discussions on urban air mobility. You really feel this could be the future, and it makes sense. And then during the last months, we moved the city Airbus to Manching. Manching is a restricted military site, so it's much bigger and offers more freedom than the airfield in Donauwörth. And this is the perfect spot to start enlarging the flight envelope. So we will continue with the automatic hover, and out of the automatic hover we will move on to slow and medium forward flights and increase the altitude. And what is important, we will have I would say, for a lot of flights we will perform, we will have noise measurements, because it's very interesting to see how the noise emission is not just in hover, but also in slow or medium forward flight. And then at a certain point in time, I'm not sure. It depends on the progress we are doing. It depends a bit on how much we think we can squeeze out of this demonstrator. But for sure, there will be a certain point in time where we will say it's enough for the City Airbus, and then we will complete the lessons learned and plan the next steps. So the lessons learned include not just the City Airbus. We have the knowledge of Vahana as well. Vahana were our US friends, which is a different type of aircraft with double tilt wing. And they completed their flight campaign, I think also during this year. And this is something which is very nice because you have two different concepts, the know-how of two different concepts, and you can merge them to whatever is the best for the future. Good, and I think that's it for the City Airbus. I think we have just one video at the end, just to give you a flavor to see for the, I think it's the first automatic flight, to see how it looked like. And I think the noise should be part of the video as well. So I hope it works. Yeah.
Telemetry, ground control station, we are starting the takeoff procedure. So pre-flight test, 3, 2, 1, top.
Yeah, it is a great day for the City Airbus. We performed today the full automatic flight. So this means we had an automatic takeoff of the aircraft, the stabilization in the air, and of course an automatic landing of it.
Airbus 4, Red Fox 2, we are ready for first takeoff. For takeoff, 3, 2, 1, takeoff. Engine ramp up. Aircraft steady, aircraft lifting. All parameters in green.
Everything went perfect, so we are very happy. This was a great achievement for us. Manching is the next big step for us, so we will move to Manching end of August, and we will extend the flight envelope of the aircraft. So we will fly forward, and then we will fly at medium and higher speeds than we did here in Donauwörth. There we have the secured area to do this kind of flight envelope extension we need to do.
Everybody, ground control station, we go for landing. Seat rate is okay. Eagle has landed. Congrats, guy. Cockpit, congratulations, everybody.
Et voila, that's it. So, questions?
Very impressive. How do you overcome this noise problem?
The question was how do you overcome the noise challenge, and that is going to be a big issue for electric aviation.
I think it takes some development. So what we have here is just a three-bladed rotor, so it's not particularly optimized for noise. So for sure, the blade design, the blade tip design can be optimized further. We have to find the right spot in terms of blade tip speed, because this has an impact as well. And then what we have in mind is, in particular for the flyover, to be more silent than we are today. So we have a lot of concepts ongoing, and the investigations are not starting now, they are ongoing now, to make sure that we are less noisier than we are today. This kind of aircraft as it is here, it is less noisier than a helicopter. As I said before, it's not that annoying. I think the video was a bit misleading. If you are there, the sound emission is very pleasant, if you can put it this way.
A pleasant helicopter noise.
Yeah, and I think all this catalog of measures, so blade design, blade tip design, improving the forward flight efficiency, and then moreover finding the right adjustment for the blade tip speed will make the difference.
Blade diameter, big factor?
Yes, yeah, for sure. So this is, we are here at around 2.8 meters, so it's a quite big blade. To make it more efficient, we can increase the blade diameter. So these are factors which are important. The blade loading or the disc loading of the aircraft has to be considered as well. So this was the first step. We are very confident and very happy that we are on the right way to make it as silent as needed.
Right. One more question here.
Why did you choose 4 propellers and on top of them, so in total 8? Counter-rotating probably, no?
Counter-rotating propeller, yes. So 8 is a quite good number in terms of redundancy to be able to cope with single failure problems. So this was one reason to take 8, and then we wanted to stay as compact as possible. So this is why we opted for the coax configuration. This is not so efficient in terms of hover, but we discovered a lot, I would say, of ways how to introduce ducts, how to have narrow ducts just on the lower propeller in a way that you are very efficient in hover. And then you can be also as efficient or more efficient in forward flight compared to having a very huge or a very high duct, which usually you would apply on a coax rotor.
Right, last question.
It's quite heavy, 2.2 tons, is including passengers.
Yes.
Okay.
So it's just a demonstrator, but even for the demonstrator, the payload, I think it's quite attractive. So I don't have the exact number, but it's above, or it's more than 200 kilograms for the time being. But of course, we have a lot of flight test instrumentation on board, a lot of equipment, which in future will be the payload.
Payload is going to be everything in terms of fee-paying passengers, so definitely understand the drive towards automation.
Yeah.
But yeah, I think automation is the future, but it is just going to take us time to get there. So thank you very much, Marius. Brilliant.
Thanks.
Right, so moving swiftly on, we have now Professor Harry Wagner from FMS, so it's Future Mobility Solutions, and I had a brief chat with them, and what they're doing is looking at simulation to try and help optimize city design, and it's going to be interesting to see how they incorporate that into future mobility solutions. So, sir, take it away.
Hello, welcome everybody. Good afternoon. Good afternoon to all the people who are digitally online. My name is Harry Wagner from FMS, Future Mobility Solution, and I would like to talk to you today about routed networks or network mobility. So what is this title about? I mean, why this title? And what has this to do with AirTech? What has this to do with drones, with flying in the third dimension? I'll try to give you an answer, but first of all, my key statement would be for today, no matter what type of technology you have, no matter what type of product you have, no matter what type of service you have, from our perspective, it's the integration and bringing technology, products, customers, and everything together. And this is why we think mobility needs to be networked. It won't be of any future perspectives to have a perfect product, a perfect drone, perfect urban air mobility, without integrating urban air mobility into all the other transport modes that we have. And this is why we think mobility needs to be networked, whereas today mobility is very oft routed. So we have to use the infrastructures we have. And to start off, I very often take this comparison. It's all about demand and capacity. And when we talk about mobility, and I will talk about mobility in general in my speech, but I will have some excursions into the urban air mobility as well. what are cities doing if we have a lot of traffic? Cities are very often focusing on increasing the capacities. So building new streets, building bridges, building tunnels. But what is very often neglected is to focus on the demand side. What the customer can do. I mean, we often have solutions that customers very often don't even know. So without having a customer who knows the solutions that I have, how can I transport my product, my service, and exploit it and make it successful at the end of the day? So you all know these figures. I don't need to focus on these numbers. You know that the people on the road are currently constantly increasing. You know that the goods on the road are constantly increasing. It has been increasing over the past decades and will continue to increase in the next couple of years as well. So what we think is, when we talk about mobility, we think about mobility needs to be integrated, mobility needs to be networked, and mobility needs to be looked at from the demand side as well, not only from the capacity side. I don't want to say that the capacity side can be neglected, but we have to put both things in common and put together. So how does a central station look today? I mean, you know probably this is Munich Central Station. Very often central stations are based in the cities, in the downtowns of the cities. We have a nodal point there. Mobility is coming together at this one point. In the cities, there is not a lot of space to increase. There is a connection mostly of regional and long-distance modes, so it's basically railways, and flexibility and space is very limited. So thinking about the third dimension, thinking about establishing drones into cities as well, we need to think of how we can do this in central stations. Is there enough space? Where can they be located? Where can they take off? Where can they land? A lot of things that have to be considered when we talk about future mobility hubs. I mean, we call this a future mobility hub because it's a new word. The old language would say it's a central station, no matter what you call it. The problem that we have is, and it doesn't matter if you look into Munich, if you look into Frankfurt, if you look into Hamburg, and all the other big cities in the world, it's always the same circumstances, the same challenges that we face. So now, with the technologies and the new products entering the market over the course of the past years, with e-scooters entering the markets, with drones probably entering the market shortly, with car sharing products, with bike sharing, with bikes, with all the new modes of mobility, we very often tend to think that these new modes of mobility will increase the mobility situation in cities. The chart that you see here shows you that it's exactly the opposite. While e-scooters are entering our cities, public transport has decreased a lot, and this is something that must not happen. I mean, when we talk about new mobility modes, it is very important that we try, and again, I repeat this over and over again, we have to try to integrate it into the forms of mobility that we are currently having, for instance, public transport. And what I would like to see is a figure here where public transport increases as well as the other mobility modes increase as well. And there's a lot of discussions, and you read it in the news every day, about digitalization. Now, when we talk about mobility, there is always hardware involved. So there will always be, no matter if it's cars, if it's street scooters, if it's drones, there will always be hardware. And the key challenge is that we bring the mobility hub and the digital platform together with the physical mobility hub. It doesn't help us a lot if Uber is offering autonomous cars if everyone who's sitting in a car is sitting there alone, the same as they do today. So we have to think about a better split within the streets. How do we use the capacity that we have? How we do use this capacity more intelligent? And there is no, as I said, there is no difference if 60 people sit in their personal cars. I mean, if they are in a traffic jam in Beijing, it doesn't really matter if the car is autonomously driven or not, because the car is standing in the traffic jam anyway. So the hardware issue and the platform, the digital issue, is something that we have to bring together. And when we talk about mobility, we shouldn't only think of mobility. We should think of our lives. We should think of our working habits. We should think about a lot of things that mobility is used for, basically, to do. And we are engaged in a couple of projects that are thinking about future mobility hubs. So it's not about bringing a drone, a train, an e-scooter, car sharing, bike sharing together. It's about bringing together also working space. So let people meet and work on the mobility hubs and try to put the mobility hubs outside the cities. I mean, Munich Airport, or all the airports in the world, basically are doing something like this in a similar way. They all rent workspace. You go to Munich, you fly into Munich, you meet some other people, you meet working space, office space, and you work there. But this shouldn't only be happening in the airports, but also in the cities and in the major mobility hubs that we have in our big in our metropolitan regions. So shared space, co-working areas are some issues that are very important. And again, it's about bringing the physical layer and the digital layer together. You may have, I don't know how you traveled here today. You may have taken your personal car, you may have taken the train. Sometimes when I talk, I ask how many mobility apps do you have on your cell phone? And typically people say 9, 8, 5. I think the record was 26 or something like that. And we are thinking about why does it need to be like that? That in Munich, I need the MVG app. In Hamburg, I need an app. In Berlin, I need an app. Why can mobility not be further integrated so that I, as a citizen from Munich, for instance, have my Munich app, and if I travel in Berlin, I use my Munich app. And payment and all the other stuffs behind the scenes, I don't want to be involved with that type of stuff. So like the airlines do it, if I book a flight to Cedar Rapids in Iowa in the USA today, I go to Lufthansa and book my flight, and later on I'm sitting in a United Airlines plane or any other planes. And so all the payment is done between the airlines themselves. And what we have done, or what we try to do currently, is building a platform where several digital platforms can hook on, and the customer only needs one platform and can use the services from other platforms as well. We think this is very important. This will be more important with more mobility modes entering the market. So if at one point in time we talk about urban air mobility, about flying in the cities, the ecosystem will become bigger and bigger. And if Tesla has done one thing very smart, it's not about developing and building electric-driven cars. This is not the smart thing that they have done. The smart thing is that they have thought about the whole ecosystem before they develop their product. So they have developed their product, but they have thought about charging. They have thought about a charging infrastructure. They have thought about factories who build batteries. So they haven't only thought about their product, the car, they have thought about the entire ecosystem. And with the ecosystem becoming bigger and bigger again, with new mobility modes, this will be more and more important, not to only focus on your product, but also focus on the entire ecosystem that is involved. Okay, 60 seconds, commercial part. The FMS, Future Mobility Solutions, we are a young company based, located close to Ingolstadt. We focus on vehicles, on software and functional development from all types of vehicles. We focus on intelligent trips, so we develop solutions for intelligent getting from A to B. And we focus on the places that we are living. We work with cities, we work with communities, and we help them find the perfect mobility concept. So we have currently, I mean, within the last couple of years, we have developed a solution that we call Virtual City that helps us to simulate different mobility concepts and to hand over to cities and to simulate what type of mobility concepts they have, different scenarios, and then to choose the right scenario for the individual situation. And by the way, this week, Monday, we have been awarded from the BMVI, which is the German Traffic and Mobility Ministry, from Andreas Scheuer, with the German Mobility Award. And now give me 90 more seconds and I show you one video what the virtual city tool that we've developed is doing.
Traffic jams, emissions, stress, frustration. The population is growing, and with it, the need for mobility. Individual traffic is causing road infrastructures around the world to collapse. Transportation systems are reaching their limits and can't keep up with the dynamics. In order to make your mobility sustainable again, we have to break new ground. Therefore, we developed the virtual city at FMS. And this is how it's done. Enter your location. Our solution creates a virtual image for you. Your city wakes up digitally. In the three-dimensional world, you can design your infrastructure as realistic or visionary as you want. Add existing and new mobility offers and test which mobility mix fits the best to your reality. Simulate realistic traffic volumes in order to experience your decisions directly and to convince the population and decision makers. Improve your mobility ecosystem and make space for everything that makes the city more livable. Virtual City at FMS. Cost efficient, flexible, fast, and user-friendly. The way to a better mobility for our society.
So in a nutshell, with more and more mobility modes entering the markets, we have to really think about sustainability, and we have to think about the appropriate concept for each challenge that we're facing. So far, 20 minutes are over. Thank you for joining. Thanks for your attention. And I'm happy for questions, and our stand is just across, just right here. If you have further questions, you're welcome to join and talk to my colleagues and me.
Thank you very much. Really fascinating. I find it interesting because I look at vertiport infrastructure and how that could incorporate into micromodes of mobility and how we actually get passengers onto micromobility or onto public transport. But the interesting graph that you showed was that as micromobility increases, the use of public transport decreases. So you're just having that singular switch of mode. I would have thought that the real goal is to try and get people out of cars. And so is that some of the work that you're doing to try and encourage that shift, or are you just working on the planning of that and let the cities make that strategy call?
Yeah, good question. I mean, obviously we would have liked this shift as well, but the figures show that this is something different. What we thought when we started out 3 years ago, we thought cities have really difficulties to decide which concept is the right for my city, for my individual situation. So what we try to do is we try to simulate different scenarios and then try to show how it's going to happen. Now, with street scooters entering the market and not being able to take them on buses, it's pretty easy to figure out that this may cause any difficulties. So that shift that we have at the moment is a shift that we also don't like, and what we have to do is we have to put services into the market that allow the integration of different forms. And it's not only the street scooter and the bus, because this we can use today already. In the future, it will be the drone and the bus as well, or the drone and the taxi. If we think about vertiports, where do we build them? We have to build them in locations where we can ensure that from this location on, integrated onward mobility is available and possible. And if we don't do this, new concepts will probably fail.
It's interesting because one of the things that I talk about in my presentations on vertiport infrastructure is that vertiports have to complement public modes of transport, not compete. Because I think as soon as cities start to figure out that vertiports are going to increase ground congestion, they're just going to say no, because it doesn't make sense for them to do that. We've got time for a question here.
I can't hear.
Sorry, we haven't got the mic on.
You showed in your video usage of cable car in town. What is your view on this?
my personal take on this is that this will become a mode of transport in Germany as well, but obviously and unfortunately the politicians are very neglected to do it yet. But I think this is a further mode of transport that's going to happen in big cities. If you look into South America, this is already established and very well appreciated by the public. And in Germany, we have difficulties. We have difficulties about flying above grounds. We have difficulties with the shadows resulting from the cable cars. But this is true. I mean, this is what they discuss. And but I think within 10, 15, 20 years, we will see first cities having roadways, cable cars within public transport in the city as well.
Wow, a prediction. Right. Unless there's any other questions. Oh, that's brilliant. Thank you very much, sir. Appreciate it.
You're welcome. Thank you very much.
Right. So now we have Maximilian Funk from Funk. Oh, I was looking for you a little bit earlier. We didn't have a chance to meet up. Right, so I'm actually very interested, and you've probably seen their vehicle, which is just sat out in the entrance there, a very interesting concept in terms of a cargo drone, which is very interesting because I've recently been asked to participate in the World Economic Forum on cargo delivery drone type systems. So I'm very interested to hear about this. So I will hand over the podium to you, sir. Cheers.
Okay, hello everybody. Very warm good afternoon from my side. My name is Max Funk, and I'm in charge of the business development at B Appliance. At B Appliance, we manufacture and design heavy-duty transport drones, eVTOL aircraft. And I brought this topic to you because you learned a lot about urban air mobility and air taxis yesterday and today. And I think it's also time to talk on what's available on the market today. And there are means of transportation, aerial transportation, even VTOL transportation, which are called helicopters. But there are good reasons why helicopters are not the eVTOLs that we imagine with air taxis. Also, on the other hand, other side of the scale, there are drones, small consumer and prosumer drones, which have been filling the market in an insane speed. But the question really is, what's in between? What's in between that chasm between small drones and light helicopters? And that's exactly where B Appliance is based. And that's the topic that I want to talk to you about. So let's flip to this side. Just a really quick introduction to get warm here. Again, my name is Max. I studied aerospace and management at Technical University of Darmstadt and in Colorado at the University of Colorado in Boulder. And I had the pleasure to work as a student for multiple large aerospace companies. And after finishing my degree, I thought, okay, let's go back, go into a smaller, more agile kind of business and join B Appliance. I'm also holding a pilot private certificate. I've always really enjoyed to link the academia with real aviation, and that's exactly what we do at B as well. We like to focus on the technical details. We like to be really efficient, but at the same time, we like to go out and fly and make sure that that's a feasible concept, and that's where we both match. Little intro slide for you. This slide I found not in a newspaper, but in a website that talks about a newspaper, like we do it today. And my big question to you as experts now is, why are we not there yet? This image was shown in a newspaper in Chicago, I believe, in 1956, and they talked about how close urban air mobility is and how close a flying carpet car would be, and that so many people are already thinking about how can we transport people by air just like in a car. And there's good reasons why this hasn't been on the market yet and why we're struggling with it. And some of those I'm going to address, and that's exactly what leads us into cargo drones. Let's look at another image here. This is a construction site, and it's a great example on how many tasks are easier from an aerial standpoint. If you take a look, there's no roads yet. There's applications for lifting. You see that big crane. Sometimes things need to be lifted, but it takes a lot of time to build up a crane. But also access of remote areas is a thing that is way easier from an aerial standpoint. Besides the construction site, there's other modes that you can imagine. Defense and security is one, all the way up to urban air mobility. All these applications are easier from the air, but so far have not been done with a helicopter. Why is that? Well, the main requirements are trifold, is what we see and what our customers see. It's about flight time, it's about payload, and it's about cost. So if I can manage to stay in the air for a long time, bring enough payload, and do that for free, that'd be the perfect product, right? So this is the combination that we're looking for, and this is the main criteria what our design, for example, was based on. Let's look again into existing applications, and I said in the beginning it's also about helicopters, and one mean of transport that can do those aerial missions is the helicopter. This is a R-22 Robinson helicopter. It's one of the most built helicopters in the world, very proven concept, and super reliable. So a great aircraft. Also, you can fly up to 3.5 hours, and with that flight time you can bring about 168 kilogram of payload. So if Daryl and myself would go flying, that's probably already a little above that. So we had to wear really light clothes. So it's a mean of transportation, but it's hard to work with this kind of application. And also, as we all know, helicopters are really expensive. Why are they expensive? Lots of mechanical parts that are really complex. So you have a machine that is expensive to operate, but however proven. On the other side of the scale, there is a large drone. And drones have not only been toys, but they've been used for the first applications to do business and to operate. This is in DJI mattress. This is kind of one of their top products in terms of payload. But still, we're not even close to the areas of a helicopter. However, it's really cheap to fly them. They're really broadly available. I can go into a grocery store and buy them, basically. But the question is there anything in between a helicopter and a drone? And our approach to that is the aircraft that we brought, that you're very welcome to visit. It's called the BH-6-350 multi-rotor VTOL aircraft. And the concept really is to bring the same missions that a helicopter can do at way lower costs. So we're talking about cost reduction if you take that R-22 of more than 40%. If you take a little larger helicopter that might do a similar mission, we're talking about even higher savings. But the principle is taken out of the drone world. Make it as easy as possible. Have a design that's really thoughtful. The 6 rotors do have a meaning. We want to have large rotors for efficiency, but at the same time, enough rotors to have redundancy. So if a rotor fails or a motor fails in this configurations, the other ones, the RPM will go up and you will still have a safe flight. But if you go too small and have too many, you lose efficiency, quite a lot of efficiency. I want to talk about applications, okay? So what does this drone do better than others, other vehicles, and where can we work with? And one application that I brought is agriculture. Already today, the drone market of agriculture is $1.2 billion US. Okay, so already farmers are used to work with drones, mainly to analyze fields from above, do video surveillance, save deer, for example, that's in the fields, and so they're used to that kind of application. However, aerial application, which you see right here, so crop dusting or spray aircraft, those are still aircraft. In the United States, there's like 3,200 spraying aircraft which are working today, but the fleet is very old. Most of the designs are out of the 60s and 70s, and they're longing to be replaced. And there are products, for example, from DJI, which do exactly that, but with really low payloads. Like they're talking about 15 liters of spray volume. And what our BH6 can do is it can carry 70 liters and fly for an hour. So that's a size where it gets interesting both for farmers and operators to have this kind of aircraft running all day long. You don't need a pilot. You don't need to have a teardrop approach to fly from one field to another. You can be working all day long. And that with the drone base, which is a highly automated aircraft. Another one would be transport and logistics. I think that's pretty self-speaking. We can again carry high payloads. We can also lift things up, which is good for the construction site example. And we deliver the platform, and our customers say, well, we need this and this kind of application. Can you tailor it to that mission? And here you can see, this is also something that you can see at our booth, is we have a little cargo box, for example, but that can be any size or shape, whatever the mission is. A third application is governmental service, or all the way down to defense and security. It can be a great platform for optics. To do surveillance missions, those optics that you usually see on helicopters. There's little reason why a helicopter needs the people who survey inside the helicopter. Like they might as well transmit the images down to your ground station and have that platform hovering for up to 3 hours, in our case, on a crash site or on a on an emergency site, for example. So now the fun part starts. We don't only make nice images, we also fly. And this is a video that I want to show you. It was out of our test flight program to prove that we are airborne today, that we can have really stable flights. It's taken at our home base where we do all the flight testings. And this is the aircraft. Again, 6-rotor layout. It is, unfortunately you cannot hear the sound, but it's quite impressive how silent it is. It's way quieter than a helicopter, and if you come to our booth, you'll see that now we have the ducted fans, which again brings down noise and increases efficiency. So what we do is automated flying here. We fly from one point to another on our testing field to see how does it behave accuracy-wise, how does it behave with the environment, with little winds, and how precise can we fly. Also, we've done engine failure tests, so we actually shut down one engine and saw how the other RPMs go up, and it remains stable flight and does an emergency descent and landing. And yeah, it's quite impressive to see the aircraft fly in real. And you're more than welcome to reach out. We try to fly as much as we can to gain more data. We've been flying actually since 2019, always improving the aircraft, and we'll go down that road. A couple of technical details. I don't want to get too much into detail. The question is, how can we deliver that combination of payload and range? Well, the secret is we don't rely on batteries, but on a hybrid drive. We did a lot of calculations. What is the best propulsion system, and what's the best energy source? And if you do the math, and that's well, pretty standard aerospace math on hovering flight, for example. If you want to do a hovering flight of about 1.5 hours to 2 hours, kind of a typical helicopter mission, with our aircraft, every single part would need to be built out of battery, like all the way up to the tip of the rotor would need to be battery, which is of course not feasible. So what we do is we have that little turbine generator, which is hooked up to, or the turbine is hooked up to a generator, creating electricity, which feeds into a small battery, and that battery feeds into the motors. So we have the easiness of 6 electric rotors, which is really nice because we don't have complex mechanics, and the range given by the range extender, which gives that combination of payload and range. We are a small group. We are only 6 people. It started basically in 2018, first flight 2019, and you've seen how close to a product state we've come so far. It's important to understand that we are a system integrator. So we don't make the electric motors ourselves. We buy them, and that's true for all the major components. We work with a lot of incumbent companies which are really talented in aerospace, and have them design or specialize their products to our application, and we will sell the UAS as B appliance. A quick sum up of the advantages. We have real performance, so you can fly for an hour with 71 kilos. That's something really important to understand. We also have the full data security. So when you buy an B aircraft, you will be using your own data, and it goes nowhere else. That's the promise of us. Technological leadership, we haven't really touched on the ducted fans too much, but it's quite hard to make the housing of a propeller really efficient. And in efficient, I mean that you have the what we call a shroud, or shroud is just another word for the ducted fan, but it's hard to make that efficient at the one time, giving you more thrust, and not adding too much weight that the weight eats away the extra thrust. So that's exactly the combination that we managed. Again, you're welcome to check it out in person. And we do offer this as a platform, and you as a user or the customer can specify what mission you want to do, and we're happy to help with whatever attachment is under there. Is that a camera system, highly sophisticated? Is that a box? Is that a spraying system? All of those can be realized. Where do we stand and what we're looking for? We are right in the test program. You've seen that. We have first revenues as a company. But also now, actually, that first one up there, installation of ducted fans, we're right in that. So those are installed. We've been flying with them, but now the testing goes on and on and on. And of course, we want to deliver a perfectly safe and stable aircraft to the customer. Next step is that installation of the gas turbine. And finally, the commercialization as a product. The step from a prototype to a product is quite hard to make, and that's where we need strong partners. We're looking for a new financing round to get that venture capital in. We are looking for strong partners who are ready to take that first step, who join us on that path with a feasible product and a feasible process and aircraft. This is our team. Again, some highly passionate people on aviation, experts from either aerospace or electronics, and business people. And we are happy to expand this team and again go down the route towards serious production. This having said, I want to give a big thank you to you. Please feel free to ask any questions. Feel free to visit us. You may gently touch the aircraft if you like, and we're happy to talk to you about drones, aviation, and everything that belongs to it. Thanks.
Right, so do we have any questions from the audience? Oh, there's a microphone up here, sir, if you just want to ask your question.
Thank you for a great presentation here. Who are your launch customers and what are quantified use cases for your aircraft?
Okay. So with launch customers, we are in the beginning of talks, or not at the beginning, but at a later stage of talks. So this is really the turning point, having this prototype as a product. And launch customers also, to be honest, are mainly outside of Germany, sometimes outside of Europe, because regulations, again, is a huge issue. So right now, it's still in the development phase. We have proven that this aircraft flies. We've shown that this is the feasible concept, and we need to make this step the step that you touched on, sir. What was the second question? Or was there a second question? Use cases. Yeah. Yes. So the aerial application is really interesting. What I showed, you can show that this is cheaper than having the incumbent version, which is either helicopters or spray planes. This is a main use case. Transport, for example, to offshore parks, wind parks is an issue. Usually you have a ship that needs to dock at different windmills, wind rotors, so that can save time wherever it saves time. That's a major use case. There's also energy suppliers is one, like the big companies that fly along the power lines with helicopters today. That can be automated, so we're in talk with those, and those will most likely be the first applications. Yes.
I would like to ask the difference between helicopter and your drone. Mm-hmm. For example, for firefighting, would you first do the drone or the helicopter? And another example, the Zugspitzebahn, for example, it was also delivered with helicopters. Better helicopters or better your drone?
Okay, so the first one, area of firefighting, is an interesting issue that you raised. I would claim, like the typical firefighting airplane has about somewhere between 5,000 and 10,000 liters of deterrent, and you will not cover this with our drone. Even in the swarm, it would just not make sense. So that application is something where we say, we can calculate, but we will not get the fire out with that. But for example, if you take California, there's teams of firefighters that actually get deployed with parachutes into the hot zones. So they would parachute in and get the fire out as a ground team. And that is one of the most dangerous jobs in the United States. And usually they run out of equipment. Either the fire gets on there and they need to protect, or they run out of digging equipment. And that could be a solution where B picks up tools, picks up water even, or whatever they need, fly through the smoke, again, better than the aircraft they use right now. They have to have visual contact and get deployed right where the team is and give them the goods that they need to fight that fire. So that would be an application for firefighting. Yes, and go up the Zugspitzbahn was the other one. Yes, I mean the transport to remote areas, remote locations with goods, with food, where you need, sometimes you need the helicopter today, but usually then the runner or the owner of the hut would say, the helicopter is too expensive. You know, I rather send up 5 or 6 people who bring up goods in their backpacks and down garbage. And but if I could do it for half the cost, I do it right away. So that's another great example.
Right. So one last question.
You did not comment your last picture. Is that a vision or is it a dream? But I can tell you, I've seen it, I think, from the Vertical Takeoff Society in America. There's already a kind of recreational personal drone, 2-seater.
Yeah. So I strongly believe that we will see transport drones before we see personal aerial vehicles like the one that I showed. Again, that we want to be safe all the time. The picture that I showed is just to stress that with the aircraft that we have, if we increase size by 30%, we have 200 kilos of payload, and then it doesn't matter, do we put a box underneath or a cabin that holds the two of us?
Well, one and a bit of me.
And that's what will be easy. But going the other way, like having that air taxi first and then going down, I'm not sure. So that was just to touch on what can be next and more of a futuristic vision. The more feasible, the more safe eventually version is transport drones, cargo drones.
Yeah, I'm fully expecting somebody to put themselves in a box and ship themselves via a cargo drone in the near future. I think an Australian did it decades ago, trying to get from Australia back to the UK. Spent 2 days upside down in the box, I think at KL, yeah. Anyway, crazy thing, crazy people. BV loss, so you're working on that as well. You've seen the news recently that BV loss for bridge inspections has been approved in the US by the FAA. Is that on your pathway?
So to operate an aircraft like this efficiently, you have to go BV loss.
Yeah.
For sure.
Yeah, absolutely.
Yeah.
Okay, right. That's brilliant. Thank you very much, sir.
Thanks.
Thank you. Right, just before you grab the podium, sir, I'm going to... Part of our COVID precautions. Right, so right now, sorry, a bit of housekeeping whilst I'm doing this. We have Torsten Wellweber from Apsis, and I had a quick chat with him about the system that they're doing. So we're actually moving into the digital world right now. And he's going to take us through what they're doing to help ensure the safe operation of these vehicles and systems and processes as we're going forward. So over to you, sir.
So thank you, Darren. Holistic security architecture for future mobility. So this is a quick roundup of all the things that were not mentioned in all the quite fascinating topics until now. So let me see. Future mobility, and I will not repeat all the buzzwords, and they will certainly shape the future of what we will use as mobility. But they all have things in common, you know, connected mobility, artificial intelligence, smart infrastructure, automated assembly, and even additive manufacturing. That is all at the bottom line software-based. And wherever you have software and communication, there is this intrinsic feature that you can change things. And changing things in an unintended way is usually a security problem. So what this means is you have things to look out for throughout all your life cycle of your system, your equipment, your platform, whatever you want to look at. And when we now look at future mobility in terms of cybersecurity challenges, everything that I scrambled onto this slide is, in the end, an issue that could lead to severe business impacts in the end. Now, just a few high-level examples to give in terms of what could actually happen, what could you be facing if you are in a security situation. The most obvious, of course, is your good old vehicle and passenger safety. If you're looking at drones, at automated, autonomous vehicles, be ground-based or flying or whatever, you could have some issues of manufacturing integrity if we use 3D printing of whatever form. You're basically going directly from digital, well, CAD design to computer-aided manufacturing. And if you purely rely on, well, this is my engineering PC and it's sending data to my 3D printer, there may be man-in-the-middle attacks that manipulate the data, and what comes out of your printer is not what you actually designed on your PC. Legal liabilities for your autonomous, smart, future mobility concept, you will have passenger data moving around all your networks. If you are unlucky, like British Airways was a couple of years ago, you will be fined some, was it 300 or 400 million pounds, which is quite some business impact. And infrastructure availability, now that we rely for the smart traffic management, again, be that in the air or on ground, on algorithms and software and data being collected. Even today, there are, let's say, security analysts who will show by means of, there was one story from a guy in Berlin who put, I think it was some dozens of smartphones in a carry-on trolley and walked down one of the bigger streets. And they all had Google Maps activated on them. And because he was walking, moving so slowly, it appeared as a traffic jam on Google Maps, which would then lead to, you know, diverting other people in their cars using the same service. Just as some examples of that. Now, some more examples, because this actually happened. It was not it was not on mobility as such, but all these cyber attacks happened on non-IT systems. So number one, Maersk, the shipping company, they were faced with a collateral damage due to some cyber attack happening or taking place on some nation. In the course of that, they lost $300 million worth of business. In between, they did not know where any of their containers, any of their cargo actually was, and what to do with those ships coming into port and so on. Triton was quite interesting because nobody really thought of that before. Someone was tampering with the safety shutdown system of some petrochemical plants. Luckily, it was discovered because some controllers crashed. Well, they had a computer breakdown, basically, and nobody could make sense of that until it was they analyzed that in forensics and all that. And the outcome was that someone tried to manipulate the safety shutdown system of these plants in order to probably cause a severe impact, first of all, plus disabling the safety function of everything. So we would have a huge literal blow in some of these plants if it was not due to malfunctioning malware prohibited this from actually being effective. Mirai, again, smart and future mobility, Internet of Things. Mirai was or more or less still is, a so-called botnet, where software weaknesses in the firmware, in the software of your webcam and other appliances was exploited to put on malware that was then turned into a so-called botnet to be cybercrime as a service. You could rent that service and it was actually rented out to do some denial of service, large-scale attacks on certain servers to take them down. And to make the link to future mobility, if we have a increase in monitoring, in sensor nodes, all that, what will be necessary in the future, we have to address the security of these devices to make sure that they will not be taken over by any adversaries. Now, why would anyone do that? Let me go through the list of questions, so to say, if we look at the layman's first questions to that. So we could have rampaging malware, script kiddies, malicious competitors to your whatever business, some cyber thug making money off your service being available. You could have militant activists. Extinction Rebellion does not specifically completely exclude any violence to things to get to their goals. And of course, you can have nation-state actors. As some forensics points to, the Maersk incident was collateral damage from an attack on the nation of Ukraine. Now, why should anyone want to do that? Maybe they just didn't intend to actually harm you in this way. Script kiddies, because they can. We've been teenagers one time in our life, right? We did stupid stuff. And there are teenagers out there as well, and they have, some of them have computer skills. Cyber thugs, malicious competitors, and so on, because they just because they want to. And it could even be a nation-state actor. North Korea is generating revenue for them by doing cybercrime. And in the end, cyber attacks may impact, again, your data, your software, a function being built out of that, and they will lead to what we call threat conditions, similar to in safety failure conditions, which then will have impacts on your assets. Now, the way to approach that is right backwards to this. And we've been using this methodology. It's UK ED 203 based. So if you want to look that up, it's well defined. We go through the impacts, impact metrics. We look at the threat conditions. So what impact could you have on your assets? And what level of impact will this have? We will analyze the attack vectors. So any security attack, any cyber attack takes at least one actor, one attacker, to enter your data system, your communication system at one entry point, and he will follow a possible way of communication towards a target that then will be compromised in some way. All that together will be countered by security measures. So the simple, firewall, your antivirus software, and so on. And you should have something similar, even if you're not talking about a PC, but your drone control node, or your managing software for your autonomous flight management. And all that together will build threat scenarios, which you can then analyze in actually analyze in different ways to determine the level of risk. First of all, the level of likelihood of such an attack being successful, and in the end of the risk that then pretty much relates to your plain old risk assessment that you would do on your business risks and similar. Now, for large commercial aircraft security risk assessments, we first of all looked at the safety as given in CS25, airworthiness, flight safety, and so on. Today, we have extended that again for commercial aircraft to operational impacts as well. There are airlines operating the aircraft, and there are more reasons not to take off than just the safety of the flight and passengers. You also might want to look at liability topics, or even your reputation if you care. And it might not be good to have been hacked and to be required to announce that you had a major security breach and all your customer data is now up for sale on the darknet. And even environment will be a stake for that, as with the advance of smart city, smart buildings, you will have the idea of optimizing your environmental footprint. And if the data that you're relying on is tampered with, your heating system might run wild while it doesn't have to. So there will be a need for complex threat scenarios in addition to that, where you will probably face some scenarios based on advanced persistent threats, so basically a chain of hacks taking place that will not be simple scenarios where you go, okay, there could be a hacker, he will enter my web server and that's it, and then display some funny web page on that. But he might compromise your Office PC, and from the Office PC move on to the manufacturing firewall system, and from there continue on to your automation systems, and on and on and on. So for future mobility, again, to close the loop, the same approach should be taken to make sure that no cross-functional dependencies will be forgotten in these cyber scenarios. This is basically the V-cycle of requirements-based engineering. So no big deal. You have the design phase, you have your test part. I've added the in-service, which usually, in requirements-based engineering is a little bit, so you sell your good and then off you go. Because we're looking at things with software in them, you should take care of the in-service part of the life as well. At the same time, again, looking at the mobility sector, this does not necessarily only apply to one aircraft functional systems and equipment building up all this, but this would be the infrastructure, some system, some service using that infrastructure, some vehicles being the service, so it scales up to whatever you like. And they will be designed, they will hopefully be tested, of course, and they will certainly be in service. And in service life for software is just like you do on your PC, on your smartphone. You have to make sure that newly discovered software vulnerabilities are not able to, cannot be exploited. Because if they can, there are just open doors to your device. And if your device is a taxi drone, then I don't want to be in there if I must fear that some third party is actually controlling that. And maybe combined with the passenger data that he might be able then also to retrieve, know that, oh, now it's this Mr. Wollweber, or maybe it's this Mr. Trump using that. And now I could, divert this to this other helipad and just take him hostage. And nobody can do anything about that. And now this is a stupid example because, who wouldn't? But then, okay. So one more aspect to this, and this, wait, wrong picture, to give you another hint on how complex this might be. So this is a bad old picture taken from our training slides, but I guess that's quite obvious. You have an aircraft, a lot of functions, a lot of systems. The functions you will just break down, your functional breakdown approach for engineering, for safety, or for all that. The thing is, in security, the functions are fine, but a cyber attack is always, has to be directed at some piece of hardware. Even if you think, well, okay, I could manipulate the data on the wire, well, actually you're manipulating it either at the receiver side or most likely on the memory on the processor. So what we need is a functional to equipment breakdown or translation, and you have to make sure that you properly get that and you have it completely solved, to really be able to address the impacts, which will be your business impacts in the end, and relate those to the equipment that is taking part in this function. Again, as I said before, in the V cycle, you have to look at infrastructure, to platform, to the user, to the vehicle or equipment. And for every party in this global subject, there will be defined dedicated areas of security need. But still you have to look at the big picture as well. And there might be situations where you can relieve the need for extra security on a specific part of your vehicle, because it will be covered, the security of the function will be covered by some other system. like when we discussed, well, when we were presented with the additive manufacturing of the Airbus parts, they are one by one monitored by CT. Okay, so this seems to be good enough as a security measure, from a security point of view, as a measure to ensure that I cannot manipulate the manufacturing data in between. Otherwise, I could, change the size of the shaft or make them hollow or whatever other. And if you don't double check afterwards, then they might be prone to just break once they're used. And this modular and scalable assessment way of working in security is certainly necessary for the future mobility in all aspects of them. So that's it. Thank you.
That's brilliant. Thank you very much. You are here on the, you're at the show. You're just down. What stand number are you?
Wherever it says Apsis.
Right, they're just up over there. I know that we're at the end of our session now. We're going into our break. Is there any burning questions that anybody has in the application of this? Right, okay. So if you have any other questions, I would suggest that you head over to Apsis, and their stand is just over there. We've had a really interesting chat earlier. My question is going to be, do you think that the electric aviation industry is taking this seriously enough, and are they going to have the right protection in place in time by the time it starts rolling out in a couple of years? Right, pregnant pause.
There's still chance to get it right, for sure.
We're doomed.
It's on the other hand, I'm not so sure because we're moving fast on a new fascinating business, and there is so much that you can achieve by means of the B drone just shows that. Why don't we just upscale your little DJI toys, but for serious business? And why don't we think about that and take it to the next level and even extend the range and usage and all that? Now, cybersecurity is always, tends to be late in the process. So yes, it can be done, and yes, it will certainly be addressed by a lot of the actors. But then again, I like to raise the point every time to see, well, did you do your homework already, or do you want us to support you?
Yeah. Okay, with that, we'll end the session. So thank you very much, sir. Right, so we're going to be coming back at 4 o'clock, I believe, so 1600. So we've got about 20 minutes. There's coffee at the back. Feel free to wander around and go visit Apsis, B, and the other exhibitors which are here. Thank you. Brilliant. Thank you very much.
Okay, I'm there. Okay, so you have. So please tell me when to start. Can you hear me? Okay, so I'm online, I can go, yeah, correct? Okay, so hello to the audience. My name is Joseph Kallo. I'm from the DLR, and at the same time, I'm talking also for the University of Ulm. And we have some contributions on our work also from other partners from the outside. So I will just start my presentation. Hopefully it will work now. So sorry for the inconvenience. Can you see my screen and the slides are going through? Okay, so at the Aerospace Center Research and Space Agency of the Federal Republic of Germany, DLR, we have two groups. We have a group in Stuttgart and one in Hamburg. And I will tell you today some work about our fuel cell and battery systems work for more electric and all electric aircraft. And also out of this DLR, we had the startup company H2Fly, which is called Hydrogen to Fly. Also, I'm in charge of the University of Ulm Institute of Energy Conversion and Storage, where we look in a special way to electrical machines and power distribution also for aircraft applications. So first of all, I would like just to give you an overview. Our main work, so there are a lot of possibilities to put hydrogen, but also new fuels and also electric hybrid propulsion into aviation. But our work focuses on the hydrogen usage with fuel cells, fuel systems, with the hybrid or without. That's a possibility today also to go without, and then by using an electric motor to fly around, just to give you an overview. Why are we doing this? What we see is that if we take those aircraft classes like the A320, 737s, and so on, so let's say the regional and the medium aircraft class, which takes a big part of the aircraft application today. What is that if we have a plane which can go around about 2,000 kilometers, we could cover a lot of that transport, and also we could save a lot of those emissions if we can go emission-free. But to make a difference, this is my first statement, we have to start thinking big. At the moment, in the hydrogen fuel cell world, we're thinking in a couple of hundreds of kilowatts, and that is, from my perspective, too small. So to cope with these requirements here, we definitely have to think about going to the megawatt level. So what is our vision? Our combined vision from all these institutes is to go with the general aviation. I think we definitely can go from this perspective with 7-seater, 6-seater, 10-seater with that technology. A big challenge would be to go into like a 4-seater, but also we have a chance to deliver propulsion systems, VTOL applications, going there from, let's say, 20 minutes with batteries to something like 1 hour 15 with the fuel cell hydrogen application. Other applications are also there, but not relevant for the mass. The history of our emission-free aviation at the DLR and at the University of Ulm started in 2007. Since there, we finished a lot of projects. Our newest project, which is the HY4, the 4-seater hydrogen fuel cell aircraft, is a platform to test technology. It's not a product. It will not go and will be built in a couple of airplanes, will be just one. But the important thing about this is it enables us the possibility not only to work on the technology, but also it implies that we have to deal with the permit to fly and with the qualification base. Based on that, we have to look at the background. We definitely have a new architecture which we need for the systems. So going from like taxi, takeoff, and then departure, going to cruise, we have to take care about low pressure, low partial pressure for the oxygen. And then we have also to take care about the mission and the whole mission time, not only for, let's say, the on-ground application. Mainly for cruise, we need new architectures for the air supply. What you see here, and hopefully you see a good, so you can see the video. We have the HY4, which took first flight in 2016. And since 2016, so at that campaign, we had 32 takeoff and landings. And we used hydrogen from the fuel cell to propel the aircraft. Important here was also to understand the operations. So we had a chance also to refuel the hydrogen system in a couple of minutes and then go flying again. That was also important. And it was also important to understand with all the partners. We had Pipistrel Vertical Solutions, we had the University H2Fly and the DLR, how to bring the next step into the technology. And our next step in the technology is not only a functionality, so much more important was to take a very close look on the processes, so on the procedures to develop such powertrains. And based on those procedures, we started to rethink the system. So the 6th generation, which is now implemented since 2016 into the HY4, is a fully redundant hydrogen electric powertrain. And we are not talking about only the integration architecture, which was done by H2Fly, implements the hydrogen storage system, which is redundant, the fuel cell system, which are redundant, then the power module control device, which enables a very high redundancy on the energy distribution side. We have a backup battery, which in the future will not be used anymore. And then we have a redundant inverter architecture for a double motor architecture. The propeller, there is just one shaft and one propeller, but we have 2 by 3 phases independent motors. Also important is our cooperation with Diehl Aerospace. In some projects, we had a chance to implement the Diehl IMA, which is now the version 1.0. And the new implemented Diehl IMA will then be refurbished to a 2.0. Will then to take the overall control of the complete powertrain. We are not talking just about controlling one fuel cell or one power distribution module. We are talking about how to implement a redundant Del-A control unit for the powertrain in total. This just 6th generation is now implemented. So we had a lot of homework on the fuel cell systems, on the integration, on the storage, but also on the cooling and on the thermal management system. Then a lot of integration on the safety side, developing new sensors, implementing new sensors, and also understanding the controls on the very basic level. And then we have this new 6th generation, which is now implemented into the new HY4. And hopefully you can see the new video. This is tape from yesterday. So we have the new generation functional. It's completely design freezed. And we are driving on ground, hoping for the next couple of days to get the EASA permit to fly. In this case, we will start then flying around and testing. The next steps which we will do is with our partner from Air Liquide and the EU Project 7, we will go and implement the first liquid hydrogen storage system into an aircraft. This storage system will have roughly something around 20 kilograms. This technology at the moment is just, let's say, the 20 kilograms, it could be bigger, but for us, this is completely enough to do the testing. But much more important, to build a qualification base for such hydrogen storage systems. So just to give you also an impression where our perspective is the edge of the visibility for the storage. We know some divars from the early 70s into the 80s. From the US. There they had a chance to store roughly 1.5 tons of hydrogen with something like usable electrical efficiency at 50% efficiency of 26 megawatt hours. So we definitely have to look to bigger systems. We have to look to much improved systems and also to integration. Based on this, at the H2Fly, which is the partner which takes care about the system architecture and the integration and the implementation of the whole system, powertrain system. We started with the processes which are needed for such development. Then we definitely have to look at those SAA working groups and all those new working groups arising now in fuel cell safety and also for qualification basis. But also what we have to do is to elaborate sensors which can be implemented into the aircraft, then build hardware and software which is redundant and also works on Del A systems. So at the end, we can improve the safety of the whole system. On the hardware side, we have to take care about the component redevelopment, balance of plant redevelopment, and also, which is very, very important, on the testing side. And last but not least, we definitely have to take care about the operations of the hydrogen on ground and in the plane, so we have a safe handling. After that, we have to go there and think about how to implement all those things in a second generation into a bigger airplane to get an efficient airplane architecture. Feasible from our perspective, just to give you an impression, from our perspective, and this is very, very simple, it's not aerodynamically optimized, it's just to understand where to put the volumes and the weights. An early study from 2017, and what we have seen there, and this is important, we have seen that the range of the electric powertrain, if we go with a battery in this complex system, we can go a couple of hundreds of kilometers, maybe. A maximum of something like 170 came out in this concept. When we go with pressurized hydrogen, we can reach something like 900 kilometers range. When we go with the liquid hydrogen fuel cell, we can reach something like 1,700 kilometers. We have the comparison with a gasoline hybrid, with a diesel hybrid, and so on. So in this case, we have to be fair and say emission-free will cost us range. So my colleague from Braunschweig made an early study on a 328 with efficiency optimized wings. And what we have seen there is that if we put the full payload and we have energy density in the full system, tank plus fuel cell plus electric motors of 1,200 watt hours per kilogram. And we are far away from those 180, respectively 120, if you take also the motor when you go with a battery. There is a chance with a liquid hydrogen system to go something between 1,500 and 2,000 kilometers. If we have this newly redeveloped storage systems, which Air Liquide, as an example, has already now in the space application, we can also dream about the 2,600 watt hours per kilogram. But this is a vision, so please take it at the moment. Feasible today is definitely the 1,200 watt hours per kilogram. So based on that and based on the work of our colleagues from the University of Stuttgart, we redeveloped also a very simple system just to get an impression what are the energy density data and what is the range. And what we can say is that we can take a 40-seater and go depending on the storage system which we have around 2,000 kilometers. If we take out a lot of volume for the storage and put passengers instead, we can say that we can go 55 passenger at 1,000 kilometer today with today's technology. So if we want to go bigger, we definitely have to develop the systems, the upscale the systems into the next level, going to very high voltages and also high currents, but also to redesign the planes. So that would be a vision. To summarize from our perspective, I would say 40, maybe even 70 passenger is feasible from today's perspective with today's technology. Then we definitely have to take a very close look to the upscaling of the technology from hundreds of kilowatt to multiple megawatt scale. That is a really big challenge, but that is feasible from a technological perspective. And then we have to focus on the BOP, balance of plant customization, for the fuel cell, the hydrogen, and so on, to get an overview how expensive the completely refurbishing of systems for the qualification base would be. And based on that, we need new homologation and qualification requirements. And from there, we definitely have a chance to go into the application. So with at the end of the presentation.
That's fantastic. Thank you very much, Professor Callow.
Are there questions?
Yeah, definitely. So you're really pushing the hydrogen element of aviation, and some of those numbers look really interesting to me. 55 passengers, 1,000 kilometers. That's in a right sweet spot, I think, for sub-regional aviation. I'm very interested in that. What do you think the timelines are for developing that technology?
So from our perspective, we have to say we go into air taxi application, and there we can go with, let's say, a 4-seater VTOL around 1 hour 15. Then if we go to general aviation, we can go to 6-seater, 10-seater, and we can go to something like 1,500 kilometers. If we go to the 40-seater, roughly 1,500 kilometers also, then we have to take in account, I would say, the air taxi application, eVTOL, is feasible with the right amount of money, but it will take the time for balance of plant and the qualification base. And 2026, I would say it's a realistic number to go into a first prototype which can be certified.
So 2026.
Then, yes.
Right.
From our, let's say, technological point of view.
Right.
And
okay.
With the general aviation, fixed wing, I would say we have a chance to go into something like 2025 for a 6-seater. And for the 40-seater, I would say with all those CS25 requirements and the upscaling on the 1.5 megawatt at least, we need 2030, 2032 to go into a really good certifiable plane. I'm not talking about demo. I think demos, you can go into demonstration of, let's say, non-permit to flying object in the air taxi in like 2.5 years from now into a fixed wing. We can demonstrate that next year with a round amount of money in the, let's say, just doubling the HY4. That's, let's say, with the right amount of money feasible. And for the 40-seater, it will take for the demonstration from our perspective at least 6 years. Okay. So please differentiate between demos and really a system which can go into certification.
Right. Okay. But you believe that there is the pathway to get us there to commercial operation. So I think that's a really interesting thing. What about the hydrogen infrastructure to support that? Do you think that countries are doing enough to deliver hydrogen for these types of aircraft?
So when I'm looking at the numbers for the infrastructure for the road application, and we have some numbers going around in Germany, if we would put the whole car application from gasoline to hydrogen, it will take something between 2.5 and 5 billions in infrastructure. Just to give you an impression, Germany is paying every year 100 billion euros for buying fuel from outside, just to give you a perspective. And it will take, for those 5 billions, it will take roughly 5 to 7 years to put that infrastructure in place. So taking in account that we would need maybe 300 to 400 refueling station, even taking in a small airfields, so a big part of the small airfields, our calculation showed we would need something in the region of, let's say, a 3/4 of a billion, it's like 700 million euros, to completely fill up the hydrogen infrastructure for the refueling stations for the airports. So that is not a big number from our perspective, but it has to be a business case. And at the moment, we do not have the business case with this. So it has to be taken in account, but it has to be looked at from an economic perspective also.
Yeah, so which came first, the chicken or the egg?
Yeah.
We're definitely into that case. So is there any questions from the audience? We started a little bit late, but of communications challenges. Any questions for Professor Callow? No. Okay. Professor Callow, thank you very much. I always enjoy listening to your presentations. I always learn something. Definitely some numbers are sticking in my head on that, and I'll be sure to reach out to you because I have a lot more questions. Right, so for Professor Callow, thank you very much. Right, so sorry, I'm going to try and get us back on time. Technical University Munich, Professor Florian. There he is, right, brilliant. I'll hand over to you, sir. We didn't have a chance really to speak earlier. I'll let you take it away. Thank you.
So, welcome ladies and gentlemen, and thank you for giving me the opportunity to give a short presentation here. We were struggling to get my laptop connected, which unfortunately didn't work, so now we only have a PDF of the presentation, so I have to skip my videos. But nevertheless, over the next 15 minutes, I want to give you an overview over some selected challenges related to manned electric VTOL airplanes, because everybody's talking about air taxis, and I just want to address some of the relevant issues there. So basically, the remote control should just work with next, right? Yeah. So as a quick justification why my institute is working on the topic, for me it's very important that we are not doing only fundamental research, but that we are really applied and that we are actively assisting product development in this area. And so the eVTOLs just make sense for us because over the recent years, we did a lot of things on manned fixed-wing airplanes. We collected experience with multicopters, but in countries outside Europe, we also collected experience in the certification domain. And so basically the step towards transition type unmanned systems was a very natural one. And if you then combine the manned and certification activities with the unmanned transition type vehicles, then the next logical step would be basically manned eVTOL airplanes. And so to set the stage, Europe was quite fast in establishing certification requirements for these manned eVTOL vehicles. It's very important that we are always talking about piloted vehicles, so it's not about autonomy, but the trade-off or the penalty for Europe being fast is that Europe set the safety requirements really, really high. And so basically it placed a big market entry barrier, especially if you want to go for commercial operations. And currently, below the official rulemaking, there's of course a lot of working groups within ASTM or EuroCAE, which are preparing draft standards and also acceptable means of compliance for different existing rulemaking drafts. And my institute is very actively joining these groups to provide inputs there. So that was just two slides as justification why basically I'm talking about the manned eVTOL stuff. And so the scope of this short presentation will address the flight control system, so basically not the general vehicle concept. And I want to focus on aspects which are very specific to these eVTOL planes. So basically, I will not address everything that is taken from classical certification, not because it would not be relevant, but just I want to focus on the novel aspects. And so basically, the contribution I want to make is that we say, okay, now we have to do a lot of things for which there is no traditional learning curve, because it's a new type of vehicles, and how can you guarantee certain safety characteristics for these new types of vehicle where basically no long-standing experience could be collected over the last couple of years. Then another thing would be the so-called simplified vehicle operations. So basically, I don't think that manned systems will fly fully automated without an operator on board over the next years. However, there's something between no operator and a fully certified pilot. And especially in the United States, the rulemaking for this SVO, simplified vehicle operations, has already begun. And so we are also contributing to draft standards there. And then, of course, the most important aspect is safety, and I would like to address some approaches to safety assurance. In this very short presentation, I mainly focus on what you do during development, but there's also advanced things on the flying vehicle, like, for example, runtime assurance, online monitoring, and things like that. So as I really had to cut down the time for the presentation, I only show some things which I consider as very relevant, because now there's a wealth of new projects all around the world in this eVTOL domain. And a very typical thing, what people are doing is that they build small subscale models and they fly their subscale models. And then you say, look, it's working on a 20, 30, 50 kilogram prototype vehicle, so now let's build the big one. And I have more than 20 slides. I show only one of them just on the topic why transferring knowledge from small vehicles to large vehicles is not valid. And this would, for example, be the cyclic load in the rotor hub of a rigid rotor when it's subject to slipstreams during transition from powered lift flight to wing-borne flight. And there you see, if we compare a small drone, a 40 kilogram drone, and a 600 kilogram eVTOL, that basically the root bending moment, which is a cyclic load at every RPM, would scale with a factor of 250,000, which is definitely not linear, but which is to the fifth power basically in the end. And so if you don't account for these things right in the beginning, then you will be stopped by some bad surprises. And from internal talks to other people in other companies, I know that they have been experiencing these bad surprises. So just if you look at these moments, bear in mind that the maximum torque of the gear of a small car, like a small Volkswagen Golf or something like this, is 250 Newton meters. So you see, you really have significant alternating bending moments in the rotor hub. There's a lot of other aspects, and so you have to take care of unsteady effects. You have to take care of the interaction between basically the lifting propellers and the frame of your vehicle, because typically you have these types of lifting bars and other elements which of course lead not only to efficiency losses. In the beginning, I think the efficiency is not the big point, but it also leads to safety relevant aspects like vibrations, like noise and so on. So noise in terms of stimulating sensors, which can have some safety impacts. One other thing is, many people do their configuration for the nominal case. However, if you really want to build a manned aircraft, it's very important that you take care that also in failure situations, the airplane will be continue to fly safely. And therefore, basically, when we do our vehicle design, we make sure that if you fail every single propeller, that the system is not only trimmable, but that the remaining maneuverability envelope is still complying with what you get from current handling qualities requirements. And for the handling qualities requirements in wing-borne flight, we take the military handling qualities requirements, which you typically take for fixed-wing airplanes. In hover, we take the ADS-33, which has been established for helicopters. Here, for example, the red volume would be the maneuverability zone, what you can achieve from a standstill to a standstill within 3 seconds if all engines are running. And the volume you see inside is the intersection of what remains with a single engine failed. And if other people, I've seen this very often, try to make the design, then basically they account for the fact that the system must still be trimmable if an arbitrary engine is failed, but don't account for the remaining maneuverability requirements. Like here, for example, there would be 2 examples from the ADS-33, which is valid for helicopters. And so you have one requirement when it's about heading change and hover, and another requirement which is the response in the vertical channel, where basically it's about proving that even if you have failures with your system, if an arbitrary engine fails, then depending on the probability of this failure, you must ensure that you still satisfy level 2 handling qualities in order to later have a system that should have a perspective for getting a type certification with a qualified pilot on board. The next thing I briefly want to address is that in this new domain, we have a lot of uncertainties. And so this means that all the modeling we have to do and all the analysis we need to do needs to move away from classical deterministic methods to probabilistic methods. So in the end, basically, in the beginning, you have very high uncertainties which are given by probability density functions for your different contributing parameters. And then basically, if you have target requirements, you want to be able to state probabilities at which a certain requirement is violated. And so by that, you can stay in a very safe sub-envelope for the first flight, and when during a flight you collect more and more data, and by parameter estimation you're improving the validity of your model, your statements get less and less conservative, and by that you slowly can expand the envelope. But instead of doing trial and error, you in a very proactive manner can manage basically the safety of your flight testing and then also later of your operation. The only important thing is that you should be rather conservative when it comes then to the spread of the data in your initial modeling. And so basically this stochastic propagation of characteristics is something which is quite new because it requires very high computational power, and so we invested a lot of things in the last years to make these algorithms very efficient, so you can also make statements for remote probabilities like 10 to the minus 7, 10 to the minus 8, where you could not start with, for example, classic Monte Carlo procedures. And so basically the big takeaway of what I had on the first couple of slides is that number one, testing on small drones is valuable, but not really representative. So you use the results from the small systems rather to verify and validate the prediction capability of your tools, and then you apply those tools to the larger vehicles because the things really scale in a nonlinear manner. Then the other thing is a lot of transient and nonlinear effects which you may neglect for small systems, you cannot neglect for the large systems. And it's not only the one engine in operative case, but it's very important that right from the beginning you make sure that you design your system with all failure cases in mind. If you try to do this later on, then you have to start right from the scratch. The second aspect I simply and quickly want to address is the simplified vehicle operation, which is an operation concept where basically the qualification of the operator can be reduced from somebody coming with a classical pilot's license, because all those systems are full fly-by-wire systems anyway, and there's no mechanical reversion. Of course, you try to provide basic operating functions which have a lower operator workload and are easier to fly. And at this point, basically, we're using two side sticks. The right side stick basically is behaving similar to a normal aircraft. However, you command high-level commands. Pulling and pushing directly commands a sink rate or a descent or a climb rate. So when you release the stick, you maintain the altitude. Moving the stick left or right is commanding a side acceleration free turn rate, which leads to a coordinated bank to turn behavior in forward flight and basically to rotating on the position in hover. Whereas the left stick in hover is commanding a ground speed, where basically you can shift your position over the ground, and if you advance the left stick forward, then you will hit a notch. You need to press a button to overcome the notch, and then the system transitions. And in that range, basically, once the system is transitioned, then you have something like an airspeed command system. So basically, I just, to keep my timing collected, the next 3 slides into this single slide. So basically, so far we had a lot of people fly in the simulator, a lot of politicians also, and you see that people are very quick to learn to operate the system, and so there's a true perspective to reduce the amount of required flight training. On the other hand side, of course, you also need a professional assessment. And so the question is, how do you assess the handling qualities of such a vehicle? And there we took something which has been done in the military helicopter domain for a long time. We were adopting the so-called mission task elements. And so the funny thing is that independent of us, FAA had the same idea, and we were very happy that, for example, the FAA chief test pilot for the Part 23 domain, who's also responsible for eVTOLs, was flying the simulator in our lab and confirmed that basically the strategy which we are moving is very consistent to what, at least in the United States, is seen as a very viable way of certifying the handling qualities of such vehicles. And of course, the evaluation of these tasks is both automated and, on the other side, basically manual when it comes to the subjective feedback by the pilots. How many minutes do I have left? Because as I start, -9, so how much do you give me? Because I just wonder. So then I just get 3 minutes, so I'm catching up for Mr. Callow. Thank you, Mr. Callow, no worries. The next beer is on you. And so basically, we developed a lot of tools which are helping in safety analysis, in finding out weak spots in designs by doing active optimization to violate requirements, which of course is very helpful if at a very early stage in development you want to find out where do you have weaknesses in your design you're not aware of. And basically we do a lot of things in terms of stability and robustness analysis, especially when it comes to systems with high uncertainties and these probabilistic statements. So basically then I just skip all these slides. The very important statement is also how can you make valid statements for failure probabilities in the range 10 to the -7, 10 to the -9, where normal Monte Carlo methods would fail, where we also have a valid method. As a final statement, basically, my institute is also contributing a lot to production systems. We do a lot of flight testing, and so basically the video I would have liked to show you would have been the full transition of a 300-kilogram eVTOL vehicle, because I know in Germany nobody did this transition so far, and so I was happy to share the video. Now you see a still photo, so you don't have to believe it, which is good, because then we keep on flying under the radar, so to say. But in the end, I think this eVTOL domain is something with a big potential in the future, and it's a big opportunity. And I think if you address the stuff not too emotionally, but with a very technical rational, and if you don't try to trick or cheat with Newton, but respect physics, the disruptive inputs from other technology domains allows us to do a lot of things in the near future which have not been there before. And so I hope that under different conditions, with more people and without face masks, maybe in a year or two, we can show you nice flying videos. So I thank you, and I hope I helped catching up at least some minutes. Yeah, that's it. Thank you very much.
That's a master class in actually how you do that. Amazing. Are you sticking around for the rest of the show? Are you guys on a stand here?
So I will stay for the rest of the session now.
Okay.
And so basically, I'm happy to talk under compliance with the current special rules.
Right. Okay. Does anybody have any burning questions? Obviously, it's a very technical subject. But as he said, he's going to stick around for the rest of the show. So maybe that, or your email address, was that on your presentation? I'm sure. Or
so basically, yeah, but as the presentation is gone, people don't remember. So if you look in the program, it's first name dot last name at tum.de, and we put some posters there. We wanted to have a stand with people, a populated one, but as one in my team indeed caught corona, no fears, I got tested.
Right.
We decided, as we're not allowed to work, that we don't put people here at the stand, because that would have been a bit crazy.
Yeah.
If basically we're not going into the office, but then run around with many people here.
Oh, that's brilliant. Thank you very much, sir.
I'm safe, I'm negative. I got it yesterday, right. So no worries.
Okay, that's brilliant. Thank you very much. Okay, so we're going to go on to Autosar, and it's Günther Rickert. Are you here, sir? There we are. We had a brief chance to talk a little bit earlier about what he's doing and the way that they're going to be incorporating their technology into this new class of vehicle. So I'll pass it right over to you, sir, and away you go.
Yeah, thank you very much, and welcome. We are automotive guys, and you might ask yourself, why are we here? Do the automotive guys plan to enter the third dimension? No, that's not true. What intrigued us to come was the issue of future mobility, since we are convinced that the car cannot be longer seen as an isolated box in which people are driving around. We have to see that we have to interconnect to many other information sources, data sources, for instance, traffic control centers in futures. But once, for instance, you want to organize a transport chain, you have to connect to other modes of transport, you have to find parking places, you have to book something, you have to pay features, and therefore we are developing a global standard for software and methodology in highly dependable vehicle systems of future intelligent mobility. To be quick, I just refer a little bit to the objectives from our point of view on future intelligent mobility. I think climate friendliness is an issue. We heard it during the whole day. Reduction of accidents is also an important issue in road traffic. This will be done by driver assistance systems or highly automated driving. Optimization of traffic flow. This will require cooperation between the vehicles and traffic control centers. Cannot be done solely based on individual vehicles. Broader access to mobility in multimodal traffic. As I've mentioned, if you want to organize a transport chain, we need to have communication between the different modes of transport and the partners. And we all know that we cannot solve the issues of congested cities just by automate the cars. They will claim the same space, so we have to change the use of the model split. So some place for the car, for the individual cars, but some place also for public transport. And we have to link all these things together. So interconnectivity becomes a big topic, and also the issue of transport automation, since robot taxis, robot buses, and as we have seen, some new concepts like VTOLs will play a role in future mobility, and therefore this is important. The selection, the challenges for the vehicle architectures are quite high. We have to meet high levels of safety, security, reliability, availability, and maintainability. So the typical RAMS requirements you had already in the aircraft industry, but it's now coming more or less at similar levels to the automotive industry, since higher levels of automation will require fail operational systems in future. Vehicle-to-X and Internet of Things is an issue. Car will become a part of the Internet of Things. We will have cloud-based services, and we have to assure a security of data communication. We have to provide quality of service for such type of communication, otherwise this will not be accepted. And we will have an issue of over-the-air update and upgrade to bring in new functionalities, to modify in case of any errors which exist in the system. So we have to provide flexibility to update our vehicles which are out there. Increasing data rates and volumes will require new concepts for interconnection of the in-vehicle system. So we have developed since many years the so-called automotive Ethernet to allow us to have high data rates. We will use the 5G network for data communication to the outside world. And we will have to deal with centralized multi-core processors which require specific adaptations of the software. This is part of what we are doing in AutoSAR. So the main consequences for the E/E architectures and software architectures are listed here. You see, standardization plays a big role. We want to have standardized interfaces, for instance, for sensors, to have the opportunity to bring in sensors from different companies without changing the whole system. So we want to have standardized interfaces, standards to ensure deterministic and dependable behavior, simulation standards, and so forth. So standardization becomes more and more important and is really a big issue for the whole automotive industry. And I think something what we have learned in automotive industry could probably be even used in other industries like yours. New types of in-vehicle computers are required, as I've mentioned, the needs for performance, flexibility, and connectivity. But, you know, we are not starting from a green meadow. We have already cars running, and so therefore we have to assure backwards compatibility with existing solutions. That's different a little bit to Tesla, which started from a green meadow. We have to think of all the existing solutions and have to have a clear migration path from the current systems to future systems. And we have to have the fulfillment of the requirements for safety and security, as I've mentioned. So if you have a look on the architectures in vehicles, so it started all in the early 70s with a simple number of ECU units interconnected either by specific company-specific buses like the E-bus at BMW, or later on the CAN bus, which then became a larger standard in the automotive industry. Then we had the first steps towards centralization with a centralized gateway to communicate over the centralized gateway between the different parts of the vehicles. Then we started to integrate the ECUs and bring functions together. Still using the central gateway, then the end of 2000, the beginning up to 2010, we had the idea of the domain function. So each domain, vehicle domain, chassis, drivetrain, entertainment, all these domains became separated domains with quite powerful computers on top and smaller ECUs behind, and they communicated over the gateway. And now we are moving to more centralized functionality with very powerful vehicle computers. As I've mentioned, it will be many coprocessors. This is the only way to address the high computing power which we need, especially for higher levels of automation. So there will be even pressure from outside to move towards international standardization, since we will see a lot of international organizations and institutes which are establishing no rules and regulations, so either from UN or ECE or other authorities and national governments will place new requirements. We have to have the homologation, and we have to have an established certification process, and this is only working if we have a globally harmonized development process, processes and methodology. Both methodology and development processes and the certification will no longer be a differentiating factor between companies, since we all have to face the same certification process. So why not having a common standard and defining together the state of the art? When international standardization defines the future state of the art, this is a big advantage which you get for certification if you can really refer to the state of the art, and it saves a lot of costs with respect to verification and validation. So our slogan is collaborate on certification and standardization, compete on implementation, new functionality. So now about AUTOSAR, a little bit a quick introduction. AUTOSAR is a global partnership of leading companies in the automotive and software industry to develop and establish the standardized software framework and open E/E system architecture for future intelligent mobility. That's our mission, existing since the beginning in 2002 for AUTOSAR. And our vision is that we will be the global established standard for software methodology in a few years. We have worked since 2002 and have made a lot of progress since 2002. AUTOSAR started as an internal project of BMW. Then we saw quickly this cannot be done just by one company, so we decided we go for standardization and invite others to join. So we brought in the main players and formed a powerful standard around the world. And if you now look on the partners, we have more than 280 partners, 284 I think at the moment, and it's really the list of names, the who's who in the automotive industry, which is working together. It's electronics industry, it's software companies, engineering companies, really a big part of the industry. And if you look at the numbers, the 20 companies are under the 22 top-selling OEMs and are covering about 75% of the total market revenue. So you see it's a big power now. After 15 years, 18 years of existence, AUTOSAR have reached quite a huge market acceptance. So the big advantages, and it was the idea from the very beginning, to have a possibility of reusing existing software modules and to exchange between the various companies based on the standard software modules and even some ECU platforms between different companies. Exchangeability was a big driving factor. And we had, from the very beginning, the approach to start first with the traditional systems, which had, for instance, in drivetrain or in chassis, high real-time requirements. So we developed the so-called classic platform which can address these real-time requirements very well. It can also address the safety requests up to ASIL level D. ASIL is a specific safety standard which exists in automotive industry, is the ISO 26262, which defines the safety levels which we have to meet. and computing power is rather low, about 1,000 Drystone MIPS. But it's used very much. Classic platform is well accepted. It's many years in place, and in most of the modern cars you are driving, you have computers running based on the AUTOSAR classic platform. What comes now is the adaptive platform, and the first application will come next year, as far as I know. Real-time requirements a little bit lower, mid in the range of milliseconds. Safety criticality can be addressed at least at ASIL B, but you have to see, you can always decompose an ASIL D system into two ASIL B solutions. So it's fully fully compatible to the high safety requests, since we need to have for fail operational to be at any case with a two-channel solution, so we can decompose two ASIL B versions. The computing power is very high. It's greater than 20,000 Drystone MIPS. And you see a third level, third area, it's the infotainment area, which we deliberately left out of AUTOSAR in the past, since other developments had been taken place, like Genevieve was just existing at the same time like when we created AUTOSAR. So we left this to Genevieve, and now meanwhile other things are coming, like automotive grade Linux, Android-based solutions, and we surely will find ways to cooperate with them and to integrate them in the total concept. But we don't have plans to do it by ourselves, since there is enough solutions outside. So the classic platform has, from our point, four pillars. One is the functional safety, the efficiency issue, it's field-proven, and is very performant, hard real-time capabilities. I've mentioned a lot of features. You can read it faster than I can speak. I think this is well established, very well accepted, widely used worldwide, and really already in application. Now the new platform has three pillars. One is safety and security, so we provide a lot of safety mechanisms in the platform, also in-vehicle communication with secured protocols like secured IP secured or DTLS for external communication. We have the possibility to connect, so we basically use within AUTOSAR protocol some IP, which was developed originally by BMW, but is now brought into the standard and available to all participating in the standard. And we allow connections to other systems like DDS and REST. And last but not least, we have the issue of over-the-air update and upgrade, and this is the third pillar with specific modules which allow us the update and configuration during the operation of the vehicles. Here you see the modules of our software platform, and a lot of the modules contain safety features, like, for instance, checksums, persistency of data. We monitor platform health, so whether the memories are working correctly. We have budgeting, monitoring of the usage of memory. We have cryptography. We check whether we get authorized data once we send data to the car. So a lot of modules are built in which address both safety and security. And what is the big advantage in future? I think we all are willing to continue the way, and if we are looking in the different companies, we all see we have the same, more or less the same development cycle. There's not much difference. And if we have such a common understanding and such a standardization, we can work together, we can exchange data which we have. We can have a much better verification and validation of our systems, and we can use testing data from other companies. We can exchange data between the companies. It's a big advantage which will come by this approach. So let me conclude. AUTOSAR offers a comprehensive software framework and a lot of building blocks for future dependable vehicle functions as part of future mobility solutions. Both platforms are compatible to each other and meet high demands for safety and security. And it's a very sound basis of certification. But this is also an opportunity in which we can discuss with people here from the aircraft industry. You have more experience on the certification issue, but probably we can exchange a little bit our idea of standardization, which is probably not so much used yet in the aircraft industry. So thank you for your interest, and I'm looking forward to your questions.
Thank you very much for that. Very technical, obviously, and you're trying to bring your expertise into the aviation industry. I noted that a lot of your statements are about standardization, and that's something that I noticed early on a few years ago, this standardization challenge, where you're having different people writing standards, almost starting a VHS versus Betamax war. I'm glad to say I'm thinking that there's a lot more alignment in the industry now, but again, it is a big issue. Is that something that was experienced in the automotive industry as well, early on in setting standards?
Yes, well, we had at the beginning, I think when we created the whole concept and the idea, also at the beginning there was some reluctancy at some companies, you know, to open and to bring in their own IPs, but at the end all companies saw it, if you have to solve everything yourself, you have to spend such a huge effort, and it will increase the costs so much that it makes no sense. So it's better to agree together to bring in the IP. The IP is protected by our contract, and we work together. We exchange between the companies. Each company benefits from the experience of others, and I think we all have a big advantage in terms of costs, in terms of development time, and in terms of verification and certification.
So the advantages of collaboration. Right, is there any burning questions? Right. Okay. If not, we're going to move on. Now you have a stand down at the far end. You'll notice it's the one with the car, automated car going around in the circle. If you've seen that, go have a look. I had a little look earlier. So again, thank you very much, sir.
It was a pleasure. Thank you.
Right. Brilliant. So we're looking for Thomas Binney. Is Thomas here? No. Just bear with me a second. I am going to decontaminate everything for you. All right. Thank you very much.
Good evening. Sorry, it's a bit late, so I will not take much time. I will just start with my presentation. This is in continuation with what Dr. Gundar has mentioned. So I'll address something which we learned, like which we practice in AUTOSAR, how we handle the challenges with rising code complexity. So I'll have 3 points. I will just skip introduction part because Dr. Gundar has mentioned. So I'll go to the standardization areas, what we adapt from AUTOSAR. I'll just skip few of the slides. So these 3 key points which are main interest for or for the software vendors, like my company, I represent a company named KPIT Germany. So we do software based on AUTOSAR standards. So for us, the standardization of interfaces, standardization of exchange format, standardization of methodology achieved by AUTOSAR help us to enable reuse of software product across the product lines, interoperability with different software vendors, abstracting platform and software for rapid prototyping. So the time required for adapting to a new platform or a new microcontroller, it is very easy because of these 3 factors. I will go in, I'll cover a couple of areas. When it comes to standardization of interfaces, as you have seen in the first session and later, This is our architecture, the AUTOSAR architecture, where the interfaces between the modules, between the layers are standardized. If you go in depth, if you take one particular stack, we call stacks, a group of common functionalities, we call it as a stack. If you take memory services as a common functionality, there are many modules come into picture. AUTOSAR defines how the data exchange between these modules, how the APIs looks like, what is the signature, what kind of data it handles, it gives, and it accepts. So this is well defined in AUTOSAR. This enables a company or a vendor to develop a software which can be reused or mixed with any other vendors from the market. For example, if you take the topmost module, if it is from a vendor 1, you can even integrate with a module or a better module from a vendor 2. So that kind of flexibility is achieved by providing this standardization of interfaces. So when we go into the standardization of exchange formats, AUTOSAR defines a well-formatted method to transfer data between the OEMs, the manufacturers, and the ECU providers and software suppliers. So AUTOSAR defines something called AUTOSAR XML file. This is a format we use to share the data or the requirements or the configuration requirements between companies. So this is just a picture of how the data looks like. It's exactly an XML. It follows some schema and syntax defined by AUTOSAR. And when it comes to the standardization of methodology, AUTOSAR defines a clear workflow, how the input has to be created, how the output has to be created, and an input of one stage has to be consumed. So this is well defined as part of AUTOSAR. So if you can see the first part, system configuration input, this is created by the OEM. He will create it according to cater all the ECUs within his vehicle, and that will be shared to a tier 1, who is an ECU provider or a component provider. He consumes the system configuration, he consumes that particular ECU related information, and he shares that particular ECU information to all his vendors, software vendors. So this is how the methodology is defined, and each stage involves the tooling, each stage involves some automation. Those are those can be developed independently without interacting with these people, because the standardization already defined how the data exchange format should be. So this is just a workflow, how it looks like in a real world view. The middle part, the green part, is how the software vendors looks at these kind of inputs, how they consume from an OEM or an ECU manufacturer, and how they will take the inputs and deliver at the end, we have to deliver a .c file or .h file. I'm just taking an example of AUTOSAR Classic. So as Dr. Gundar mentioned, so these 3 key points enable us to give a ready-to-use software, improve data exchange between OEMs, less complexity. Some people have documents, some people have Excel sheet. Here the data exchange format is well defined. The infrastructure ecosystem can be created independent of a particular OEM or independent of a particular tier 1. And the software, the code, which is highly complex. Previously, we used to handle thousands of lines of code for each OEM, separate lines of code. But here we have a generic code which can be customized, which can be maintained according to the configuration provided. So that is what we, as a software vendor, KPIT could able to achieve from AUTOSAR. Just I'll take 1 minute about KPIT. My company, our Europe center is in Munich, and we currently cater around 8+ OEMs, and we have around 700 engineers working on AUTOSAR products and services. So as Mr. Gundar has mentioned previously, I will skip this slide. So we have AUTOSAR Classic. So our Classic solution is branded as KSAR. So this is our offering. We offer all the modules available up to 4.3.1. We are going to consume the latest 2011 specification in next year. And we have adaptive solution, which Dr. Gunnar has mentioned, for high performance computing. So we have up to 1911 stack available. So all these components, including the tool infrastructure required to use, generate, and integrate, is available with us. Thank you. Thank you so much. Thank you for giving this opportunity.
Quick exit. So AutoSAR has been getting a bit of airtime today. Obviously, we heard from them a little bit earlier, but that's the platform, and you provide all the services, which actually turn it into a deliverable product for. And how many employees did you say you had?
We have 700 dedicated engineers.
700 engineers
working in different programs.
Right. So this is a completely new world for me. It's not something I understand or really get into.
It is not. We are one of the top 3 software vendors, but you can consider the similar other 2 companies are there in the same size. So it's a bigger world.
That's brilliant. I think it's telling in terms of the complexity of the work that actually goes into putting these systems together to make sure that the entire offering works in a compatible way. And I don't understand it, but I'm grateful that there are people like you that are out there helping it out. Any questions from the dwindling audience? No, right. Okay. I'll put you out of your misery. Thank you very much,
Thank
sir.
you. Thank you so much.
Right. So if I understand. Dr. Stefan Schwartz of Bernard Technologies, and I understand that he's got an. Right. I see your face.
Can you hear me?
Yes, we can see you. We can hear you, sir.
Oh, great. Thank you.
Right. Okay.
Yeah, I'm sorry that I cannot be here in person. I'm unfortunately a little bit ill, so I'd rather stay off the.
Fair enough. I'll just hand straight over to you, sir. So please take it away.
Okay. Thank you, and thanks for having the chance to talk to you here. I'm trying to share my screen. I hope that this will work. So, can you see everything?
Presentation mode, though.
Okay. Yes, we can see you. All right, perfect. So, yeah, thanks again for the chance to talk to you. I want to quickly go into detail of what we are at the Bernard Gruppe, and I want to give a slightly different angle on how to the requirement of the infrastructure in order to allow autonomous driving. The Bernard Gruppe is a company that is about 40 years old now, and we always worked a lot on infrastructure and planning and realizing infrastructure for all kinds of mobility. We are located originally in Austria, and now we have 13 sites in German-speaking countries, and we are also internationally. We also have international projects all over the world where we realize infrastructure projects. Just very quick outline, we start really from feasibility studies, and we work on environmental impact studies. We do structural examinations. We also, in the planning phase, we do a whole general planning all the way down to execution plannings, where we can prepare for everything for infrastructure tenders for public sector. And also for the realization part, we usually are involved with the project management and the controlling, the site coordination and construction supervision, and a lot to do with the monitoring side. And the monitoring side is basically what we want to come into now. Just very briefly, we have 4 sectors: energy, industry, infrastructure, and mobility. The last with energy is everything about power generation, consumption, and transport. Industry is a lot about measurement techniques and research, and also the production of intelligent systems. Infrastructure is mainly about building and planning tunnels, bridges, and so on. And with the mobility, we concentrate on planning streets, railway lines. We do a lot about mobility concepts, optimizing the traffic flow and traffic guidance systems. And this is basically the background we are coming from. And more, our industry also goes towards the autonomous driving and vehicles. And our standpoint is that also the infrastructure side needs to be prepared for that. So it was very interesting to see the automotive side of it, because I think there's a lot of interaction required. And for us, when we talk about autonomous driving, we typically start with digital twins, where we want to make a digital system of our road. For example, here is an autobahn in Austria, where we have different sensors where on the autobahn, which allows us to track the vehicles and create a digital twin of this sector. And based on this, we can analyze the movement of the cars, and we can identify dangerous scenarios. And consequently, this will be the basic data that you need to allow autonomous driving. Here is a model that has been generated by one of our partners in a research factory. I hope the video works. It's basically a high resolution map that was taken, and based on this digital model, we can then implement live traffic data onto the road and analyze the trajectories. This has all been done quite thoroughly nowadays already on the autobahns. The problems we see is now when you go into a city. For example, here, based on a normal intersection, turning right, very often it's not very easy to see danger or traffic participants coming from the right-hand side. Here is an example where this has been tested. Turning right for a vehicle here is basically a nightmare. You have an additional bicycle line that is between your forward line and your turning right lane. And while an autonomous vehicle will have sensors based on the car, it will easily be able to detect any dangers or any dangers surrounded by him and react to that. The problems we see is when there is a traffic participant coming from out of the line of sight, and if it comes quite fast speed towards the intersection, it may be too late for the car to actually see it with sensors based on the car. So what we propose is a sensor that is required on the infrastructure that is looking into these like dead angles that you see. This, I think, has been established more and more nowadays. For example, also for the turning right for the trucks, which don't see bicycles. So this is already a human error that you witness, but also for autonomous vehicles, I think this is a requirement that will enhance your traffic security. For this, we propose a system that we developed in-house. It's actually based on an optical system, and the thing here is that the video material is directly evaluated inside this processor. This means that no video is recorded or transmitted, and therefore you don't have any problems with your GDPR compliance or any other safety data protection issues. And coming from the infrastructure side, what we actually used to do is we use this to count traffic participants, and it allows us to classify 8 different participants, starting from pedestrians and bicycles to motorbikes, cars, buses, vans, trucks and trailers. And what we can do is we can follow the people and the traffic participants, and we can draw the trajectories of those people and of those traffic participants with this. So here you can see a live video demonstration of this, where we can detect from where to where they are going. We can also establish a speed for those traffic participants, and based on these trajectories, it allows us to extrapolate those and give some warning signs in case there are some dangerous scenarios occurring. Furthermore, it allows us to identify problems of the infrastructure. For example, cars slow down or hit the brake very hard repeatedly on the same intersection. That means that obviously there must be something not very obvious for the drivers, and so this allows us to target these trajectories and enhance the safety. So what we can do furthermore is, apart from just following those people, it allows us to completely analyze the whole traffic or this whole intersection area. It allows us to classify different vehicles or different traffic participants. We can see if there is waiting times, if there are queues, if there are accumulations. We can see we can analyze people flow, and this basically gives you a whole overview of what is happening on the traffic, like on an intersection in real time. The way this works is the image captured from a camera is basically loaded onto a flash memory. Based on that, we have an optical detection, and based on artificial intelligence, we teach or we train the system to classify into different classes. So we can, based on the features of those different participants, we can classify and then count and track those individual people really anonymously. Apart from traffic counting and traffic flow, this also allows us to analyze the public transport or movement patterns of people, and also allows us to monitor the parking spots. So here, for example, it allows us to analyze how many people are getting on and off the bus, how many people are waiting there, and are there crowds starting to occur because this also is an effect of traffic safety. Lastly, I want to quickly go onto the parking monitoring, where we say the imaging capture of the static traffic is also the same as for flowing traffic. So we can also identify parking spots here, and it's the same principle where we can then really spot by spot identify available and occupied parking spots, and give this information really to the car in real time. And furthermore, the big advantage of this is that this is basically a single spot sensor that you have inside a parking house, but we can also have this along the road, where you can measure on-street parking, and based on that you can cover a much larger area of your parking guidance systems, and also identify this as potential threats, because cars that are parking on the street are typically a good interference to your traffic flow, and also another dangerous also arise dangerous situations. So basically, to summarize, what we wanted to show here very briefly, and is that we believe that going through that the infrastructure-based sensors will be a critical situation or a critical part to enhance your traffic safety, and is a requirement to allow for autonomous driving, because only with additional sensors we believe that you will have enough safety to allow fully autonomous vehicles. So thank you very much.
Very much, sir. Right, we're a bit thin on the ground here at the show, but that doesn't necessarily mean that we haven't got tens of people watching online, because this is going out via YouTube. So if you're on the internet, hopefully Mr. Brian Gessler, the managing editor of eVTOL Mag, is there. Hopefully he'll be able to put in a shout out for the show. So in terms of the service that you guys are offering, one of the things that I look at is the vertiport infrastructure and how we have to try and integrate it with the public transportation systems. I'm very interested in the modeling that you're doing to try and improve the safety of passengers when they're on the road or using public transport. Is that a growing market for you in terms of what you're doing?
Yes, definitely. So obviously you want to, or what's coming more and more is that people want to improve the public transport in order to get rid of cars inside the streets. So a lot of the things that we have to do is we make sure that traveling for people will be as efficient or even better, and as safe or even more safe. So obviously the security part for public transport is a big factor, and it's actually especially in Germany with all those limitations about air quality, it's becoming more and more a topic.
Brilliant, okay. There was a presentation earlier today about the incidence of using micromobility, and the observation was that as micromobility modes of traffic increase, the use of public transport decreases. So you're just having the shift of mode from one mode of transport to another, where I think the goal is trying to get more people onto public transport. Is there anything that you would be doing or advising cities to help increase the abandonment of personal cars to using public modes of transport?
Yeah, so basically the goal we typically set is that we want to make public transport more efficient than the cars, rather than making cars less efficient. You know, there's always two ways to go. People typically use the way with the least resistance, if you wish. So you can either increase everyone's resistance and make it harder for everybody, or you can improve it for everybody. Our approach is that we want to enhance public transport with really worked out concepts where we analyze how you need to organize your parking, how you need to time your public transport, and what's coming more and more is actually individually triggered public transport. So depending on either real-time data or historic data, the timetable is adapted to work the public transport more efficiently. So there's a lot of intelligent
well, that's brilliant. Thank you very much for that, sir, and best of luck. Thank you for joining us.
Thank you.
Cheers.
Yeah, thank you.
Right, okay, we're moving on to our last presentation of the day. It's one that was sprung on me. I didn't know anything about it. You may have noticed that we have a young team of students here that are developing an electric aircraft. They're going to come here and tell us all about their program. So I'll let you do all the introductions because it's your show. Cheers.
Well, thank you very much for the introduction. Welcome to the presentation of the EastLink Focus Project at the Airtec Munich 2020. My name is Alexander Weiser. I'm a mechanical engineering student, a master degree now. I'm at the Swiss Federal Institute of Technology, and I co-founded a project which now builds the first four-seater electric plane with modular batteries. You may ask, what is a focus project? Well, a focus project is a very unique concept of the Swiss Federal Institute of Technology in Zurich. There are 12 students. They have 8 months' time to develop a very innovative product. This is a full-time project for them. That's not a 9-to-5 job. That's 150% commitment, effort, and work. Well, what can you achieve in that time? I don't want to tell you about every project. That's way too much. We have Hyperloop. We have Aris. We're building a supersonic rocket. We have an electric race car. But we also have, for example, an electric motorcycle. 2017, within 8 months, 12 students built the first electric bike with 2 wheel hub motors. What does that mean? Well, we have a higher recuperation efficiency over the entire system as we can brake with the front motor, and therefore the students were able to have a motorbike which has a range of 400 kilometers plus. The students in that time developed their own electric drivetrain with a special focus on the battery management system and on the motors. And then we used that to have a second project. The second project, the E-Tech City, was basically an advancement, an improvement of the E-Tech Alpha. They now decided to put a focus on a more city user case, and they now put a new focus also more into the motor. They have a special developed motor exactly for that type of motorbike. Further, the battery management system, inverter, human-machine interface, everything was improved. Well, the E-Tech Alpha actually was kind of a kick-off. We noticed there is no electric aircraft, or we didn't know. And then we started looking and started with a feasibility study. Nikolai Solenthaler and me had the task to make a feasibility study and develop the first concept for an electric aircraft within ETH. While Nikolai Solenthaler was on the task to develop the entire aircraft concept, so the packaging, where to put something, which wings are we using, what is the general concept of the aircraft, I was on the task to develop the drivetrain. And we achieved a very good product by using innovative technologies. And, well, for electric aviation, we have to think outside of the box, and we did that. The JTEC pre-study concept has a range of 485 kilometers, can carry 5 passengers plus 1 pilot, and has a battery capacity of 210 kilowatt hours. That at a maximum takeoff weight of 2.2 tons. Now, we used that concept and went around the world and looked for partners. And we actually also entered a competition. The SERP Design Challenge 2020 had the goal to use technologies of Industry 4.0 to improve wildlife surveillance, to stop poachers more efficiently. And we entered this competition. It was carried out in May 2020. Actually, it was planned at Krüger National Park with the wild park rangers live there. We had to do everything online, and still we were able, from Switzerland to South Africa, to, well, convince the panel of experts and to gain the first place with our project, showing that silent aircraft, which are easily chargeable on the ground with solar technology on the roof of the hangar, for example, that they are usable for wild parks and wildlife reservoirs all around the world. Well, we used all of that to start the eSling project. And for that, as I said, we went around the world and looked for partners. And in September 2019, we found Sling Aircraft. Sling Aircraft is a kit manufacturer. They are based in Johannesburg, South Africa, and they are a very fond partner of us, and they help us a lot, and they are on the project 100%. We actually made, with our models from the pre-study, a first concept of the different, very rough concept of the different aircrafts that Sling is offering. And then in the end, we found out that the Sling TSI model is the best model that we can have for our project. Well, who is carrying out the project? It's a core team of 12 students. There are top-notch students, best in the class at the last bachelor year. 9 mechanical and 3 electrical engineering students. They're supported by a team of 5 industry experts and 1 academic tutor, which is basically the connection to ETH, helps out at all the parts that we need. Well, we are using a fuel burning model and electrify it. Why? Because ETH doesn't have its own aviatic department. That's also why we had to do all this pre-work, the pre-studies. And if you're using a fuel burning plane, we have to modify it to have a high efficiency and actually to fit the entire thing into the aircraft. Now, I was for that purpose in South Africa at the beginning of the year. I took the rough concept, made it a little bit finer, put up a few notches, and then I decided to put in the batteries in the old fuel tanks. So I kicked them out, put in new battery fuel tanks, and then also for a new cruise velocity that we have, we need to increase our wingspan to fly more efficiently. The second placement for batteries is also in the motor compartment, and then we have our optional range extender. So if we have only 2 passengers, then we can take out the back seats and put in range extenders, also batteries, to have a higher range. What are the advantages of E-Sling? Well, the E-Sling, obviously environment. We have our CO2 emissions reduced by 100%. We have our noise emissions reduced by up to 75%, especially during the starting phase, which is, well, for most people the most important phase because they live close to an airport. Next thing, economics. High energy efficiency plus low maintenance costs for the electric parts results in operative costs sinking by 40 to 60% compared to a fuel burning model of the same size, depending on your user case. Now you may ask, well, that's standard for electric vehicles. Well, what makes us special? Our exceptional values are modular batteries. We can take them out, put new batteries in, no charge time, we are back in the air, quick turnaround. We have an innovative cooling system. We have a battery range extender which we can just simply plug in and reach higher ranges. For an electric aircraft, we have an enormous range of 350 kilometers for the 4-seater. And then, last but not least, our project setup. ETH is one of the top 10 universities in the world. We take the best students, put them together with established industry partners like ABB, Airmaster, Sling Aircraft, and on and on and on. And then we will reach up with trend-setting research, putting in new records, new heights in electric aviation. Now, 8 months, how are they? I'm just going to show you a rough concept how we splitted them up. First of all, we had a team, we had a little bit brainstorming, team building, and we are now deep in the development phase. At Christmas 2020, we'll actually have the design freeze of our electric drivetrain. At that point, everything has to be designed. And then we will put our parts on a test bench and put them through their paces. After that, we assemble the aircraft, and then in May 2021, the entire aircraft will be rolled out to the public, first seen in end of May 2021. During the entire time, we're working together with the Swiss authorities to be sure that our parts are actually able to be certified as an experimental aircraft. And with that, we then will be quite quickly be able to start our maiden flight of E-Sling. Now, what are we developing ourselves during the project? Well, in one word, the electric drivetrain. Well, that's actually 2. So, what is in there? Motor, inverter, battery. The cooling of all 3 of these things, plus the battery management system and the human machine interface. That's our focus, and we're going to develop everything special for the E-Sling so that we have the best product available for this aircraft type. Where are we developing this? We are based in the Innovationspark Zürich. It's in Dübendorf, Switzerland, a little bit outside of Zurich, with direct access to the local airfield, so we can start our tests right there out of the hangar. What is the Easling in numbers? Well, we have a starting power of 110 kilowatts. Sorry. We have an energy capacity of 55 kilowatt hours. With the range extender, we are up to 80 kilowatt hours, a range of 350 kilometers, at a cruise velocity of 160 kilometers per hour. The maximum takeoff weight is the same as the one of the Sling TSI at 950 kilograms. And what we are doing, I just want to really stress it, we are developing the first four-seater electric plane with modular batteries. And that's, well, it's end of September, the pictures, but that's basically current status of the production of the airframe. The airframe is produced in Africa. We are actually expecting it to be in Switzerland at mid of November. And we have to thank a lot of people, a lot of sponsors. First of all, Sling Aircraft, now on the project for an entire year. CAT FM, Swiss World Cargo, Designwerk, ABB, Airmaster, obviously for the propeller, and the Live Your Dream Foundation. Now, I want to ask you to become a partner and to join the future, to join electric aviation, to join a sustainable world. And, well, take out your phones, read the QR code. You are directly on our webpage, and then you can get in contact with us. You can get in contact with us on many social media, on the webpage. Just go out, ask us about anything you want to know about the project. And if you want to join us as a partner, you're very welcome. We are a student-driven project. We are a research project, so we are depending on sponsors. So I'm very happy if you come up to us and talk with us and want to help us out and, well, join the future. Thank you very much.
Oh, don't go away. I have questions.
Good.
We may be thin on the ground, but I do follow the space quite closely. So start 8 months, May next year, you want to be flying.
May and next year, the aircraft is completely assembled.
Oh, May completed,
and
right.
ready to fly. And
Yeah.
then we obviously have to wait on the Swiss authorities to give us the permission to fly. But as we are working hand in hand with them, we hope that it's quite fast.
Yeah.
But obviously that's a process that we cannot define how long it takes. It takes as long as it takes until it's safe.
Yes, well, that's the devil's in the detail there, isn't it?
Exactly.
Is there any questions in the audience that's not from your colleagues?
Yes, please.
Yeah, I'm a pilot and I'm interested in flying electrical. There is, of course, existing electrical sports flying around, PP Vestral or the Siemens activity before. So what is your difference? Just the four-seater concept?
So the huge difference is we are going four-seater.
And the
That's
modular
nothing
battery.
that has happened, and the modular battery
The
system.
modular
So
battery.
we are able to have quick turnaround times on the ground,
Right.
and we are able to extend the batteries and have higher ranges through that. And that's the huge difference to other projects which are currently upcoming, but obviously huge kudos to Pipistrel, who are the first ones who ever made and certified aircraft, electric aircraft, which is amazing.
Yeah, and Tecnam is now also in the process.
Yeah.
Now, I wish you all success and I wish you a lot of
Thank you very
partners.
much.
Right, any other questions? Right. So the funding that you're getting, this is obviously from the partners that you have in there. They're contributing funds. I'm assuming that they're also contributing equipment for the project as well. So very, very collaborative between the universities and industry. Is that the model that you're using here?
Yeah. We're working closely together with industry. That's the goal. That we help each other. That we are able to give them something new technologies, and they are giving us their experience, and sometimes also parts and maybe monetary funding, depending on what they are able to give currently.
Right. And then long-term goals and objectives. So you come to the end of your program. You've developed your drivetrain. Are you going to look to commercialize, spin-off, or what's your future plan? Where do you see the team in 5 years' time, say?
Well, where do I see the team in 5 years' time? Hopefully everyone is finished with their masters at ETH.
Hope so.
And then I think we have to see. We have to fly it. We have to test it very thoroughly. And spin-off is always an option, obviously. That's common at ETH. They're very successful spin-offs. And if we can join them, we are happy to do that. And as a business case, I mean, basically, this aircraft is ideal for training flights. You have short flight hours, like 1 to 1.5 hours of training, and you can land the plane, take out the batteries, put a new, and then the next pilot is in the air and is trained. And because of the low cost, it's very, very nice for, well, all these schools teaching pilots in the future.
Yeah, it's interesting. In the UK, I heard of a flight school that was actually looking to be established specifically for using electric aircraft. So I am hearing rumors of this type of operation, that kind of requirement. Right, so if I gave you a blank check, would that accelerate things? Or you're with your 12 students, is it just about money, or is it about expertise that you would really need to bring in to deliver it?
It's about both, but the expertise is there. We have the projects where we have all the developments, so we're using this knowledge. But yeah, we need also money to go on events like this, to present ourselves, to present obviously also our sponsors, and yeah, to buy different things where we don't find partners to help us out with the components. So yeah, a blank check is always welcome.
A blank check. Everybody always likes a blank check. Right. Okay. And you guys are on the stand just, I think, over here.
Just around the corner.
So at the front. So if there's anybody who wants to go by, and of course for those tens who are watching us on the internet, we had their QR code. You'll be able to go back to that and look them up. So, thank you very much.
Thank you.
Right, and with that, I think I am going to draw to a close the Airtec Munich conference. Thank you very much, everybody who took your time to come and see us. Actually, in the flesh, so to speak, the first face-to-face B2B meeting of 2020, given everything that's been going on with COVID. I think is a testament to Airtec Munich in that they were able to attract this many people and put in the safety requirements so that we could have a successful conference. So again, Airtec Munich will be hosted next year, hopefully under a lot less restrictive conditions. And then, as I had said before, we also have the GUAS Air Summit on the 7th and 8th in September next year, and that's put on by Farnborough, which if you rewind the YouTube bit, you'll be able to find the links to that. But just you can follow me on Twitter. I'm a close partner with the GUAS and Farnborough airport side. So with that, thank you very much.
to us. He's a smooth operator.